So good morning all. So it's day 3 of the conference, Physics Frontiers 2024. So before we start, I just want to thank all the participants and the organizing committee of this conference for supporting us during the first 2 days of this conference. So thanks a lot to everybody. So today we have 4 sessions in which 4 plenary speakers are going to be joined with us to share their research works. So without further delay, I just want to welcome our first plenary speaker, Dr. Debajyoti Dutta sir from Bhattadev University. So welcome you, sir, to this conference. So I just want to give a brief introduction of Debajyoti Dutta sir. So Dr. Debajyoti Dutta has obtained his PhD degree in physics from Guwahati University after completing the master degree from Delhi University. So later he joined as a postdoctoral fellow at HRI Allahabad. Dr. Dutta then appointed as an assistant professor in the Department of Physics in Assam, Don Bosco University, Guwahati. Dr. Dutta has been contributing immensely in the field of high energy physics and particle physics. He has published many research articles in prestigious journals like JHAP, PRD, etc. So it's a pleasure to have you, sir, in this national conference.
Thank you, Darpan. And thank you so much for giving me this opportunity to talk in this conference. And I'm really happy, and I have seen the way you are organizing this conference, and it seems to be a very successful one for the students and research scholar of this northeastern area as well as from the outside. So without further delay, so if you allow, then I can start my talk and share my screen.
Please
Yeah,
continue.
okay. Okay. Okay, is it visible?
Yes, sir, it's visible.
Okay, so I have to, if you don't mind, I have to sometimes off my camera because my internet is not so good. So please don't mind about that.
Okay, sir, no issues.
Okay, so just so it is visible, right?
Yes, sir, it's visible.
Okay, okay, okay. So let's start. So good morning, everyone. And again, I'd like to thank the organizer for giving me this opportunity to talk in this conference. So my topic of presentation today is neutrino oscillations, past, present, and the future. So I'll try to cover some part of the historical background as well as the present status of neutrino oscillation physics, and also what is expected in the very near future from the different neutrino experiments, so that I'll try to explain in my talk. Okay, so this is the outline. First, in the introduction section, I'll be talking about historical development in neutrino physics, and then I'll come to neutrino oscillations. There, I'll be discussing about a little bit of theory as well as the different experimental prospects, and then issues and present status of the neutrino oscillation physics, and then future prospect, and hence the conclusion of my talk. So this is the outline. And so in the this is my very first slide. So where let's start with the very popular plot of beta decay. Okay, so if you see this plot, so here it's a blue line, which is the continuous spectra. It is the kinetic energy spectra of the beta particle, which is varying between the energy 0 to the Q value. So it shows that electron, it shows the kinetic energy spectra of the emitted electrons. But now, if it is the observed spectra, but it is suppose before the discovery of neutrino, or before the prediction of neutrino, so when beta decay was studied, so at that time, so the expected curve should be like the spike that is occurring at the end of the curve, end of the this spectra. Okay, because the beta particle which will be emitted in a beta decay, so that should carry all the energy. And if it is carrying all the energy, then it should appear at the end at a particular fixed value of energy. So that is what expected, but we didn't got that. What we see is that it is a continuous spread of an continuous spectra of energy distributed between 0 to the Q value. So this already uh, uh, confirmed that there is some problem with the beta decay. So we need some new particle, new additional particle to establish this curve, because here there is a sharing of energy of the beta particle with some other particle. So to confirm that, not to confirm, but there are other three reasons to believe that in this part, in particular decay, it's a three-body decay. So one particle going to decay to other two particle. So if it is a three-body decay, then there is a violation of energy, momentum, and angular momentum. Because from the angular momentum point of view, it is the electron which is spin half particle. So to accommodate that, to conserve the angular momentum, so there should be some particle which is also having spin half. Okay, so keeping all this point in mind, so in 1930, it is Pauli who hypothesized the existence of a new particle, which is later called neutrino, to account for the energy momentum conservation as well as the angular momentum conservation in the beta decay. So that means that this experimental data actually forced Pauli to assume the existence of a new particle. But at the time of discovery, Pauli was very certain that it would be very difficult to observe this particle, because, and that's the reason why he said that it's a ghost particle that I have talked about. But based on the Pauli's hypothesis, so it is Fermi who developed a theory of beta decay by 1935. And he postulated a universal weak interaction constant, that is ZF, we use, and it is called Fermi constant. Okay, so now after development of Fermi theory, so it was seen that it could predict the spectra of various beta decay with proper accuracy as given by the experimental observation. So it is already confirmed that there is emission of a particle which was not earlier, about which it was not talked in the earlier stage, and it was later called neutrino. Okay, so this is the first theoretical development in the neutrino physics. And then let's talk about the detections of neutrino. So the theory is ready now. Experimentally, although Pauli said that it would be very difficult to detect this particle, but people are not sitting, so they start looking for this particle. And in that process, so when you because neutrino, it's a particle which is not interacting too much, so it's rarely interact. So that's why the difficulty arises. So so the people, experimentalists who are looking for detecting neutrinos, so they have to look for higher flux source of neutrinos. So that's why they started with in the very early stage, they were to produce high flux of neutrinos, they were talking about using atom bombs also. But that idea was rejected later. But then instead of atom bomb, so one scientist at that time suggested that let us use nuclear reactor. Okay, so then this group of scientists started using nuclear reactor, which through the inverse beta decay reaction confirms the existence of neutrinos. Okay, so this experimental setup, so this is the inverse beta decay reaction where proton in the final product, so we have the positron and the neutron. So in the so this proton, then this positron in the detector when it is created, so this positron annihilates immediately with the surrounding electrons, and then it produces gamma because pair annihilation. So in that gamma is being detected in the detectors, and that detection of that gamma confirms that there are antineutrinos produced in the nuclear decay. So in short, I'm just explaining this slide. So let's go to the next slide. So this is the group, Kawan and Renins. So they did this experiment in 1956, about which I talked in this slide. So it is the inverse beta decay reaction, and they have confirmed that they have detected neutrinos. So after their result, so after they have got the success, so then they wrote to Pauli. So this is the famous letter written by them. So they write to Pauli, we are happy to inform you that we have definitely detected neutrinos from fission fragment by observing inverse beta decay of protons. So this was the letter, and this is the group of people with these two Kawan and Rins. So these two scientists. So I took this photo from YouTube. Okay. So now the thing is that once neutrino is detected in this reactor experiment, so then another group of people, so they also were looking for neutrinos. So that group was led by Ray Davis. So Ray Davis was a chemist actually. So he's a chemist, but he was very much interested in neutrino physics. So the development that was going on in that particular era, so he was very much interested. So now what he planned is that, so when the other group, so Kawan group, so when they were working with the reactor experiment to detect anti-neutrinos, so he also set up a detector near the same reactor. And that detector is filled with 3,800 liter tank of carbon tetrachloride. Okay, so and his aim was to detect argon through this particular reaction. And he was expecting that nuclear reactor that the other group was using, so that will emit neutrino. Okay, so this was his expectation, and he will get argon. But as a result, he didn't see any argon atom in the detector. Okay, so the detector was filled with carbon tetrachloride. So he was expecting that it will observe argon, but his experiment failed. So his failure leads to the understanding that the neutrino and antineutrino have different interactions. So they are not same, because in the previous experiment done by Kawan group, so they have discovered antineutrinos, but neutrino is not discovered when the detector is placed near the same reactor. Okay, nuclear reactor emits antineutrino, and hence Kawan group saw the signal, but Davis reaction required neutrinos, hence this experiment failed. But Davis was the person who was very much interested in neutrino physics, and that's why he didn't leave the hope. So he then started a new experiment, his next experiment. So this experiment, in this new experiment, he used massive 650 tons of detector to observe solar neutrinos, and he was looking for electron neutrinos, because the solar is the source of sun is the source of electron neutrinos, and he was expecting that he will be able to detect solar neutrinos. Now so with this huge detector, he was detecting neutrinos, and this detector was set up in 1967 in Homestake mine. And so after detecting electrons, he faced a problem. The problem is that, so solar neutrino flux was much lower than the expected. So so he set up the experiment. So this is the experimental site. This is the experimental site that was set up by Davis. Okay, so in that experiment, he was expecting, let's say, suppose sun is producing 100 electron neutrinos. He was expecting that there should be 100 electron neutrinos in the detector, but it was much lower than his expectation, what he was observed. So observed rate is only 1/3 of the predicted rate. So that's a bad news. And this is the starting of the solar neutrino problem. Okay, so Davis did his calculation, he rechecked his calculation. He was a it is said that he was a very he did his calculation very neat and cleanly, but he couldn't find any error in his calculation. So he rechecked and rechecked, and for 30 years he continued his research in neutrino physics. And then, but he said that no, there is no errors in my calculations or in my estimation. So everything is perfect, but there is something wrong happening on the way while neutrino is traveling from sun. So his idea and his prediction is totally correct, and it was proved in 1989 by Kamiokanda detector, who's for the first time detected the who for the first time confirmed Davis result, saying that yes, there is some deficit, and that deficit is in the observed rate as predicted. Okay, so in 1989, so it was the Kamiokande detector, and then in 2001, it is the SNO Sudbury Neutrino Observatory, which also reconfirmed Davis' prediction, and it also said that yes, that the neutrino is whatever expected. It is not getting, we are not getting that in the detector, and it is because of neutrino oscillation. So I'd like to join one sentence here that during the 1970s or 80s, so people were theoretical development was going on regarding this, what is happening. And then it was predicted that the neutrino oscillation theoretical prediction is already done by Pentacorvo. So they were saying that, yes, so neutrino can oscillate. And if neutrino oscillate, that leads to a very strong and that neutrino oscillation means neutrino have mass. So that means, which is in standard model, neutrinos do not have mass. So this is a new confirmation that neutrino have mass. So these two experiments are very important in the history of neutrino physics, because they for the first time experimentally proved that neutrino oscillates. And for this, his study and for his report, he Davis is he was given Nobel Prize. A share of Nobel Prize was given to him in 2002. Okay, so now this is all about the electron neutrino. Davis experiment was the first experiment to detect electron neutrinos. Let's talk about atmospheric neutrinos. So atmospheric neutrinos, they are being created at the top of our atmosphere because of the interaction of the cosmic rays with the atoms at the topmost atmosphere. So here you can see in this figure that during the cosmic ray interaction, we get pions, and then pion gets decaying to muons, and then again on the travel, muons decaying to electrons, producing muon neutrinos and electron neutrinos. So they are the end product, and these muon neutrinos and electron neutrinos and antineutrinos, they were reaching the ground. So if we set up detectors in the ground, so then it will be possible to detect atmospheric neutrinos. So now there were, as I said, in 1917, in that era, so people are talking about the GUT, Grand Unified Theory. So they were talking about the unification of strong, weak, and electromagnetic force that was proposed, theoretical proposed. And as a result, so people start talking about proton and neutron decay. So it now as the theory developed, proton decay and neutron can decay, and it should decay. So now if they are decaying, so we have to detect them experimentally. So again, people start developing experiment for detecting this proton decays. So in that process, this actually Kamiokande detector has been set up, so about which I have already talked here. So Kamiokande detector, so the purpose, it was an atmospheric neutrino detector. So it was set up, and okay, so now this Kamiokande detector, they were, as I said, at the topmost atmosphere, we are muons are the pions getting decayed to muons, and then muon getting decayed to electrons. And hence we are getting the neutrinos, muon neutrinos, electron neutrinos. So this is confirmed, and the Kamiokande collaboration and IMB collaboration. So they have confirmed that they have detected atmospheric neutrinos. So they were the first experiment to detect. But at the same time, they have reported another problem that is named as atmospheric neutrino anomaly. So this is a similar kind of problem that happened with the solar neutrinos. That was called solar neutrino anomaly. So here it is atmospheric neutrino anomaly. So in the same in this atmospheric neutrino anomaly, so the detectors were detecting less number of neutrinos as expected. So that means there is some deficit in the detection process. So in 1998, a very large detector is set up that is called Super Kamiokande. So it is much bigger than the Kamiokande detector. So you can see the detector size here. So this is the Super Kamiokande detector, and this detector is filled with 50,000 tons of ultra pure water to detect neutrino interactions. And these are the PMT sets up at the walls or edge of the detector. Okay, so this was 20 times bigger than the Kamiokande detector. Okay, and so this detector reported that there is deficit of atmospheric neon reaching the ground. So this is another way of confirmation of oscillation of atmospheric neutrinos. So that means neutrino oscillation has been confirmed by solar neutrinos and atmospheric neutrino oscillates. And since neutrino oscillates, so they have mass, and this leads to some new theory. Okay, so and this theory was, as I said, it was neutrino oscillation was already theoretically predicted by Pentacorvo. Okay, so neutrino oscillation reported by Super Kamiokande experiment and SNO experiment. So as I have already discussed, so in 1998 it is Super Kamiokande, and then in 2001 it is SNO. So these are the two leaders, Professor T. Gazita and then Arthur McDonald. So they have been given Nobel Prize for their contribution in the in neutrino physics, and they have been given Nobel Prize for neutrino oscillation in 2015. Okay, so with that, let's come to the sources of neutrinos. So neutrinos, we encounter neutrino. It's every second in our day-to-day life. So trillions of neutrinos are passing through us. Okay, so but they are not harmful. Okay, anyways, so sources of neutrinos. So we have solar electron neutrino sources. Sun is the sources of solar neutrinos. So PP through the PP cycle, they produce electron neutrinos. Again, atmospheric neutrino, as I have discussed. So cosmic rays are the primary sources. They hit the upper atoms in the upper atmosphere and produce the atmospheric neutrinos. Now, reactor neutrinos. So it is reactor neutrinos are produced by man, and we produce reactor neutrinos through fission reaction. And so another source is accelerator neutrinos. So there are only two artificial source of neutrinos, that is man-made source, that is reactor neutrino and accelerator neutrino. Okay, so in the accelerator neutrino, we use a high intensity proton beam to hit a target. So target during that process, so we calculate proton on target. So proton hits the target, and in the process, pions are created, and then pions decays to muon, and during that, muon neutrinos are produced. Okay, now in reactor experiment, the maximum energy we can reach is of the order of the 3 to 10 MeV. Okay, so we cannot go beyond that. So okay, so how many time I have, Darpan? Are you there? I think I have 5 minutes, so I have to go a little fast. Okay. Okay, so in the reactor neutrino, so we have this fixed energy. So only variable what we can do is the baseline. Okay, but there is also a constraint on what baseline we'll choose. Okay, but in case in accelerator experiment, we have the freedom to decide E and both E and L. Okay, so based on that, we can calculate the ratio. We'll be talking about that in the coming slides. So neutrino detection, there are two processes: charge current interaction and neutral current interaction. So in the charge current interaction, it is the W plus minus boson, which is the mediator, and here in the neutral current interaction, it is the Z boson, and it is detected through recoil measurement in the final state. And when neutrinos comes to the detector, so if it is electron neutrino, we'll be looking for the counterpart leptons, that is electron, and if it is muon neutrino, then we'll be looking for the muons, the counterpart charge lepton, because we cannot detect neutrinos directly. We have to detect the counterpart leptons. So for that, in Cherenkov radiations will be produced, and we'll be getting fuzzy ring if in case of electron, and we'll get clear ring in case of muon. So this is the process that's experimentalist handle while detecting neutrinos. So this is the theory. Let's come to the theory of neutrino oscillation. I'll go quickly through this, and here so this is the very basic quantum mechanics equation, and so on the left hand side we have the flavor eigenstate and the mass eigenstate. So flavor eigenstate must be expressed as a linear superposition of mass eigenstate, and then U is the mixing matrix. So it is the PMNS matrix, as most of you know this, and this is the evolution of this is the time evolution equation, Schrodinger equation. So here Hamiltonian is the square root of mi square plus pi square. So when you put that, you'll get the evolution of states. So how the states evolves, you can calculate through this equation. So from that, what we can calculate is the probability. So in neutrino oscillation, this probability is very important because we deals with the probability, and from there we calculate the number of events, and then we talk about the chi-square analysis, whichever we will come to that later. So probability. So probability is calculated through this from the evolution of states. And then this is the survival probability. So what is survival probability? So if electron neutrinos is created at Sun, and we are having a detector here at the Earth, so when electron neutrinos is traveling this distance, so due to oscillation, we will not get all the electron neutrinos here. There are some electron neutrinos will be left out to the detector. So how much electron neutrino is left, that is given by survival probability. So this is the formula to calculate survival probability. Now I'll not go to that formula. So to simplify the statement, so I'm considering the two flavor scenario where I am assuming that we have nu E and nu mu, two flavor state, two orthogonal linear superposition of two mass eigenstate nu1 and nu2. Okay, with masses m1 and m2. So if that is the case, so this is the survival probability. P alpha, here alpha is E and beta is also E, because we want to see how much electrons left out, electron neutrinos left out at the detector. Similarly, it is P mu mu. So in this reaction, in this expression, you have seen that I have some parameters, that is theta, sine square 2 theta times sine square this particular term. This is the phase term, and this is L by E, about which I have talked little some time ago, and del m square, that is the mass square differences. This square of the m2 square minus m1 square, that is del m square. So del m square drives the oscillations, and theta is the mixing matrix, mixing angle. Okay, so in two flavor case, we have one mass square differences and one mixing angle. And but this parameter delta m square L times E. So this term, this term, it is quite crucial to see oscillation. Okay, so there are some limits I have written here. So this has to be of the order of 1. Only then we can get oscillation as well as sensitivity to both the delta m square as well as theta. If it is less than 1, that will also not work. If it is very much greater than 1, that will also not work, because then we will not be able to observe the oscillation, because it will be oscillation will be averaged out. Okay. So in three flavor oscillation, we have three mixing angle, theta 1, 2, theta 1, 3, theta 2, 3, and one phase delta Cp. Okay. And two mass square difference delta m square 2, 1, delta m square 3, 1 or 3, 2. Okay, so this is the PMNS matrix. I have write it in 3 cross 3 matrices. So this part contributes to the atmospheric mixing angle, atmospheric neutrinos. This part comes from reactor and accelerator neutrinos, and this part comes from solar neutrinos. So if you take their products, you will get the proper mixing matrix. Okay, so this, now there are 3 mixing angle, as I said, theta 1, 2, that corresponds to this part, solar neutrino part, theta 1, 3, that correspond to the reactor and accelerator neutrinos, and theta 2, 3, that is corresponding to this part. Okay. Now, where do we stand? So what is the present status of this oscillation experiments? So as we know, theta 1, 3, it is measured solar, as I said a little earlier. So it is measured solar by solar experiment and reactor experiment. So it is properly measured, precisely measured. Theta 1, 3, it was reported precisely measured by reactor experiment and accelerators. Diabe, double shoe, Renault, these reactor experiments precisely measured. And this value comes around 8.6 degrees. So it is not so small. It is a quite important value and large value. Again, other delta m square 2, 1, it is also precisely measured. So what is not measured is delta Cp. Delta Cp. So we have very less information about delta Cp. We measured theta 2, 3, but there are still confusion about theta 2, 3, and that is called octant of theta 2, 3. So in which octane, so here, so in this, whether theta 2, 3 will be greater than pi by 4 or theta 2, 3 will be less than pi by 4. So that confusion is still there, and it leads to octane degeneracy. And whether theta 2, 3 is 45 degrees, that is also not clearly known, but we'll know these things. And then order of delta m squared 3, 1. So that is the mass hierarchy. So we'll be talking about that. So other part I am skipping. So here there are a few new possibilities which are exploring by the new experiment. We'll be exploring by the new experiment. So I'm not going to that. I'm trying to move fast. So this is the neutrino mass hierarchy. So on the left hand side we have the normal mass hierarchy.
Sir?
Yes, yes.
So this is gentle reminder for the time, sir.
Sorry?
This is a gentle reminder for the time, sir. So sorry to interrupt.
So how much time I have?
Like it is supposed to be 30 plus 5. You can have like 5 minutes, 5 to 6 minutes.
Okay.
And we'll have Q&A sessions. Yeah.
Okay. Sure.
Thank you so much.
Yeah. Okay. So on the left hand side, I have the this hierarchy. So normal hierarchy plot. Why normal? Because M1, M2, M3, they are in proper order. But here this is the inverted order, because M1, M2 is okay, but M3 is somewhere below than M1 and M2. So now we do not know which one is the correct one, which one will be the neutrino mass ordering. Presently, in the last 6-7 years, experimental data were suggesting that it will be the normal hierarchy, but there is a twist in the data. So that to that I'll come very soon. So this is about octane problem. So here you can see for a corresponding value of delta Cp, let's say it is 0 degree delta Cp. So we are having two values of theta 2, 3. Okay, so for a given set of values of neutrino oscillation parameters, let's say theta 1, 2, theta 1, 3, delta Cp, delta m square 2, 1, delta m square 3, 1, how can we have two values? Okay, so that is the problem with octane, because we cannot say whether this one is the true octane or this one is the true octane. And octane is divided by theta 2, 3 equal to 45 degrees. So whether theta 2, 3 is above 45 or below 45, that has to be confirmed by the experiment. Okay. Now these are the base fit values. So I'm skipping this plot because here you can see the present oscillation values theta 2, 3. It is on the higher octane, that is above 45 degrees. This is the base fit value, but you can still observe the 3 sigma allowed range. So the range is from 39 degrees to 52 degrees almost in the normal ordering case. So that means the whole range is allowed, and this is the base fit value. So it is not well defined that the range is in the higher octane or in the lower octane. Okay, so I'll come to this through the different results. So here I'm showing the present results from T2K and NOVA, because these are the two long baseline experiments which are taking data, and they are data for the last 5-6 years. It has been discussed that they were showing normal hierarchy, giving preference to normal hierarchy. But recently the trend has changed. So if you see these plots, so number of events that we are getting in T2K and NOVA. So here, the red one is normal ordering, and blue region is the inverted ordering. So here you can see only a small fraction of delta Cp is accommodating this 1 sigma range in T2K. But in NOVA, it's a huge range that is allowed. So I'll come to the next slide where you can view these things problem. So in inverted hierarchy, there is a consistency. Okay, there is a consistency in the NOVA and T2K result. So this is the NOVA plot and red one is the T2K plot. So there is a consistency in 2019, and the recent data says that we are getting much better base fit with more data, and it is consistent. But in the normal octane, so you can see there is an inconsistency. This is the NOVA result, which are at the base fit, this separation is increasing with more data. So this is quite interesting, and this tension is still there. Okay, so T2K and NOVA combination can best fit now the inverted hierarchy, and delta Cp value is 3 pi by 2. And these are the T2K and NOVA setup. So I'm just skipping this thing. And here I'll not discuss all about the plots, but this plot complement this result. So I just said that. And here, why I add this plot, here this red line is from some new experiment, not new experiment actually, it's a very interesting experiment, ice cube experiment. So these two. So you can see the parameter space is now decreasing in the data taken by 9.3 years by ice cube neutrino observatory. So ice cube is a very important experiment. That is set up in the Antarctica. I'm just skipping this slide. So let's talk about the Fusargen experiment. Fusar, Dune, Hyperchemiocande, Juno, SBN. SBN stands for Short Baseline Neutrino Program at Fermilab. So this is the Dune experiment. You might have heard of this. So 1300-kilometer baseline. So here you have the detector, and here you have the source at the Fermilab and Stanford Underground Research Laboratory. So it's an underground beam of neutrinos. So that underground, why it is underground? Because it gives the maximum exposure to neutrinos to interact with matter. Again, this is a short baseline program where source is here and you have multiple set of detectors set up. So this is a very close detector set up to unoscillated neutrinos, and there are different neutrinos detectors are set up at different distances. Juno is another experiment which has lots of possibilities, and Juno is the only reactor experiment which can contribute a lot to the neutrino mass hierarchy because of its long baseline and the construction site advantage. And hyperchemiocande. So hyperchemiocande is another powerful detector. So it has two detectors, one at the superchemiocande site I have already shown here. So in the near superchemiocande, so they will be setting up another big detector, and one long detector is planned in Korea. Okay, so this is some slide from ice cube. So I'm taking much time, sorry for that. So this is the detectors. This is a 1 cubic kilometer detector. Very interesting experiment it is, and it is contributing to neutrino physics, cosmology, and dark matter everywhere. And it is also why it is so important, because it is detecting astrophysical neutrinos coming from the extragalactics and high. So you can see they have already detected 80 neutrino events of TeV of energy. It is not the normal energy, which is 10,000 times higher than the normal atmospheric neutrinos energy. So I'm just going to the next slide here. This is the physics goal of this experiment. So new generation experiment will be able to precisely measure the unknown neutrino oscillation parameters. They are also trying to setting up for proton decay study, indirect searches for dark matter, to study supernova neutrinos, geoneutrinos, and ice cube. It is not a next generation, it is already running experiment. So they are detecting extragalactic neutrinos, and also the most important part is searching for new physics. So here I have kept some slides. So if someone interested, I can answer. But it is the dune CP violation reachability and mass hierarchy reachability, and this shows the fraction of CP violation and mass hierarchy reaching ability with time. In how many time they will be able to discover that. So this is all about it. Hyperchemical, they are also having use detector which can have high reach of statistics, so high number of events. So because of that, they can detect CP violation as mass hierarchy very easily in the very initial stage of their experiment. Still, I need to know, I'm leaving this slide and then I'm coming to my conclusion. So here is the conclusion side. So neutrinos are particles which have surprised us in the past, initially thought to be undetectable, and oscillation is discovered unexpectedly but have been seen in solar atmospheric sector by multiple experiments. So at present, neutrino oscillation in the precision era, as I said, the new generation experiment will do that precision measurement. T2K nova, they are taking data, so they will be giving some conclusive results on theta 23 of 10th and hierarchy and CP violation. So upcoming experiment will measure the precision. So with this few words, I'll stop my slides. Thank you. Thank you.
Thank
Okay,
you. Thank you.
Yeah.
Yeah. Thank you so much, sir, for your nice and informative presentation. So I just want to apologize because in between your talk, you have just asked anything to ask something to the organizer. So due to some technical difficulties, we couldn't respond to your question.
Yes,
So
but that is the
I
that's okay.
apologize for that.
Yes,
Yeah,
that's
yeah.
fine, because I was just looking for a time actually. Yeah.
Okay, fine. So thanks a lot for your time and accepting our invitation to deliver your talk. So it's time for open discussion. So if somebody want to ask any queries or questions, then you may.
I have a question. Am I audible?
Yes.
Yeah. So, so you talked about ice cube. I mean, the experiment. So, can ice cube confirm? I mean, in the future, the mass ordering. I mean, the normal ordering and inverse ordering. I mean, is it capable of doing that, or because it's at the astrophysical sources, extragalactic sources, so we don't exactly know. I mean, how much flux would be there, because there much. Because in the reactor, we basically more or less know.
No.
Flux. I mean, I don't know. Am I asking the relevant question or not?
No,
but is it capable of
Yeah, so
confirming?
as I have shown you one result from neutrino physics. So main goal of ice cube experiment is to detect extragalactic neutrinos or high energy neutrinos. But in addition to that, they are capable of doing the neutrino physics research also. As a result, I'm going back to my slide. So that what I was showing here. Let me show it here. So here you can see this is the theta 23 measurements, delta m square in this two-dimensional plane, and the data collected through a new technique that is called OSNext. So through that, they have seen that they have they were able to squeeze the space, the parameter space. They have reduced the parameter space compared to NOVA and T2K, from whom we were expecting much. Again, if you look at I could not show that. So this is the sterile neutrino exclusion plot. So here also they are contributing. So I am not an expert in ice cube. So ice cube, I am just I just keep track of that, but you can see the best bound, and it is almost excluded delta m square 1 electron volt with the best precision. You can see this is the exclusion limit drawn by the ice cube detector. So delta m square 41 of the order of 1 electron volt is almost excluded by it. So their data, yeah. So, and if you see the detector, ice cube detector here at the surface, so they are 1 cubic ton. So at the surface, they are having 1 kilometer square. So at the surface, they are having detectors. Here they are having the high energetic detectors to detect high energy particles. So at the surface, they can detect particle coming from cosmic rays also. So atmospheric neutrinos, yes, there is some possibility, but I cannot say that because I'm not an expert in ice cube or in this particular astrophysical studies. But yes, definitely they can contribute. Yes.
Okay, thanks. Yeah.
Yeah.
Any other questions from the audience? So I'm not from the background of high energy physics or particle physics, but out of curiosity, I just want to ask you a question, which may be a very naive question. So why the study of neutrino physics is important nowadays?
Okay, so the most important, I'll just give the answer in very short. So since neutrino oscillation have detected that neutrino oscillates, which says that neutrinos have mass, and neutrino in standard model, as we know that neutrinos are massless. That is one of the most important point, because massive neutrino, so to incorporate masses, we have to extend standard model. So why neutrino important? That is one of the major reason, because if you have to go, you have to look for new physics, then that is one hint that yes, you go, because you have to extend standard model. Okay, so one very basic answer I'm just giving on the basis of neutrino mass, because that was the first hint that we have to, standard model has to be extended, or we have to go for studying beyond standard model physics.
Okay.
And now that's why people are interested in new physics like neutrino decay, neutrino, sterile neutrinos, NSI, scalar NSIs, and all these things. So people are looking for new physics that can incorporate all these things.
Okay, thanks. So is there any other questions from the audience?
Okay.
Debajyoti sir, thank you for this very informative talk. I would like to know if there is any latest results on octane of theta to 3 from any of the experiments you have mentioned.
Yes, Nova and T2K. So they are measuring. They are taking data. So this result was actually from theta 2-3 measurements. But here you can see this is also the new fit. These were the results actually that came in the updated results from March 2024. Okay, so here at present I can see if I have that plot. Yes, you can see here theta 2-3. So at present, the data shows that the global fit shows that, so it is preferring higher octane. You can see the base fit is coming around somewhere 49 degrees. So if you convert this to theta 2-3, so it will be around 49 degrees. And delta CP, this is the base fit value for normal ordering. It is coming around 180, close to 180. This star mark is the base fit value. And theta 2-3 here you can go. So this is star mark, it is coming around this. So it is around 49 degrees. So this is the present
So higher
status.
octane is preferable now.
It is preferring right now the higher octane. Yeah.
Thank you.
Yes.
Any other questions? So if there is no questions, let us thank our speaker, Dr.
Okay.
Dutta sir. So thanks a lot, sir, for your time and the consideration. So
Thanks.
hopefully, yeah.
Yeah, thanks to you and to all the organizer for giving me this opportunity. So, and I would be sharing the session, but as I said, I talked with Vivek. So I had some personal issues for which I have to leave actually. So thank you once again, and I wish all the best and success of this conference. Thank you.
Okay, thanks a lot, sir.
Yeah.
So that's it from the plenary speaker. So let us move to the next session, which will be shared by Dr. Nayana Gautam from Assam Downtown University. Is an assistant professor in physics over there. So welcome you, Dr. Nayana Gautam. And I believe the schedule is with you right now, so you can proceed. Over to you. Madam, please unmute your microphone.
Good morning, everyone, and thank you so much, the organizer, for being here. So I welcome you all to today's first session of the ongoing conference, Physics Frontiers 2024. I'm very much excited and honored to share this interesting session. There will be 9 interesting presentations on different topics of high energy physics. So the speakers will be given 8 minutes for their presentation and 2 minutes for discussion. I request everyone to stick to their time. So let's start the session. Our first speaker is Debajyoti from IIT Bombay. His topic is probing the quark-gluon plasma via heavy quarks. I invite Debajyoti to start with your presentation.
So, okay, good morning to everyone. Am I audible?
Yes, you are.
Okay, so since I'm out of station, so the internet here is not that good. So I request, I wonder if it's okay to keep my video switched off.
Sure, no worries.
Okay. So, let me just try to share my slides. So, can you see my presentation?
Not yet.
Okay, just a moment.
Just share your entire screen, okay? Otherwise, the screen will be frozen. There's been an ongoing issue since yesterday.
Okay, I see. Okay, just a moment. Share my screen. So, what about now?
So
Currently I'm sharing my screen.
maybe you just make you the host. Okay, now it's there's a lag. Yeah.
Okay. So, are you able to see the presentation?
Yes.
Okay.
Let's make it in full screen.
Okay. So, so I'd like to thank the organizers to start off for allowing me to present my work here, and I'm going to be speaking about probing the quark-gluon plasma via heavy quarks. I've tried to keep the presentation a bit less technical, so that it's accessible to the majority of the students who I'm sure are attending this conference. So without any further ado, let me begin. So this is going to be the outline of my presentation. I'll begin with a brief description of the quark-gluon plasma, and then I'll proceed towards describing how we use heavy quarks as probes for quark-gluon plasma. So this is a schematic of a heavy ion collision. So how do we make quark-gluon plasma in the laboratory? Okay, so this is a schematic of that. So you see, if you see these two almond-shaped objects, these are actually heavy nuclei. So you can have lead, you can have gold, you can have gold lead. So there are many possible combinations which are used in high energy accelerators. So what happens is that these heavy nuclei are collided at ultra relativistic speeds, and after they collide, they deposit an enormous amount of energy density in the reaction zone. It's so high that the neutrons and protons literally melt, and quarks and gluons are released, and we have the creation of a medium which we call the quark-gluon plasma. So after the quark-gluon plasma is formed, its lifetime is very short. Eventually, it cools down, it expands, it cools down, and hadronizes, and it's the hadrons which ultimately reach the detector. And it's after reconstruction of the hadron tracks in the detector that we extract all the information about the medium. So my sphere of work is limited to this region of the evolution of heavy ion collision, that is the quark-gluon plasma. And so the two necessary conditions that one needs to claim that a quark-gluon plasma has formed is, number one, the quarks and gluons have to be the degrees of freedom. Okay, and the next is equilibrium has to be reached. So if hydrodynamics is able to reproduce the data, it simply means that the quark-gluon plasma that has been formed can be described as a liquid, as a fluid. Okay, so since it's a medium of quarks and gluons, they are strongly interacting particles. The underlying theory that describes that ought to describe the medium would be quantum chromodynamics. And if you see in the first figure, this is the graph between the strong coupling constant and the momentum transfer, during the interaction. So as the momentum transfer, the magnitude of the momentum transfer increases, the value of the coupling constant decreases, which suggests that at very high energies, one can undertake a perturbative treatment of the quark-gluon plasma, which makes life easier for theorists. So in the next figure, you see I've shown the QCD phase diagram. So the blue regions are the hadrons, okay, and the yellow region is the quark-gluon plasma. So in the yellow region, quarks and gluons are the degrees of freedom. And in the blue region, it's the hadrons. So the blue is the confined phase, and the yellow is the deconfined phase, and we will focus our attention on the deconfined phase. So that is the sphere of my work. So moving over to heavy quarks. So what are actually heavy quarks? You must have, this is for the students, you must have come across the quarks, charm, bottom, top. So these quarks are what we call the heavy quarks. For our purposes, we are interested mainly, with the charm and bottom quarks, because the top quark decays very fast. We don't have, it doesn't give us much information. So what happens is that heavy quarks have always been considered as very good probes of the quark-gluon plasma. Why? Because they're very heavy. So because of being very heavy, they don't equilibrate with the medium, right? So because they don't equilibrate, they carry important information to the detector. Okay? And so the formalism that we adopt is the Langevin formalism, where the effect of all the other constituents in the medium on the heavy quark is described by uncorrelated momentum kicks. So this is the Langevin equation of motion for the heavy quark momentum. So you see there are two parts to it. So one is a rapidly fluctuating force term, and the other is a slowly varying friction term. Okay, and the rapidly fluctuating force term is taken to be a white noise. So it's a delta function distribution, and the friction term is a drag coefficient. Here, kappa is that momentum diffusion coefficient, and the two are related to each other via what we call the fluctuation dissipation relation of Einstein. Now, my study actually is in the presence of magnetic field. So what happens in the presence of magnetic field is each of these two equations that you see becomes two equations. So one parallel to the direction of magnetic field, and the other perpendicular to the direction of magnetic field. And in my work, so what I do is I calculate these coefficients. As you can see in the last four equations, kappa parallel, kappa perpendicular, these are evaluated. So the central quantity is the Weldon's form, is a scattering rate, gamma. And the way we calculate it is we calculate it via the Weldon's formula. We calculate it from the imaginary part of the heavy quark self-energy. So skipping the details for a little bit. So if you see this diagram, so this is the diagram of a heavy quark self-energy with a resummed gluon propagator. So generally what you have is in the self-energy calculations is you have bare propagators, but in fact, at finite temperature, one encounters divergences, so perturbation theory breaks down. And for that, to remedy that, we need to use resummed propagators. So this is the propagator with blobs is what we call a resummed propagator. And this is the diagram for the heavy quark self-energy. It is this self-energy that we calculate. And so the sigma is the self-energy, and we take the imaginary part, and that gives us the gamma. Okay? And once you get gamma, you see in the last two equations, from gamma, you can calculate kappa, the momentum diffusion coefficient, as well as the energy loss via suitable integrations. So I just shown the final result here of gamma, the scattering rate, and from which we calculate kappa L, kappa T, and dEdx. So as I told you earlier, so there are the longitudinal and transverse momentum diffusion coefficients because of the presence of the magnetic field, and we also have the energy loss of the heavy quark. So as a heavy quark propagates to the medium, how much energy does it lose? So these are the quantities that I calculate. So let me take you through the results quickly. So the left panel is for for bottom quark. The right panel is for charm quark. And for comparison purposes, I've shown the B equal to 0 results. That means results in the absence of magnetic field in the bottom panel. Now, let's look at, so let's look at the first curve, for example, the first panel. So you look at the difference between the red and the blue curves. So there's a significant difference in magnitudes, right, between the longitudinal and transverse momentum diffusion coefficient, right? And same is the case with the right panel. But you compare it with the bottom panel, and you see that the curves are almost overlapping, right? So there's not much of a difference. So the conclusion is that in the presence of a magnetic field, we have a significant anisotropy in the momentum diffusion coefficient. Okay, so and these curves are for the condition when v is parallel to b. So v is the heavy quark velocity. So when the heavy quark velocity is parallel to the magnetic field, these results are corresponding to that. Okay, so we can also see what happens when the heavy quark velocity is perpendicular to the magnetic field. And well, it's the same thing. So if you look at the left panel, for example, the dotted lines are for charm, and the solid lines are for bottom. And traditionally, conventionally, for V perpendicular to B, we define three momentum diffusion coefficients: kappa x, kappa y, and kappa z. And so you see what happens is one of the curves here, the blue curve, is significantly above the remaining two, the red and the green, right? And so this is also because of this anisotropy in the momentum diffusion coefficients. So the key takeaway from both the scenarios is that the momentum transfer between the heavy quark and the medium happens preferentially along the direction of the heavy quark velocity. So that is a key takeaway. Now, so once we have done the study and once we have the results, the thing is, what are the limitations, okay, of the study? So one limitation that I'd like to talk about just a little bit is, let me go to the slide if I have them. Okay, so if you look at these results, these expressions, kappa L, kappa T, dEdx, although it's not visible here, I've not shown it. So these Q integrations actually have an upper limit. So these results are logarithmically UV divergent, and you need to put an upper cutoff by hand to make these results finite. So that's a drawback. You don't want to put anything by hand as a limit for your results to make sense. But the reason for this limitation is that we have only considered soft scatterings, in our work. We have neglected hard scatterings, and the reason for that is hard scatterings actually do not contribute as much as the soft scatterings do. And also it makes it nice. Yeah.
Sorry to interrupt, Debajyoti, you have
Sure.
1 minute left.
Sure. Thank you. I'm just finishing. So, so the reason for the limitation for this upper cutoff is that we neglect the hard contribution. And why do we neglect the hard contribution? Because, well, number one, it does not contribute as much, and number two, it makes our life simpler if we have to deal only with the soft contributions. And the next thing is that radiative processes are neglected. Here in this work, we have calculated, or we have considered only collisional collisional processes between the heavy quarks and the light quarks. We have neglected radiative processes like gluon-Bremsstrahlung. Okay, so these processes have been neglected, which might be important, for fast-moving charm quarks. So these are the two limitations of the study. And with this, I finish my presentation. So thank you.
Thank you for the informative talk. And now we have 1 minute per question. Is there any question? I would like to ask you one question.
Sure. Please.
Why do you consider only the heavy quarks to study physically?
Okay.
Can't we
So that's
use the
a
other quarks?
okay. So that's a very good question. So let me go back to this. Now the thing is, we are trying to probe, or we're trying to study the quark-gluon plasma. So what is basically the quark-gluon plasma? Uh, it's a medium composed of light quarks and gluons, right? So heavy quarks are not considered to be part of the medium. Okay, so the reason why they are not considered part of the medium is because they are actually formed very early in the collision, in the heavy ion collision process, even before the medium is formed. So heavy quarks actually are formed even before the medium is formed. And by medium, we mean the light quarks and gluons. So our quark-gluon plasma medium is a thermally equilibrated soup of light quarks and gluons. And we need something to study this medium. And since heavy quarks are produced before even the medium is produced, so they can be considered as external probes of the medium. And as I said, they do not equilibrate with the mediums. And because they do not equilibrate with the medium, they are able to carry important information about the medium to the detectors. So that is the reason why heavy quarks are considered, very good probes. Light quarks actually, they are part of the medium, so you cannot use light quarks to study to study the medium via an external source. So whatever is your probe, it has to be external to the medium and not part of the medium. So that is why heavy quarks are good probes.
Thank you. Our next speaker is Pritam Das from Bhawanipur College. His topic is Origin of Neutrino Masses and Inflation in a seesaw model with triplets. Over to you, Pritam.
Thank you. So can you hear my voice? Am I audible?
Yes, you're audible.
Okay. So I'm sharing my screen. Is it visible?
Yes, it's visible. Can you do it in full screen mode?
Okay.
Yes, perfect.
Okay, sorry. So I'd like to thank the organizer for giving me this opportunity to present my work here in this physics frontier. And I'd like to congratulate the organizer for organizing this successful conference. So I'm Pritam Das from Salbari College. I'm assistant professor there. So today I'll be presenting one of our work. The title is The Origin of Neutrino Mass Dark Matter Baryogenesis and Inflation in a seesaw Model with Triplets. So there are many, many topics that are covered in this work. So I will be just will be giving the outline of this work, and many of the topics are already discussed throughout this conference. Yesterday also some preliminary talks are there, and Debajyoti also explained the neutrino mass and all these things. So I'll be just very brief, and if you have any difficulty in understanding at some stage, then feel free to interrupt me in the middle of my talk. So this will be a short talk, and if you have any doubt, you can ask me. So is there any process to hide this bar? Sorry.
The bar is not visible here, so please proceed.
Okay,
It's
it
just
is
from on your end only.
Okay. So first it will be very easier for you to understand the scenario here. So what we are doing. So actually, we know the Big Bang explosion. So after the Big Bang explosion, so inflation happens. So inflation is after the big explosion, our universe expanded into a huge size from 1 to 10. It expanded up to 10 to the power 60 times of their current state. So it's a huge expansion, and during that expansion, many things happened. So those things are still not clear to us. So then this baryogenesis happened. So when the baryons are dominated over the anti-baryons, and I mean that's why we are seeing the meta-dominant era. And so as we know, dark matters are there in our universe. 26% of our the total composite of our universe are dark matter. So dark matter also frees out during, I mean, at the very early stage of the universe. That's why currently we can see the relic of the dark matter, whose value is 0.012 omega h square, which is 0.012. That's the best fit value. And then after that, this electric phase transition happened, the QCD phase transition happened, and then slowly when the universe is expanding and the temperature is decreasing, so those are the events of our universe that's really happened. So this QCD phase transition, neutrino decoupling, then electron positron annihilating. So you can see the time is, I mean, increasing and temperature is decreasing here. So as along with the redshift. So then those Big Bang nucleosynthesis happen, matter radiation equality recombination, and currently we are at the 13.6 billion years after the Big Bang explosion. So here in this work, we will try to address those three, primarily those three things: inflation, baryogenesis, and dark matter. And along with them, we will try to explain the origin of neutrino mass through a seesaw model. So to explain this work, so we have a new physics model where we introduce triplets, basically three ferment triplets and one additional scalar triplet along with the standard model Higgs doublet. So which allow us to explain neutrino mass and mixing, which are generated at one loop level. And then we address a viable dark matter candidate, and baryogenesis also we have addressed. And finally, the inflation and reheating temperature of the universe that we have explained here in our work. So the field content of our works, this is the standard model Higgs, this phi, and there are three triplets, ferment triplets, sigma 1 and sigma 2. And another one is sigma 3. So why I have written separately? Because this sigma 1 and sigma 2, they are G2. G2 is a discrete symmetry. So they are G2 even. And sigma 3 is G2 odd. And the another scalar triplet, which is also G2 odd. So that's why G2 odd, when we take a G2 odd candidate, that means it restricts its interaction with other particles which are already considered G2 even. So that's how we ensure that dark matter, if we consider any dark matter candidate, so that dark matter remains stable and it doesn't decay or annihilate to any other standard model particles. So here, this sigma 1 and sigma 2, this is the Lagrangian. You can see here sigma 1 and sigma 2 are interacted. I mean, this is the kinetic term of the Lagrangian, and these first two terms, those ensures the production of neutrino mass. And the third term here, you can see sigma 3 is interacting with delta and the scalar triplet. So this interaction, they will be giving us the dark matter candidate as well as the inflaton. So here the neutral component of this sigma 3, sigma 0, this will be a dark matter candidate in our study. So I'll be very brief to explain all these things due to time constraint. So for neutrino mass, those first two terms, they will be responsible for neutrino mass, and this will be our final neutrino mass matrix. And using the Casa-Shibara parametrization, which is a very well-known thing between among the neutrino phenomenologists who study with neutrino mass from the model perspective. So we have found a region where there are certain regions which are excluded by lepton flavor violation. So these are the regions which are excluded by lepton flavor violation. Other than that, there is a huge region where we can successfully able to address the neutrino mass and oscillation parameters. And after that, so I'll be saying few things about the dark matter. So here the last term of our Lagrangian. Earlier I have showed the Lagrangian. So in this interaction can be elaborately, expand like this. So here there are you can see, so there is a neutral component of this triplet. So this neutral component and this neutral component, and the one more thing I like to add that the dark matter particle, that should be a neutral one. It cannot be a charged one. So the neutral component, that both this sigma 0 and H, they both can be able to be a dark matter candidate. But this H, the neutral component of scalar triplet, those are they also can satisfy relic, but their masses are restricted by the direct detection constraint. That's why they fail to address as a dark matter candidate. However, the sigma 3 0, this neutral component of the fermion triplet, is able to address the current relic of our universe. And we can see with the help of co-annihilation and annihilation processes, so we able to find the parameter space, which these blue shaded regions, this blue region, those are the regions where we get the dark matter relic satisfied region at 3 sigma confidence level. So here we have shown the mass of the Higgs.
Sorry to interrupt, Chamdas. You have 1 minute.
Okay, sure. Thank you.
Thank you.
Okay. So another thing is the leptogenesis part. So here, the fermion a triplet that can decay or either decay or annihilate into the standard model particle as well as a Higgs boson. They can give rise to a lepton number asymmetry. So we have checked both the annihilation and decay processes, and here you can see this x-axis is Z, which is m by t. So here annihilation processes delayed, happen later to the decay process. That's why we get some lepton asymmetry, and which are, if we can see here, there's a slight deviation from this is the equilibrium number density of sigma, and here you can see this red dotted line. There's a slightly deviated from the equilibrium, and it produces sufficient lepton asymmetry, which then converted into the baryon asymmetry of our universe. And here this line, black horizontal line, shows the baryon asymmetry of our universe, of the current value, which is 8.75 into 10 to the minus 10. So here we get some satisfying region where the baryogenesis also can be satisfied. And along with that, we have also the inflation thing that we also explain. So here the neutral component of the scalar triplet behaves as an inflaton, and we get some parameter space, which are, these are the results from the experiments, the Lightbird and BK18, 1 sigma and 3 sigma confidence level. So here this in our case, where we consider this n. So here this value we get from 30 to 75. So till 60 to 70, those kind of regions are allowed from this inflation data. And the reheating also, we have explained that after inflation happened, the heavy inflaton, that H, the neutral component of the scalar, that decays or annihilate to the standard model gas boson as well as Higgs also. So we can successfully explain the reheating also. So these are the conclusion of our work. So we study a minimal model with 3 set of fermion triplet and a scalar triplet. Those are additional particle. So fermion triplets are there to help us to explain the neutrino mass, as well as the third one, the neutral component of the third scalar fermion triplet behaves as a dark matter candidate, and the neutral component of the scalar triplet behaves as a inflaton. And we have also explained the decay and annihilation, from the decay or annihilation of the fermion triplet, the baryogenesis via leptogenesis mechanism. Okay, thank you.
Thank you, Chamdas, for your wonderful talk. Now we can take one question. Does anyone have any question?
Yeah, so just quickly, can you describe in slide number 6 how you excluded, the mass and all? Not
So
very
here,
deep, yeah.
So mass and all means,
how
how
this
this
you
wide
even
region there. I mean, only these blue regions are there and not all the things are blue. So that's what you are asking.
Yeah. So how you got this? Yeah, blue region. Yeah.
So that's why we have written our model in Fain rule, and then we scan the throughout whole the region in micro omega. There is a free available software. I mean, this is a Linux-based software, micro omega. So here we have run the codes, and then we have give the constraint of the direct detection bounds as well as the dark matter relic, where the relics are satisfied in 3 sigma region, 0.117 to 0.123. I mean, I guess these are the correct bounds from the 3 sigma region. So there we get those regions where these relics are satisfied. So there are two plots are shown, where one in this case where this Yukawa 3i is 0, and in another case this Yukawa is non-zero. So here we get some when for non-zero Yukawas we get some more allowed parameter region.
Okay. Thanks. Yeah.
Those are the scan plots, I mean, from micro omega.
That. Yeah. You just scanned the parameter space and then looked
Yeah.
out where.
With the couplings and all the masses, so we just scan the parameter space. So if you like to discuss more, I can discuss later. We can discuss.
Yeah. Thank you. Yeah.
Okay.
Let's thank our speaker once again. Our next speaker is Pralay Chakrabarty from Guwahati University. He will be talking on 2 new variants of mixed muta symmetry. Pralay, over to you.
Thank you, ma'am. Am I audible?
Yes, you are audible.
Okay, I'm sharing the slide. So is my slide visible?
Yes, it is. Can do it in full screen mode. Yeah, it's good.
Okay, good morning, everyone. I would like to first thank the organizer for giving me the opportunity to present my work. Myself, Pralay Chakrabarty, and the title of my talk is 2 new variants of mixed mute of symmetry. I am working at Guwahati University under the supervision of Dr. Shubhankar. So here are my contents. So before going into the main work, let us give a brief introduction to the standard model and neutrinos. So the standard model is a theory that can explain the masses and interaction of the fundamental particles. It incorporates the masses to the particles through a mechanism called Higgs mechanism. And to construct the UQA term, we need both the left and right-handed fields. And since the right-handed neutrino field is absent in the standard model, hence the neutrinos remains massless. Now the neutrino flavor states are not equal to their mass eigenstates. Rather, they are the superposition of the mass eigenstate nu1, nu2, nu3 with definite masses. And this mixing is carried out by a 3x3 unitary matrix known as Ponte-Carbo, Maki, Nagakawa, and Sakata, in short, PMNS matrix. And like any other 3x3 unitary matrix, the PMNS matrix U is parameterized in terms of 3 mixing angles and 6 phases, where θ12 is known as the solar mixing angle, θ13 is the reactor mixing angle, and θ23 is the atmospheric neutrino mixing angle. And delta is the Dirac CP phase, alpha, beta are Majorana CP phase, and phi 1, phi 2, phi 3 are 3 unphysical phases. So this is the standard parametrization adopted by the particle data group. Now the neutrinos show a peculiar characteristics known as neutrino oscillation, where it converts to another flavor where it travels in space. And this oscillation is expressed in terms of the probability of conversion, which depends upon these parameters delta m21 square, which is the mass square difference, theta is the mixing angle, L is the distance between source and detector, and E is the energy of the average energy of the neutrinos. The neutrino oscillation suggests that the neutrino masses cannot be degenerate and non-zero. And to explain the neutrino mass, we need to go beyond standard model. We can understand the neutrino mass through the famous seesaw mechanism. And there are several types of seesaw mechanism, but in this work, I shall adhere to only type 1 and type 2. In the type 2 seesaw mechanism is a minimal extension of the standard model where we add the right-handed neutrinos. And in the type 2 seesaw mechanism, we add a heavy scalar triplet. But in this work, we shall be using the type 1 plus type 2 seesaw mechanism. So these are the experimental data for the studied parameters.
So before going into the main work, let us give a brief introduction to the mutosymmetry and mixed mutosymmetry. So the mutosymmetry is a correlation that can exist in the inside the neutrino mass matrix texture. So it tells us that the 1,2 element of the neutrino mass matrix equal to the 1,3 element, and 2,2 element is equal to the 3,3 element. And this mutosymmetry is very novel symmetry, as there are several mixing schemes can be derived from it. For example, the tri-bimaximal mixing, the bimaximal mixing, hexagonal mixing, golden ratios, etc. Now, the recent experiments have ruled out this mutosymmetry because its prediction of θ13 is 0. So, we slightly twist the relation of mutosymmetry in such a way that the 1,2 element is equal to the minus 1,3 element, and 2,2 element is equal to the 3,3 element star. So we name it as the mixed mutosymmetry from the motivation that we take the contribution from the muto entry symmetry, that is the 1,2 equal to minus of 1,3 and 2,2 element equal to the 3,3 star. This contribution is taken from the reflection symmetry, and the A, B, D, F are the complex parameters. So this work is published in Physics Letters B, and I was one of the co-author, and this work is led by Mr. Manas. So these are the prediction of the mixed mutosymmetry, which is consistent with the experimental data. So first we thought that the mixed mutosymmetry is a single texture. Rather, we realized that it may correspond to the family of textures. So we proposed to other variants of the mixed mutosymmetry. So here we have shown the mu1 and mu2 are the two variants of mixed mutosymmetric neutrino mass matrix textures. So let us give a brief introduction to the general and physical mass matrix. So a general mass matrix carries the information of 12 parameters, 3 mass eigenvalues, 3 mixing angles, and 6 phases. However, the physical mass matrix mu tilde tilde excludes the unphysical phases, and we can demarcate the mu tilde from mu as shown in this equation. But in the present work, we shall adhere to the general form of the mass matrix, which will carry the information of 12 parameters, including the unphysical phases. So the mu1 gives two complex constraints as shown in this equation, and the unphysical phases are like that. The first constraint gives two real equations where a1, b1 are the function of 11 parameters except θ13, and a2, b2 are the function of 11 parameters except θ23. And the second constraint gives two mass ratios where a3, b3, a4, b4 are function of 9 parameters except the mass eigenvalues. So these are the analytical expression for a1, b1, a2, b2, a3, b3, a4, and b4. Now mu2 gives two constants, the complex relations, and for this the unphysical phases are like that. Now the first constant gives two real equation in terms of the sin θ13 and tan θ23, where a5, b5 are the functions of 11 parameters except θ13, like the previous one, and a6, b6 are the function of 11 parameters except θ23. And the mass ratios are same as the mu1, since the second constant relations for both the texture is same. Now these are the analytical expressions for a5, b5, a6, and b6. Now the predictions of the mu1 texture is consistent with the experiment. It predicts two mixing angles θ23 and θ13 and two mass square differences m31 square and m21 square in the light of normal ordering. These are the input values for the first texture mu1. This is the prediction of the second texture where it predicts the same parameters θ1 to θ23 and two mass square differences, and it can be seen that these predictions are consistent with the experimental data. And these are the input parameters for the numerical analysis for the texture 2. Now there is a question that whether these textures can be realized from a symmetry or not. So to show that the type 1 we have shown that the
have 1 minute left.
Okay, miss. So the texture 1 can be realized from delta 27 symmetry and from this field content, and the texture 2 is can be realized from A4 Lagrangian from this field content. So to summarize, we propose two new variants of mixed mutosymmetry, and we study the phenomenological implications, and we see that both the textures are consistent with the experiment, and these textures can be derived from delta 27 and A4 group. So these are my references. So first, I would like to thank God for giving me this life, and I would like to thank DST Inspire for providing the financial support. I offer my sincere gratitude to my guide for constant support throughout the work. I would like to thank my lab mates for valuable discussion and suggestions. And lastly, I would like to thank my beloved parents for their silent efforts. This is the place where I work. Thank you.
Thank you for your informative talk. Now we can take one or two questions.
So Proloy, in your slide 33 or 34, so
Yeah.
go the previous one. Yeah, so how can you in this thing, so how can you just put theta 1, theta 2, theta 3? I mean, what are those? Phi
1. These are unphysical phases because we are dealing.
Phases?
Yeah.
What phases?
These are the unphysical phases.
Oh, unphysical.
Yeah.
So
we yes.
They are coming to the picture.
Actually, we are dealing with a mass matrix that contains the 12 parameters. We are not absorbing these unphysical phases. We are keeping them intact because so it may contribute towards the correlation. So these are the values for the unphysical phases.
And why phi 1 is not there?
Because these two correlations from the texture 2 is independent of phi 1. If you can see here, there is no dependence on the phi 1, only phi 2 and phi 3. That's why the phi 1 is, this texture is independent of phi 1.
Okay, thank you.
Okay.
Hello.
Yeah.
Okay, I have one question.
Yes.
If you observe this unphysical phases, phi 1, phi 2, phi 3, so what will be the difference in your result? Or can you do your calculations by observing these phases? Like, what is the importance of this phase?
Yeah, okay. So you can absorb these phases earlier from the by redefining the charge lepton fields. But as it can be seen from equation 7, if you put a constant on m nu, it will automatically include the unphysical phases. And if you put the constant over m nu tilde, it will be independent from this from 3 unphysical phases. We can try this to study this correlation by observing the unphysical phases. I think this result will be slightly different because there will be no involvement of these phases. And these unphysical phases will come in the picture only if the correlations holds true. Otherwise, this mathematics is independent of these unphysical phases.
Okay, that's all. Okay, thank you.
Thank you.
Is there any other question? If no, then let's thank our speaker once again. Our next speaker is Manas De from Guwahati University. Over to you, Manas.
Yes, thank you, ma'am. Is my screen visible?
Yeah, it's visible. Can you make it full screen?
Is it visible now?
Yeah, fine.
So hello everyone, I am Manas De, research scholar in the Department of Physics, Guwahati University, India. I am here to present a talk in the national conference, that is Physics Frontiers 2024, organized by the Department of Physics, Bhawanipur Anchalik College. And the title of my presentation is Neutrino Masses, Majorana Phases and M beta beta in an A4 symmetric seesaw model. So these are the contents of the presentation. So all these preliminary things are discussed by Debajyoti sir very nicely. So I would like to briefly go over these things. So we know that the standard model of particle physics is a well-established framework that explains the masses and interaction of the fundamental particles. And it is also predictive because it predicted the W and Z bosons and also the Higgs bosons well before the experiments. And despite the tremendous success of the standard model, there are many issues that the standard model cannot address. That is the origin of neutrino masses, the mass hierarchy of the neutrinos, the origin of neutrino mixing pattern, lepton flavor violation, matter-antimatter asymmetry, dark matter connections, and many more. So as the title is related to neutrino sector, so we shall discuss on the neutrinos. And we know that the neutrinos are an essential part of the standard model of particle physics, and they come in three flavors. So that is electron neutrino, muon neutrino, tau neutrino. And it is believed that the flavor states are an admixture of the three neutrino mass eigenstates, and the mixing between them is carried out by 3x3 unitary matrix known as the PMNS matrix. Now, the neutrinos are very peculiar, as we know that in 1957, Pontecorvo conceptualized the phenomenon of neutrino oscillation, which states that the neutrino may change their flavor as they travel in space. And in recent decades, the neutrino oscillation got experimentally verified by Super Kamiokande and Sudbury Neutrino Observatory. And for this, the 2015 Nobel Prize in Physics were awarded to Takaki Kajita and Arthur B. McDonald. So the probability of neutrino oscillation, that is the non-zero neutrino oscillation probability, demands that the neutrino masses cannot be degenerate or zero, which is a direct contradiction to the standard model prediction that the neutrinos are massless. This clearly shows that the standard model is incomplete and we need to go beyond the standard model. Now we used to discuss the structure of the PMNS matrix. This is the most general structure of the PMNS matrix, that is parameterized in terms of mixing angles and phases. So there are 9 parameters, out of which there are 3 mixing angles and 6 phases, and these are highlighted in this slide. In this connection, there is another important quantity known as the neutrino mass matrix, which is parameterized in terms of the mixing angles, in terms of the PMNS matrix, and m nu d, where m nu d is a diagonal neutrino mass matrix containing the neutrino mass eigenvalues. So therefore, a general m nu will contain 12 parameters. So in principle, if you can find some relationships among the neutrino mass matrix elements, so we can reduce the parameters and we can find some correlations between the parameters as well. So these are the data for the observables, that is the mixing angles, the Dirac-Sepi phase, and the mass square differences. And before we move to the model, we used to discuss some few important terms, that is the Dirac mass term and Dirac mass matrix. So Dirac mass term is generally written in terms of the left-handed, right-handed fields. And for the 3 flavor case, the Lagrangian is written in this way, where this is the Dirac neutrino mass matrix. Similarly, the Majorana mass term is written only in terms of left-handed or right-handed fields. So for the 3 flavor of neutrinos, the Majorana mass matrix is shown in this slide, where the mass matrix is complex symmetry. Now, to understand or to generate the small mass of neutrinos, we associate these mass matrices with some seesaw mechanisms. And in this connection, we used to highlight the type 1 plus type 2 seesaw mechanism, because in this work, we will be using the type 1 plus type 2 seesaw mechanism. The Lagrangian is written in this way, and the mass matrix in the middle is a 6x6 matrix. So once we block diagonalize this mass matrix, this is the effective light neutrino mass matrix coming from the seesaw mechanism. And this is the formula that we will be using. So now we come to the model. Basically, I've extended the standard model group with additional scalar fields in association with the A4 symmetry group. The charge assignments or the transformation properties of the scalar fields are shown in this slide. We also associate an additional symmetry Z10, which is like a cyclic symmetry. It will restrict some unfavorable terms in the equal Lagrangian Ly. Scalar fields obtain the respective Becker stars left on mass matrix ML. Dirac neutrino mass matrix MD, the right-hand neutrino mass matrix MR, and the type 2 mass matrix M2. And when we use these things to calculate the effective mass matrix on the type 1 plus type 2 seesaw, we arrive at the equation number 9, where we can see there's a shift from model to texture parameters, that is L, P, G, J, and H. And this shift has to be understood because we need to understand the information of the model parameters and texture parameters that we are using. So to understand this shift, we highlight these model parameter combinations in terms of these capital Ys. And again, these capital Ys are expressed in terms of texture parameters, so that it is like A goes to B and B goes to C, so that there is a linkage between A and C. That is, A is the model parameters, C are the texture parameters. So there is a linkage, so we can work it out, the information of the model parameters as well. Now, to understand the phenomenology associated with neutrino mass matrix, we diagonalize it with the PMNS matrix, and the parameterization that we have adopted is this one. This is the general PMNS matrix that contains the redox CP phase and only the mixing angles. Now, in this slide, we wish to highlight some existing mixing schemes in the literature that are ruled out by the experiments, such as bimaximal scheme, primary maximal scheme, hexagonal mixing schemes, where there are fixed entries for the mixing angles. So with this motivation, we posit approximately the best fit choices for the mixing angles and for the delta CP phase. Sorry, the delta CP phase is not the best fit value. We have taken 270° for the delta CP phase. So when you diagonalize the neutrino mass matrix, you see that there are 5 complex texture parameters in the model. However, these 5 complex texture parameters gets reduced to only 3 real parameters. That is real OP, imaginary OP, and real of G. These 3 real parameters spans the entire model and all the prediction associated with the model. So if you tune these 3 real parameters within some numerical values, so we arrive at the numerical values of these 3 real parameters as shown in this table, and for which we have predicted the 3 neutrino mass eigenvalues as shown in the table. And the sum of the 3 neutrino mass eigenvalues is consistent in the cosmological upper bound, and the model restricts the Majorana phases to vary between -45° and +45°. And we have also tested our model in the light of neutrinoless double beta decay experiment, where we calculate the effective Majorana neutrino mass m beta beta, which is given by this expression, that is UEI square. It generally represents the elements of the first row of the PMNS matrix multiplied by the neutrino mass eigenvalues. So we have calculated this part, and we have seen that the highest value of the upper bound that it can take is 28 milli-electron volt. So these are the model parameter combinations, and these informations are basically helpful because if we extend the model in calculating some other phenomenology such as lepton flavor violating decays or something like that, so we can use this model parameter informations to see how our model aligns with the experimental sensitivities. So these are the graphical representation of the analysis, that is between the 3 real parameters, and these are the plots between the mass eigenvalues and the sum of the 3 neutrino masses. This is the plot between alpha and beta, and this is the plot for m beta beta versus the lightest neutrino mass eigenvalue, that is m1. So as you can see that m beta beta lies in the sensitivity of the experimental ranges, and it falls in the sensitivity of the ongoing Legend 1000 experiment. So this is the plot for m beta beta versus m1. So I've also graphically visualized the model parameters as well. So these are the plots for the model parameters. So in summary, what we've done is that we've posited a neutrino mass matrix starting from the A4 symmetry in association with type 1 plus type 2 seesaw mechanism. The model is minimal because it on associating a fixed PMNS matrix, that is the best fit values, the model rules out the inverted hierarchy. Sorry, I forgot to mention this part. The model rules out the inverted hierarchy for the choices of the mixing angles. The model is consistent for the normal hierarchy of neutrino masses, and only 3 parameters can span the predictions of the model. The predictions that we predicted are the 3 neutrino mass eigenvalues and the Majorana phases, and also the m beta beta. So the model contains the numerical information, so we can study the other phenomenology such as BDK6. So these are the references. And I wish to thank CSR India for financially supporting my research work for JRF. And I wish to thank my supervisor for the guidance and support, and also my lab mates for the constructive discussions. Thank you. Hello.
Thank you. Thank you, Manas, for your informative talk. We can take 1 or 2 questions. So if there is no question, let's thank our speaker once again. Our next speaker is Sangeeta Dev from Cotton University.
Hello. Good morning. Am I audible?
Yes, you are audible.
Okay. Good morning, everyone. I'm Sangeeta Dev from Cotton University. Today I'm going to give a presentation on the study of the effective electron neutrino mass of the neutrino mass matrices with vanishing trace and non-vanishing minor. So this is the outline of my talk. Here is a brief introduction on neutrino, which is already given by Debajyoti sir very nicely. Neutrino physics was originated from beta decay when it was seen that the energy which was released by the electron was much smaller than the total energy which was released. So this is the beta decay spectrum which was observed. So in 1930, Pauli suggested that some of the energies have been taken away by a new particle called neutrino, which is spin half, massless, neutral, and weakly interacting. And in standard model, we get three types of neutrino: electron neutrino, muon neutrino, tau neutrino, which are massless. And in 1996, a superconducting experiment actually confirmed the neutrino oscillation, and which gave the concept of neutrino mass. So neutrino masses and mixing can be shown by 3x3 neutrino mass matrix, which is shown in equation 1, which can be written in the form of equation 2. Here V is equal to UP nu, where U is the PMNS matrix and P nu is the diagonal matrix with M1 and M1, M2, M3 are the neutrino mass eigenvalues. Here the PMNS matrix is shown in equation 3, and the diagonal elements of the P nu matrix are 1 e to the power I alpha, e to the power I beta plus delta. Here alpha, beta, and delta are the CP phases. So finally, we can see that MU is parameterized by a total of 9 parameters, out of which we only know the 3 mixing angles, theta 1 to theta 1, theta 2, 3, and the 2 mass square differences, while the Dirac CP phase delta is also known to some extent. So now we come to our model. We first construct the neutrino mass matrix as shown in equation 4. Here lambda 1 is equal to m1, lambda 2 m2 e to the power 2i alpha, and lambda 3 e to the power 2i beta plus delta. So as we consider the constraint condition of one vanishing minor in our neutrino mass matrix, so there are six types of cases of one vanishing minor. So CMN, which is shown in equation 5, is the one vanishing minor for the off-diagonal elements of the neutrino mass matrix, and CMM is the one vanishing minor condition for the diagonal elements of the neutrino mass matrix. Here M and N take their respective values. So finally, from this condition of vanishing minor, we calculate equation 8, where A1, A2, A3 is as shown in equation 9 here. So finally, the two conditions that we use in our neutrino mass matrix are shown in equation 10. This condition is for the vanishing minor, one vanishing minor, and equation 11 for the one vanishing trace. So now we define two parameters, x and y, that is x is equal to lambda 2 by lambda 1 and y is equal to lambda 3 by lambda 1. So we can write equation 10 and 11 in terms of x and y as shown in equation 12 and 13. So now solving equation 12 and 13, we get two values of x plus minus, and two values of y plus minus. So finally, we have four cases. That is, first two case, x plus y minus and x minus y plus. So for x plus y minus, we get the two values of alpha, that is alpha plus minus, and two values of beta, that is beta plus minus. And again, for the cases x plus y plus and x minus y minus, we get values of alpha and beta as shown in equation 18 and 19. So now we check the viability of the textures using R nu, that is the ratio of solar atmospheric mass square difference, which can be written in terms of rho and sigma, where rho is defined as the absolute mass of mass, that is m2 by m1, and sigma is equal to the absolute value of m3 by m1. So now we plot R nu versus delta and get a viable range of delta. And using that viable range, we calculate our Mariner phases alpha and beta. And finally, we study the effective electron neutrino mass ME using the formula which is shown in equation 22. So now this is the global fit that we use in our study. And finally, here we see that these are the 6 textures that we have. And out of this, only 5 textures are viable, out of which C23 texture, that is the condition, that is the one vanishing minor of M23 along with the vanishing trace is completely ruled out, while all the other textures are allowed. So for these variable textures, we get the values of delta, alpha, and beta, which is shown in table 3 and table 4. So finally, we calculate the effective electron neutrino mass for the case C11. So from here we see from the plot we see that the value of ME lies within 0 to 0.001 eV for the case x plus y minus, as this case is viable only for this case x plus y minus for normal hierarchy, and these are the plots for the case C12. That is the figure 2. It shows the plot for the case x plus y minus. This plot is for the pair x plus y minus, and this plot is for the case x minus y plus. So from here we see that ME lies within the allowed range. While figure 3, from this figure we see that ME lies within 0.001, which is the allowed range for ME. So finally, we summarize all the results of ME that we get for all the viable textures, and we see that ME lies within the allowed range for all the viable cases. So here are the references that we have used. Thank you. Hello.
Thank you, Sangeeta, for your nice talk. Now the session is open for questions. I would like to ask you one thing. How can you realize these textures you have mentioned here?
Okay, we can realize this texture using proof Z5. We can realize this textures only for the one vanishing minor, because vanishing trace condition does not say much about this texture. So using Zn group, we can realize this.
Is there any other question? If no, then let's thank our speaker once again. Our next speaker is Bhavna Yadav from IIT Jyoti.
Thank you so much.
Bhavna, your voice is a bit feeble. Can you increase the volume?
Hi. Now it's
Yes.
audible.
Yes, it's fine now. Please proceed.
Is my screen is visible?
Yes, it's visible. I'm doing full screen mode.
Yeah.
Can click on the next one, just next to it.
There is a bar, so I cannot click.
Okay.
Yeah.
Yeah.
So my name is Bhavna Yadav, and the topic of my today's presentation is NSI effect on tripartite entanglement measures. So this is the outline of my today's talk. I will start from neutrino oscillation, then I will discuss about non-standard interactions, that is subleading effect in neutrino oscillation, and then I will discuss about quantum correlation measures in case of neutrino and my results. So standard model is the most accepted theory in particle physics, which basically describe the interaction between fundamental particles in nature. But there are some limitations and there are some phenomena which cannot be explained by standard model, as these phenomena addressed by Manas. And yeah, that's why we need to go beyond standard model. And neutrino is a candidate, a good candidate, which can go beyond standard model and which can probe new physics. So basically, these are the sources of neutrino, in which reactor and accelerator experiments are the man-made sources of neutrino. And there is a very important phenomena in case of neutrino, that is neutrino oscillation. So neutrino oscillation is a phenomena where one neutrino created with a flavor, specific lepton flavor, and after traveling some distance, we can measure another flavor. So this is possible if neutrinos carry mass. Basically, these are the mass eigenstate of neutrino, and here nu1 and nu2 are these are the flavor eigenstates of neutrino, and nu1 and nu2 are the mass eigenstates, and theta is mixing angle here. So neutrino oscillation is the main effect, and it is confirmed by many experiments, but it is possible that there may be some subleading effects, and non-standard interaction is one of them. So non-standard interaction in neutrino oscillation refer to the interactions with some new or unknown particle that is beyond standard model. And these interactions can affect neutrino oscillation probabilities and the behavior of neutrinos. So these are the Lagrangian of non-standard interaction, this one for charge current interaction, and this one for neutral current interaction. And we can understand the difference between standard interaction and non-standard interaction via this diagram. Here, in standard interaction at one vertex, lepton flavor is conserved because here electron, neutrino, and electron. But in case of non-standard interaction at one vertex, one flavor is alpha, but another is beta. So here lepton flavor violet. And we can see similar thing in Lagrangian at one vertex alpha, one particle is alpha flavor and other particle is beta flavor. So if any neutrino traveling through Earth, then we can write Hamiltonian in this form. This is Hamiltonian for vacuum, and this one is Hamiltonian for matter. And here A is matter potential of Earth if neutrino is traveling through Earth. Then, but if we want to add the contribution of NSI, then we can add contribution in matter Hamiltonian, and we can simply add, and here these epsilons are NSI parameters. So basically this is for two flavor neutrino oscillation. Now mode entanglement is another concept in which this is a different representation. So we can write any state in term of mode entanglement. In case of neutrino, there are flavor eigenstates which we can write in terms of mass eigenstates, and we can also write these favor eigenstate in terms of mode entanglement. Like if nu alpha flavor, then in alpha it is 1 and in beta it is 0, and similarly we can write nu beta. So using that mode entanglement concept, we can write time evolution of that state, and the density matrix corresponding to this state can be written like this. And using this density matrix, we can study various quantum correlation measures. And using this mode entanglement concept, we can study these quantum correlations in neutrino sector. So what are the quantum correlations? So basically quantum correlations define the correlation between any quantum system, and the measures of quantum correlation quantify the degree of correlation. There are many quantum correlation measures like many quantum correlation concepts like coherence, entanglement, known locality. Entanglement is a very basic feature, and in entanglement, if there are two or more subsystem, more particle, and they become correlated, it means a state of one particle cannot describe independently. If we want to explain the state of these particles, so they are correlated. We cannot define it independently. So this is entanglement is basic idea, and there are numerous ways to quantify the entanglement. Some of them are entanglement of formation, concurrence, and negativity. So entanglement of formation was very basic measure of entanglement, which was defined. And if entanglement of formation is 0, it means that state is separable. It means it captures underlying entanglement completely, and this is the basic measure which defined in terms of entropy. And we can also write these measures in terms of neutrino oscillation probability. After that, concurrence was introduced, which was simpler form of EOF. And yeah, it can be defined in terms of reduced density matrix. And after that, a new measure was introduced to fill the gap of pure state measures and mixed state measures. So that's why negativity was introduced. And in this work, we study the effect of NSI on these different entanglement measures in case of different experiments. So in this figure, we did analysis of different entanglement measures for different reactor experiments. So first one for Diabe, second for Juno, and third for Camlin. Here this orange curve for negativity measures, this magenta for concurrence, and this cyan for UF, entanglement of formation. So the NSI, in case of reactor experiment, we cannot discriminate, between NSI effect and standard matter effect. So this effect is very less, but we can see from this figure in upper left panel that negativity is a weaker measure of entanglement as compared to other two, because it captures less entanglement. Then in this figure, in left panel, in upper panel, we are showing our results for T2K experiment, and in lower panel, it's for Minos experiment. So these are accelerator experiment, and here we can see that effect of NSI is visible. Here this solid line for NSI effect and this dashed line for standard matter oscillation effect. And here again we can see that negativity is weaker measure, and for higher energy concurrence is a stronger measure, but still the impact of NSI on negativity is more as compared to concurrence, which we can see from this right panel diagram. And these are the results for Dune experiment. Dune can easily discriminate between standard oscillation scenario and NSI scenario in some energy regions. And yeah, effect of NSI again more pronounced in negativity as compared to concurrence. So in summary, I can say that we studied the impact of NSI on different entanglement measures in 3-flavor neutrino oscillations for different experimental setups. And Dune with longest baseline exhibit more pronounced deviation towards NSI. And yeah, reactor experiments showing lower sensitivity towards NSI. And yeah, negativity exhibit higher sensitivity than concurrence towards NSI. Thank you so much.
Thank you, Bhavna, for your nice talk. Now you can ask questions. We have 2 minutes for questions. I would like to ask one thing. The NSI you have mentioned or you have done work is in the talk is scalar NSI or vector NSI?
Yeah, ma'am, it's vector NSI. That's why we are adding it's in Hamiltonian, with Hamiltonian. Yeah, it's vector.
Any other question?
Yeah. Basically, it's vector NSI. We are adding this in with matter effect, so it's vector NSI.
Thank you, Bhavna.
Thank you, ma'am.
Yeah, I have a question.
Yeah.
So slide number 18. Yeah, in the top panel, the first 2 panels, why you have less number of wiggles as compared to the middle and the last one? What is the cause? The energy is roughly the same. So is the length that is, is the effect of the length or what? In the middle panel and the last panel, you see more wiggles as compared to the first, the first panel.
First one, yeah. Yeah, basically this is because of baseline. Baseline is different for different experiments.
Okay, yeah. So it's the length effect.
Yeah.
Okay. Thanks.
Is there any other question? If no, then let's thank our speaker once again. Our next speaker is Pankaj Bara from IIT Delhi. Pankaj, over to you.
Okay. Is my screen visible to you?
Yes, it is. Can do it in full screen mode and please proceed.
Yes. Okay. So hello, good morning to everyone. So I am Pankaj, and I'll be speaking about this complementarity of beyond the standard model physics at the gravitational wave and dark matter detectors. First of all, I thank the organizers for this wonderful workshop and conference. And my slides are a little bit technical, but I have tried my best to avoid the mathematical jargons. So let's start. So when I say gravitational waves, as we all know, that gravitational waves were detected in 2016, and for that, Nobel Prize were also given the next year. And it was detected after 100 years of theoretical formulation. And this gravitational wave can come from two different time scales of the universe, evolution of the universe. It can come from the late time, where it is primarily come from the binaries. It can come from the early universe, which forms the stochastic background of the gravitational waves. And it is due to the particle interactions and plasma radiation and other mechanisms. And the early universe gravitational waves can be produced from different mechanisms, such as it can come from inflation, preheating, faster surface emission, and different cosmological defects, such as cosmic strain, domain-wide decay, etc. However, I am primarily interested in gravitational wave from faster surface transition because it connects with a mechanism called electronic baryogenesis, which attempts to explain why there is more matter in the universe than antimatter, and popularly known as baryon asymmetry or matter-antimatter asymmetry problem. And the gravitational waves from the first order phase transitions appears due to the principle of bubble formation, bubble propagation, and bubble nucleation. When the bubble propagates in the thermal plasma, it can collide, and then it can leave some shock waves or sound waves in the plasma, and there may be some turbulence in the medium due to magnetohydrodynamics. And together, all of them can contribute to the total gravitational wave energy budget, and it can be written as shown in a box. And loosely speaking, this amplitude of individual gravitational wave sources is scaled as the inverse duration of the phase transition, and hence connecting this gravitational wave and phase transition in a loose way. So coming to the beyond the standard model physics part, so there's a model called Assam with inner triplet, where the standard model particle content is extended with a triplet Higgs scalar, which is triplet under SE2 representation with hypercharge y equal to 0. And after imposing a discrete symmetry, say Z2, this neutral component can be a dark matter candidate. And the key findings in the existing literature says that these masses of the triplet has to be around 2 TeV to evade the direct direction constraints and also satisfy the thermal relic. However, if one also wants to have a faster order phase transitions in this setup, then it gives a tight constraint on the quartic coupling, lambda HT, and it gives an upper bound on the mass of the triplet, which comes around 250 CV. So you can see that these two pictures, the dark matter phase transition, are not in the same phase. So there are tensions in the these two observables. So if you ask a question, how can we elevate this kind of problems in such BSM scenario? So what we did, we extended minimally with a real scalar singlet and a fermion, Dirac fermion, both are singlet under SE2 representations. And our motivation is to understand the dark matter and electric phase transitions in the desert region, which is the region where the triplet dark matter is ruled out, which is below 2 TeV. And in that region, we also want to study the phase transition, whether now they can be in the same page or not. And then we want to further investigate the gravitational wave that can arise from this faster phase transition, and we can complement this so that we can complement these dark matter sources with the gravitational wave detections. So in this model, instead of one dark matter, we have imposed two different discrete symmetries. Therefore, we have two dark matter candidates. So it consists a multi-component dark matter scenario. And this is the particle interactions. This is the potential terms and Lagrangian 11 for our model extension. And in our setup, we have give wave to the singlet Vs. Due to this, it actually mixes with the SM Higgs doublet H. And due to that, we have a mixing angle, and one can have model independent parameters that is written in the red box. So once we have this model, we need to also consider the different constraints that this type of model can suffer. So the constraints can come from the theoretical point of view. It can come from the experimental ground. It can also come from the phase transition analysis, since we are also interested in this kind of analysis in our model. And we have used some publicly available codes for this implementation of these different constraints, and also use our personal codes to analyze the constraints and the data. So one way to study this parameter dependence is to first have a rough idea of the parameters that is involved in our model. So one of the important parameter in the model is the equal coupling GS. And you can see that when GS is very, very small, it actually leads to the overabundant region, except for the Higgs resonance case. And for GS very high, it leads to underabundant case, except for the Higgs resonance. However, when GS is of the order of 1, one can have relic density at multiple M psi points. So this gives an idea that what should be the GS parameter, what should be the range of the GS parameter. And one of the important feature of multi-component dark matter is that under a certain allowed mass range, this dark matter conversion channels is open. But in our case, this channel is more dominant for GS when it's very, very small. And that's for it's not very favorable, because for GS very, very small, it actually leads to overabundant. And after studying different parameters dependence, one can go for a general scan. And one of the motivation of our is to understand the physics in the desert region. Hence, we have kept the mass of the triplet around from 300 GeV to 1 TeV, where the lower bound comes from purely from the colloidal sources. And similarly, from different ranges are motivated from different observables and understanding of the parameters that I have already discussed. So what we have found is that in this setup, for a large range of M psi, relic density is satisfied. And not only that, direct detection can also be satisfied for different experiments like Xenon 1T, LZ, or Darwin. So therefore, we have obtained that this kind of setup will allow to have more parameter regions where direct detection and relic density will be fulfilled. And not only that, as we have started with our objective to revive the desert region of the triplet dark matter, which we successfully did. For example, in this plot, you can see for the whole range of this triplet dark matter, one can have total relic density and dark matter detection that is satisfying the current constraints. And it only gives bounds on the M side, which is the mass of the second dark matter candidate, and also gives a constraint on the Yukawa coupling. And one can see the parameter region, allowed parameter regions from this plot. Once we have identified the parameter regions or parameter space where the dark matter relic density and direct detection constraints are relaxed, one can now try to understand whether one can have strong faster phase transition and hence gravitational wave in this region or not. For the phase transition dynamics, one needs to identify the dynamical fields which will evolve with temperature. And we have identified these fields are the SM Higgs, the singlet Higgs, and the triplet. And these dynamical fields are mostly scalars and not fermions. And we write down the tree-level potential as shown here, which will evolve with temperature. And when we study phase transition, when we include temperature, one also has to include the thermal corrections that can come from the loop level. And also one needs to include zero temperature loop correction. This is called Kolbe-Nondo potential. And I want to mention here is that because of the particular setup, particular symmetry imposed in our model, we are allowed to write these three terms. And these terms are very crucial in order to give a barrier during the transition. And barrier formation is one of the very first criteria to have a fast phase transition. And one can in fact quantify how much contribution is coming from the tree level or loop level contribution to the potential. And we find that dominantly the contribution is coming from the tree level and also from the thermal one loop corrections. While for the one loop thermal T equal to 0 correction, this contribution is very small, and one can see it's in the negative plane. So it is actually lowering the barrier, but the contribution dominantly coming from the tree level and one loop. So in most of the cases, we will have a faster phase transition, which is characterized by these two equations. And once we have figured out the criteria of the faster phase transition, we investigated the parameter space, and we have found that in the region where the dark matter detection and relic density is satisfied, most of the parameter regions actually satisfies this SFVT criteria also. And in fact, this SFVT is now mostly abundant for the masses below 1 TeV. And after that, what one can do, that once we have this particle physics model, one can actually calculate the parameters that is relevant for the phase transition dynamics, and then one can feed these parameters to the gravitational wave calculation simulated results. So these are the important parameters, where alpha is the latent heat released during the transition, beta by H actually tells you the inverse duration of the transition, and you can see it as a T star term. So T star actually tells you the transition temperature at which this transition has happened. So one more parameter in this analysis is important is the VW, which is the bubble weld velocity. So in a very conservative way, one actually takes this VW to be 1, which is the speed of light. But for a more detailed analysis, one can actually try to look the underlying hydrodynamics and solve this VW from the scratch. So it is customary to check the correlations between different phase transition parameters and gravitational wave parameters, whether they are on the same page or whether the predictions is true from the theoretical point of view. So this is a typical pattern of the inverse duration of the transition with the alpha, the latent heat release. And for this region where the latent heat release is more high, the beta by H is very small, which is very desirable to have a strong gravitational wave. And similarly for other parameters, one can also see different correlations. Now coming to the gravitational wave detectability. So the conventional strategy is that once you identify the first phase transition regions, you calculate the peak frequency and peak sensitivity, and what you do, you calculate something called sound to noise ratio. And this is to be calculated for different detectors. So we have detectors like LISA, BBO, and DESIGO, and one have to calculate all these SNR parameters for different points. And once you do that, we have find that in the peak frequency and peak amplitude region, most of the parameter regions, parameter points falls under the proposed future space-based detectors such as LISA, BBO, DESIGO, U-DESIGO correlation, and ultimate DESIGO, etc. And similarly, one can also project these data points into these different curves to see how much points are allowed.
Pankaj,
and
sorry
yes,
to interrupt. Pankaj, you have only 1 minute left.
yeah, sure. I have to finish. And what I was trying to tell that one can project these data points on the experimental curves, and one can see that most of the points that satisfies this threshold value of the different detectors from LISA, DESIGO, or BBO, and it also satisfies these direct detection and Rayleigh constraints. So another approach to understand this detectability is to consider peak integrated sensitivity curves, because the earlier curves called the power law integrated curves carries some caveats, such as it doesn't carry the core inherent information of the SNR, where the SNR has to be calculated separately. And the peak frequency and peak amplitude calculation actually violated something called the power law of the gravitational wave signal. So one can calculate these peak integrated sensitivity curves, and one can think of these curves as an analogy to direct detection limits. And if you remember, in the direct detection limits, any points falls below the limits are allowed and above the limit is excluded. And here it is the other way around. Any points falls above the curve is allowed and under the curve is excluded. And here, as an example, I have plotted these PISC curves for LISA detectors in mind, but you can extend this calculation for the other two detectors also. However, it is not necessarily, because inherently this kind of curves tells you that any points that above the curve is allowed. So one can have a pretty much good idea how many points will be allowed and can be detectable in our case. And this is my conclusion. So we have successfully revived the desert region for the inner triplet dark matter case by simply extending with a Dirac fermion and a singlet scalar. And also we have implemented this phase transition analysis, and we have found that this dark matter and phase transition can lie on the same plane, on the same state. And we further investigated the gravitational waves, and we have implemented a new approach called peak integrated sensitivity curves to identify the detectability of this gravitational wave. And it can be detected at LISA, BB, or DESIGO, and hence our study complements the conventional dark matter searches and BSM searches at the gravitational wave frontiers. Thank you.
Thank you, Pankaj, for your interesting talk. We can take maximum one question as we are out of time. Is there any question?
Yeah, can you just go 2 slides back? Yeah, so, yeah, this and this. So,
Yeah.
I mean, in the last panel, you have a kind of uncertainty. I mean,
Oh,
is it-
yes, yes, yes. Yeah,
But-
this actually, I didn't mention it because of the time constraint. The thing is that this PIS curve, so this is called a peak integrated curve, actually takes care of different correlations of the sources of the gravitational wave production. If you remember, earlier I mentioned that gravitational wave from phase transition can come from 3 different sources: bubble collision, sound waves, and turbulence. But this kind of curves can also take care of different correlations. So if you see, there are correlation of sound wave and turbulence, and bubble collision and turbulence. So the uncertainty is appearing because you are correlating 2 different sources with 1 plot. So that's why this uncertainty.
Oh, okay.
Yeah.
Okay. Yeah. Thanks. Yeah.
Okay.
So we thank our speaker once again. Our next speaker is Rishi Bora from Tezpur University.
I don't see Rishi Bora's name in the participant list. So, Rishi Bora. Yeah, I don't think he is here. Okay, so Chairman, so can we go to the next speaker?
Yes, of course.
Yeah,
Our
please.
next speaker is Saurabh Sutia from Aizer Mohali. Saurabh, are you there?
Yes.
Okay. Please start your presentation.
Can you see my screen?
Yes, your screen is visible. Then full screen mode. And
Yes. Okay. Hello, I'm Saurabh from Aizer Mohali, and first of all, I would like to thank the organizers for giving me this opportunity. The topic of my today's presentation is a study of radiative decays of the exotic X3872 using the Bell and Bell 2 experiments. So as everyone did, I will start from the standard model. So we have 4 basic fundamental forces. So the quarks are bound by strong interaction inside protons and neutrons are bound by nuclear force, and the nucleus and the electrons are bound by electromagnetic force, and similarly those forms our material in the universe. So mesons are formed with 1 quark and an antiquark, and baryons are formed with 3 quarks. But particles can be composed of more than 3 quarks or 1 quark and antiquark. These particles are called exotic particles, and this was also mentioned by Gell-Mann in his first paper. So this particle X3872, which I'm working on, was the first state of this kind, which was discovered by Bell collaboration in this decay mode in 2003. So since then, it has been studied by many theorists as well as many experiments, and they measured the mass to be around 3871 MeV, and width to be around 1.19 MeV, and ZPC to be around 1 plus. So these are some of the models that is put forward to explain the structure of this particle, like molecular structure, tetraquark, or harmonium state. But without experimental proof, nobody believes theories. So that's why people made LSC here with CMS or Atlas LSCB, etc. And in Japan, we have Super KKB with Bell 2 detector, which I will explain in a bit. So how will we know about the structure of the particle? So there is a parameter called R psi gamma, which is the ratio branching fraction of X going to psi to S gamma divided by X going to Z psi gamma. So if this parameter is of the order of 10 to the minus 3, then we can say that this is a Debajyoti structure molecule. And if it is in the 0.5 to 5, then it can be a molecule plus some harmonium mixture. And if it is in the range of 1.2 to 15, then it is a pure harmonic. So this parameter has been measured by many different experiments. Like Baruah measured this parameter in 2009. Similarly, we see from the table that Baruah LSCB 14 result and LSCB 24 result, they saw both of the modes here, like X going to Z psi gamma and X going to psi prime gamma. But Bell and Bestry did not see these modes in their results. So they only gave an upper limit to the parameter R psi gamma. So that's why our motive is to measure the branching fraction of X going to Z psi gamma and X going to psi prime gamma, and measure this ratio to find out the internal structure of the particle. So to do high energy physics experiment, we need high energetic particle beams to be collided, that has to be collided. So the decay vortex of the particles that are produced should be found out, and they should be tracked and identified. And the data has to be stored and analyzed for physics results. So at Super KKB asymmetric collider in Tsukuba, Japan, electron and positron beams are collided with center mass energy of 10.5 GeV in the epsilon 4s resonance. And these particles produced in the collisions are detected using Bell tube detector. So this is a schematic diagram of Super KKB oscillator and the Bell tube detector. These are the different sub-detectors for different purpose, like vortex reconstruction, tracking, particle identification, and K-long muon detection. So we are going to follow the process of blind analysis, which is usually followed in experimental high energy physics. So in blind analysis, the technique is that we to prevent bias in the data analysis, we first of all carry out our study in Monte Carlo, and only finalizing our study in Monte Carlo, then we will go to the data. So as a first step, we generated 0.5 million signal events using EVT-Gen. The detector effects are simulated for the Bell MC we using Xian3, and for Bell 2 using Xian4. And for analyzing the data, we use Bell 2 analysis software framework. So this is a schematic diagram of what is happening in our mode. First of all, electron and positons are collided to form epsilon 4s. Then the epsilon 4s decays to BB bar pair. One of the B decays to X and K, that is our signal mode. Then the X can go to Z psi gamma or psi 2s gamma. So next, coming to the like our study. So these are the fittings of our signal MC. For fitting, we used we are going to follow to the unbin maximum likelihood of fit of MBC and Z psi gamma. MBC is called the beam constraint mass, and Z psi gamma is the mass, reconstructed mass of the particle, XJ72. So for fitting MBC, we use Gaussian plus bifurcated Gaussian function here. And for fitting Z psi gamma, we use T probability distribution function, which are Gaussian, bifurcated Gaussian plus logarithmic Gaussian. So to fit the smooth background, we use Chebyshев polynomial in both of the cases here. So these are the upper row is the plot for Bell MC, and lower plots are for Bell 2. So next, coming to the background study. The background study is carried out using B2 Z psi X inclusive sample of 110 Bell data. So in case of B2 X going to Z psi gamma, we do not see any peaking structure in our signal region, which is around here. We expect our signal to be in this region, but we don't see any peaks here. So we are safe in this case. So we will directly follow to the fitting part. But in case of X going to psi prime gamma, like or psi 2s gamma, we see some peaking structures around our signal region here. So this peaking structure mainly comes from B going to psi 2s k star. And currently we are working on to remove this background as much as possible. So finally, coming to the conclusion, MC study of signal and background with optimized selection criteria of X going to Z psi gamma has been presented in this presentation. Next, what we plan to do is we are going to follow multivariate analysis for suppression of the peaking background B to sideways cluster in case of X going to sideways gamma. Then after optimization of the selection cut on MVA, fitting will be performed on the signal and the background. Then we will perform systematic uncertainty and publish the result in that chart. So let us see.
Thank you, Saurabh, for your informative talk. Now we can ask our own questions. Sir, I would like to ask one question. This is very basic question. I have not gone through this Delhi experiment. What does it do actually? What is the aim of this experiment?
Okay, I will. So here in this slide, you can see in Bell we collide electron and positron. Electron beam is of around 7 GeV, positron beam is of 4 GeV. Then it produces epsilon forest resonance, which immediately decays to B plus B minus meson or B0 B0 bar meson. So mainly the aim is to study the decays of the like B meson here. That is the main aim, but we can study tau physics also, or yes, that's the main motivation.
Okay. What does this X3872 signify?
So as I explained, the mesons are composed of a quark and an antiquark, and baryons are composed of three quarks. But there are some particles which do not follow this convention. Like there can be 4 quarks, or there can be a molecular state like this, or there can be like pentaquark, glue balls. So this X3872 was the first state of this kind, which is called exotic particles. Like this is not a conventional meson or a baryon.
Okay, what does this number signify? Actually, this was my question. 3872.
This is the mass of the particle.
Okay. Okay, thank you. Is there any other question? If no, then let's thank our speaker once again. Saurabh was the last speaker of this session.
So thanks a lot all the participants for their talk. And also I would like to thank Dr. Nayana Gautam for her time and being with us today for this session. So thank you, Dr. Gautam.
Thank you. The session was really very informative for all of us. I congratulate the organizers for arranging such a wonderful conference. Over to you.
Thank you. Thanks a lot. So this session is over, and we are going to start the next session number 2. So it's over to you, Dr. Thapa.
Hello. Thank you, Dr. Gautam. It was a very nice session, actually. So next session will be chaired by Dr. Sumitra Bhattarai from Bhawanipur Anchalik College. He's a head of the Department of Chemistry. Yeah. So let me give a brief introduction. So she did her, so Dr. Bhattarai did her PhD from NEHU in density functional theory. So she will be chairing the sessions, multidisciplinary sessions, basically, on instrumentation communication technology, interdisciplinary, as well as nanoscience, and 2 talks from condensed fluids. So there's a small announcement that 2 talks, 2 presentations from the first day of the program are rescheduled to today of Dr. Debajyoti and Femina Brahma. So I request Jyoti Oja and Femina Burma to be ready by the end of. So you will be both of you will be presenting after the last talk of the session, or last presentation of the session, that is after Jumuna Mazumdar. Okay, at around 1:10 and 1 p.m. Okay, so okay, so it's over to you, Dr. Bhattarai. Please chair the session.
Good morning, everyone. Thank you, Dr. Thapa, for the introduction, for the nice introduction. And I would like to welcome each and every speaker to the second session of the 3-day National Conference, Physics Frontier 2024, Bridging Theories and Experiments. So I would like to give a brief introduction about this session. These sessions will be, as our Dr. Thapa already said, this session will be basically on instrumentation and communication technology. And the second one will be interdisciplinary sciences, as well as the last one will be the nanoscience and technology. So our first speaker for the session is Debajyoti Das. Debajyoti Das from Tezpur University, and the topic of his presentation is a flexible metastructure absorber using graphite silicon rubber composite sub-wavelength resonator for Ka-band applications. So may I request Debajyoti Das to kindly take your time and share your slide. So we have 8 minutes for presentation and 2 minutes for Q&A session.
Thank you, ma'am. So am I audible?
Yes, you are audible.
Okay. So I think my screen is visible.
Yes, it is visible. Please proceed. You can do it in full screen mode and please proceed.
So, good morning to one and all present here. So, I'm Debajyoti Das from Tezpur University, and today I'm going to present my work on metastructure absorber. So, this is the title of the talk, and these are the outlines. So, the basic question is, what do we mean by REM? So, here REM stands for radar absorbing material. So, radar absorbing material are the material which can absorb incident electromagnetic wave. So first time these materials were introduced during 1936, but then during World War II, the design and fabrication were intensified because these materials are mostly used for stealth application. So in modern day, a new technique called metamaterial absorber is introduced. So metamaterials are basically engineered materials. So here, some artificial structures are created on a substrate, and these structures are called unit cell. So these unit cells are arranged in repeating pattern. These dimensions are actually smaller than the wavelength of the interacting wave. So these unit cells are used to manipulate the incident electromagnetic wave. But then these metamaterial absorbers have very less thick. They are I can say that they are ultra thin. So sometimes thickness is just 1 mm or even that is less than 1 mm. But some problem with metamaterial absorber is that the bandwidth of these absorbers are very less. So to solve this problem, another technology has been introduced, that is metastructure absorber. So this is a hybrid design. So here the structural property of metamaterial is utilized along with the property of the constituent material. So to increase the bandwidth. Okay. Okay. So to design the whole metastructure absorber, so these are the stages I would like to say. So first we need to select a material. So as we can see in this picture, so this white color is a substrate. So here we need two things. One, we need a substrate material, and then we need a resonating structure. So this is this part is the resonating structure. So this part will mostly interact with the incident electromagnetic wave. So therefore, first we need to select a material for substrate. Then we need to also select a material for resonating structure. Then we need to do the characterization for selected material, and then we will design the structure, and then we will develop and test. So in our work, so we have chosen silicone rubber as a substrate material. So it is basically a very flexible material. So because of its flexibility, then high temperature stability, we have chosen silicone rubber as a substrate material. And then for the resonating structure, we have prepared a composite. That composite is prepared by mixing graphite powder and silicone rubber in 20 weight % ratio. So mixture is done by mechanical blending, and then we have to put it for 24 hours to settle down. Then several pellets has been designed for various studies. So the technique is, first we have to design a 3D printed mold. So this is the 3D printed mold, and then we have to fill this mold with the silicone rubber graphite powder, and then after 24 hours we will get pellets like this. So this picture actually shows that the flexibility of the material. So this is a very flexible material. Then we have done some material characterization. So this plot shows the tensile strength of the material. So this tensile strength is around 1.4 megapascal, so which shows that the flexibility of the material. We have also checked the contact angle of the material. So it is around 104.3 degree, and water absorbance is around 0.73% when we have soaked the material for 100 hours. So this study actually shows that the designed composite has a hydrophobic nature. So these are scanning electron micrograph. So this shows that the homogeneous mixing of the composite. And then we have done the most important study, that is the microwave characterization. So here we have studied the permittivity and permeability of the material. So since it is a non-magnetic material, so permeability is obviously 1, but permittivity is around, real part is around 6, and then complex part is around 1. Okay, so this is the summary of the whole characterization. So yes, material is stable up to 400 degree. Then loss tension is 0.15 to 0.18. So loss tension is a very significant part of this the study, because loss tension, the higher the loss tension, higher will be the loss of the material, and that's what we want, because we want to absorb the incident electromagnetic wave. So obviously material is very flexible, and this is lightweight, and it is of course it is hydrophobic. So from all this study, we can say that the prepared composite system shows a promising material for using as a radar absorbing material. So now the next step is to design the metastructure absorber. So to design the metastructure absorber, so this is the metastructure absorber design. So here we have a 3-layer. So one layer is copper, then one is silicon, and then this 20% graphite silicon composite. So this yellow color here is a metal. So this is a metal back. Then one matrix has been designed. So this is the silicon matrix, and then this 20% graphite silicon structure is embedded inside the matrix structure. So a very small thin layer of silicon is used, applied on the surface of this resonating structure, so that we can actually prevent them for other chemical effects. So this is the simulation study of the designed metastructure absorber. So this absorber shows that this curve is that shows the reflection loss. So here we can see that this has a resonant frequency at 34.8 gigahertz and a bandwidth of 1.15 gigahertz. And S11 is minus 43.6 dB. So this plot shows that at 34.8 gigahertz, most of the incident wave has been absorbed by the material. So now this 34.8 gigahertz is in the Ka band. So therefore we can say that the designed absorber is working in the Ka band. So bandwidth is also 1.15 gigahertz. So this is all without any bending, and also now we want to see what is the response of the absorber in presence of a bending. So that has been also simulated. So this plot shows.
Sorry to observe. Sorry to disturb Debajyoti, but you have 1 minute left.
Okay, sure. Thank you. I will finish my talk. So this plot shows the various the reflection loss at various bending radii. So these are the sort. So what we can see from that is that with bending, the performance of the absorber degraded, but still up to around 20 mm, this has a very promising result still. So if performance is more than minus 10 dB, that means it is absorbing more than 90% of the incident wave. So here we can see that up to 20 mm, the more than 90% is still absorbed by the material. That, yeah, of course, beyond 20 mm, performance degraded. So this is the summary of this whole work. So here we have actually designed a composite material, and then some physical and micro characterization was performed for the composite material. Then a encompassed metastructure absorber was designed using the composite, and this is the result of that metastructure absorber. So resonating structure was an octagon shape, then absorber is metastructure. This is flexible. Thickness was 3.47 mm, and resonant frequency is around 34.8. So here I would like to stop. So these are my references, and of course I would like to thank the whole organizers for giving me this opportunity to present my work. So thank you so much.
Thank you, Debajyoti, for the wonderful talk. It was very informative. I'm sure there may be some questions from the audience. I'm not the expert on this topic. May I request all the audience, if you have any questions, may you kindly put on your questions. 1 or 2 we may take.
Yeah, thank you.
So it seems like he is raising any questions. I would like to thank Debajyoti for the wonderful talk. Thank you so much, and we will move to the next topic. Thank you, Debajyoti. You may stop sharing the slide.
Okay, thank you.
Now, moving on to the next speaker. Before that, I would like to request, if there is any questions in between, you may kindly put on the chat box so that we will be discussed. We'll discuss at the end of the session. So next speaker is Sumitra from Surendas College. She will be speaking on the topic X-band metastructure microwave absorber based on biohybrid ionic gel. So may I request Sumitra to kindly take your time.
Thank you, ma'am. Am I audible?
Yeah, you are audible. You may kindly share your slide. Yeah, your slides are visible.
Good morning, everyone. My name is Ms. Sumitra. I am from Surendas College, Hazo. Today, I will be presenting on X-band metastructure microwave absorber based on biohybrid ionic gel. The rapid advancement of electronic devices and communication system creates a lot of unwanted signals known as electromagnetic interference. This electromagnetic interference pollutes the environment and also affects human body and living organism. Therefore, there is a need to shield such unwanted electromagnetic signals, and that can be done using absorbers. So we will mainly focus on microwave absorbers. Here is a diagram of a typical microwave absorber. Now for effective absorption of the microwave electromagnetic wave, the two conditions must be met. One is the impedance matching at the air absorber interface, and another is the attenuation of the wave inside the absorber. Now, ZA, this represents the wave impedance at the air absorber interface, and alpha represents the attenuation constant. And as can be seen from what the formula, what the parameters depend upon complex permittivity and permeability of the material. Therefore, the complex permittivity and permeability of the material is a very important parameter in deciding whether the material will be a good absorber or not. Now let us see the types of absorbers. So here it's a example of a typical conventional absorber known as the pyramidal absorber. So the conventional absorbers such as pyramidal absorbers were the earliest absorber that were developed. They are very thick, made of lossy rubber and foam. They are generally large in size. Because of their larger size, they were unsuitable for practical applications. Another type of absorber is the metamaterial absorber. So these are engineered composites that demonstrate exceptional properties that are not found in nature, such as perfect absorption, negative refractive index, etc. They are very small in size and have low density. They are of the order of millimeter. Here is the picture of the first metamaterial absorber by Landy et al. So the first metamaterial absorber comprises of three main parts: the split ring resonator, which is the electric resonator, and the dielectric material, and the metal ground plane. So the advantage of such absorber is that they're very they have very good absorption, near perfect absorption, but disadvantage is that they're limited to narrow band absorption. So another type of absorber is the metastructure absorber. The metastructure absorber generally are of the same types, just like the metamaterial absorber, but the only difference is that here the resonator are replaced by dielectric resonators. So where so the metamaterial absorber, where the resonators were metallic resonators, were replaced by dielectric resonators in metastructure absorber. So the main advantage of metastructure absorber over metamaterial absorber is that they can exhibit both narrowband and broadband absorption, and they are also flexible. Here is an example of an metastructure absorber. So the main matrix of the absorber is made of silicon rubber, and inside the silicon matrix there are highly lossy dielectric material resonators. So there has been many works going on, and in literature there has been many works where metastructure absorbers are made with embedded water atoms inside the rubber matrix. But one such problem, water atom and electrolyte solution, but one such problem with such metastructure absorber is that there is difficulty in design, and also there may be lots of error while trying to encompass the liquid electrolyte solution inside the water, inside the absorber matrix. So our main focus of this research is to replace the liquid electrolyte solution resonator with some materials which has very good conductivity and also is not in the liquid state. That is to replace such resonators with gel-like material. So for such, we have taken into account the biohybrid ionic gel. So biohybrid ionic gel are deep eutectic solvent formed from a eutectic mixture of salts and hydrogen bond donors. They have a very good conductivity. So preparation of the biohybrid ionic gel was done by taking choline chloride, which is the hydrogen bond acceptor, and urea, which is the hydrogen bond donor, in a ratio of 1:2. The mixture was placed in magnetic stirring for 1 hour at 90 degrees centigrade. Then after 1 hour, guar gum of 20% weight was added to the mixture at 80 degrees centigrade and stayed for 1 hour. Then the mixture was poured in a plastic mold of required parameters and left overnight. So after solidification of the mixture, the biohybrid ionic gel looks like this. Next is material characterizations of biohybrid ionic gel in X-band. So the material characterization was done using vector network analyzer, which uses the Nicholson-Ross-Weir method. So here is the here is the real permittivity of the biohybrid ionic gel versus frequency in the X-band region. So you can see that the permittivity is permittivity of the ionic gel over the entire X-band is of more than 12. And this is the diagram for imaginary permittivity of the ionic gel in the frequency region from 8 to 12.5 gigahertz. So this is the diagram of a picture of the vector network analyzer where the measurement was done. So next is unit cell design and simulation. For the unit cell design and simulation, Microwave Studio CST software was taken into account. So boundary conditions were set up in the software. So one Flocken mode port is used along the z direction for the propagation of plane wave. This is the diagram of a unit cell. Here, the main matrix was taken to be the silicon rubber matrix. And the silicon rubber matrix has a permittivity of 4 over the entire X-band, of around 4 over the entire X-band. So inside the silicon rubber matrix, we have embedded the biohybrid ionic gel. So this is the biohybrid ionic gel. And this is the back view of the unit cell. Here we have placed a copper ground plane in order for maximum absorption. So the design parameters are, for the silicon matrix, we have taken the design parameters to be 11 into 11 into 11, 3 millimeter, and the biohybrid ionic gel to be 6 into 6 into 1 millimeter. And the thickness of the ground plane was taken to be 0.036 millimeter. So, and this is the result that we have found, simulated result that we have found. So over the frequency range of 8 to 12.5 gigahertz, the reflection loss at 11.2 was found to be around minus 24 dB.
A gentle reminder, Smita, you have 1 minute.
Okay, ma'am. So this is the final result that we have found, and the absorption was found to be more than over 90%, and the bandwidth and more than 90% absorption was found over bandwidth of 2 gigahertz. So these are the references that I have taken into account. Thank you for listening to my talk.
Thank you, Smita, for the wonderful talk. We would like to see if there is any questions in the chat box. So far, we haven't received any question in the chat box, but I would like to request the audience to kindly put forward your questions. Any questions? It seems like there are no questions. Thank you, Smita, once again. We'd like to thank on behalf of the organizing committee for your wonderful talk. Thank you. You may stop sharing your slides. Yeah, our next speaker is Jyoti Prasad Gogoi from Kamal, from Dergaon, Deora College, Assam. He will be speaking on the topic Design of Broadband Microwaves Absorber based on perforated double layer expanded graphite phenolic resin composites. So may I request Jyoti Prasad Gogoi to kindly take your mic? Yeah.
Am I audible, ma'am?
Yeah,
Can
you
I
are audible.
Okay. Thank you, ma'am. Let me share a screen first. So is it visible now?
Yes, your slides are
screen?
visible. Yes, yes. You may proceed.
Okay. Good morning, everybody, and thank you.
One request, can you please share your slide in full screen?
Let me try. Is it okay now?
Yes.
Okay. So, very good morning to everybody. It seems that it has been an observer session like, so previous two lectures is from the same lab. Also, again, I'm thankful to the Bhawanipur Anchalik College for bringing my whole lab together today. Debajyoti and Sumitra Dole. I think they did not recognize me, but I know them. Anyway, my today's topic on design of broadband microwave observer based on perforated double layer expanded graphite phenolic resin composite. So presently it was a actually it was an old work during my PhD time. I done my PhD under the guideship of Dr. Nidhi Bhattarai ma'am. So today I'm just giving you a few information about how we can modify the structure and everything. So including this, the outlines of the presentation, I'll just give a brief introduction to the EMI shielding. Already it has been discussed, but I'll just quickly show it. Then how the absorption, micro absorption theory comes, and then how can we design the modification of broadband micro absorption for the same material. Then finally, I will show you a selected materials, then the final result using transmission line model. And it is simulated work, not a measured value. So we know that EMI shielding already discussed. It is the electromagnetic interference shielding. So it is actually because of the vast application of wireless communication system, including everything. But here I have selected the X-band because of certain application of this X-band in military communications, then radar technology, terrestrial communications, then many applications that have been observed, and we require to do a compatibility issue like how to adapt to this polluted environment, or you can say unwanted environment of electromagnetic waves. So for that, one of the solution is EMI shielding, and the solution is mostly by absorption. So from the typical observer we have got so far in commercial pattern, although it is very high level of stealth technology, but most of the case we go for pyramidal observer, then the land bag observer. There are few observers, but the main objective is to have a broadband. At the same time, it should be very lightweight of the material, and also the cost effective, because when you go for purchasing this observer, it costs around about lakhs for a particular small segment. So we try to figure it out, the cost effective issue, the lightweight, and most probably the broadband. Broadband, I mean that it is a maximum of 1 gigahertz, minimum of 1 gigahertz. So let me explain the theory of micro absorption. It is actually using the transmission line analogy. So it is looks like that. Here you can see this structure. This one, the multilayer structure. It can be analogy with the transmission line theory, where we have inductance, resistance, conductance, and capacitance. So similarly, when an electromagnetic wave incident on a particular material backed by metal plate, it can be considered that considered in a transmission line analogy way. So this is the input impedance configuration expression, where that one is this is the input impedance and one is the reflection coefficient. So the target is to find out the minimum level of reflection. The aspect of absorption is through the aspect of reflection. How much less reflection we come across, because it is at the end of the observer, it is metal bag, it is totally reflected. So this is how we the transmission line theory actually resembles to the absorption phenomenon. So here we have displayed two structure. One is single layer, that means you can see this PEC, that means perfect electric conductor, and above it, it is the layer 1, where it is actually the material we are talking about. So if we go for the mathematical formulation, single layer is given by this expression, or LC this much, and for the double layer, it is like again, it is a big expression. We did it using MATLAB program to find out the minimum value. But before that, we should know about the value of permittivity and permeability of that particular material. So it is found from the expression that one of the most important criteria to get a good absorption is impedance matching condition, which is a function of the material properties, that is the complex permittivity and permeability in a specific frequency range, and also along with the thickness. So another thing is that already I'm talking is the thickness consideration, because the different way of absorbing that incoming signal, but most in case of dielectric material, it is phase cancellation. I can say that quarter wave cancellation, because one wave is coming inside the material, get reflected from the metal bag, and it is get cancelled by a constructive destructive interference. So the condition is that to have this particular thickness of the material, it should be correlated with the guided wavelength. It is given by lambda g. Again, it is related to the wavelength we are trying to absorb, that is lambda naught. And it is dependent on permittivity and permeability, as you can see from the expression. So next is that, suppose I want to absorb a particular range of frequency for a broadband. Let us say minus 10 dB or minus 20 dB or minus 30 dB. That means it is in decibel. So it means minus 3 dB means half. So minus 10 dB means 90%, minus 20 dB more than 99%, like that. So if we could calculate. So let us say we want to absorb in X band, X band, whole X band within 30 dB absorption bandwidth. Then in this case, so we need to calculate from the resonance limit. That means it is estimated that it cannot be less than the thickness given by this resonance limit. So it is ultimate thickness to bandwidth ratio of the observer. That means if you want to achieve a particular wavelength, a particular absorption for a particular bandwidth, already discussed, but let us say there's because particular everything we cannot expect a perfect for. So let us say, is there any modification of the surface we are using? So here we have considered one modification. There are other modifications also, like frequency selective surface, but here we consider the circular perforation. That means we take the substrate, we make it holes in a perforated way, and we try to find out what will be the effective permittivity, because the impedance matching condition, it depends on the permittivity and permeability. And let us say if the signal is passing through the air, it almost keep traveling. It is not reflecting back. So if you give an environment like that to the incoming signal by the substrate, by perforation of that particular substrate in a particular fashion, let us say in a triangular lattice pattern, here it is given. So you can achieve the matching condition, impedance matching condition. When it get impedance match, the signal get entered the same substrate, then it get attenuated by many other ways, like dielectric loss, magnetic loss, whatever ingredient we are going to use inside the substrate. So before that, here we are trying to find out the effective permittivity is E effective is given here. Also, it is a complex quantity. So here, while considering this concept, we have to perforate it in a particular fashion. Let us say here H is the diameter of the holes we are going to perforate it, and the H, the dimension of the size of the hole should be 10 times less than the lowest wavelength you are going to use.
Sir, reminder, sir, your time is almost up. You may kindly complete.
Okay. So this is how we are going to find out effective permittivity. And using this effective permittivity, we are trying to find out the reflection loss for a perforated system. It is perforated means we have taken two layers to enhance the broad bandwidth. So here we have perforated two layers, and we find out the effective permittivity of the two layers. And finally, we found at the simulated work the value. But before that, let me tell you, the material I have selected is expanded graphite and phenolic resin. This is the way of making procedure. So this is how we have just claimed that it is actually happened. Then this is the calibration method. Then finally, this is the value where this is the complex permittivity for the non-perforated system. From that, we have calculated the effective permittivity. In using this effective permittivity, we have calculated the reflection loss graph. Number one is the reflection loss. Number second graph is the complex impedance. So this is how we found that the bandwidth for minus 10 dB is around about 3.5 gigahertz for this particular configuration. That is configuration for 10 weight percentage and 8 weight percentage. That means the layer 1 is 10% and layer 2 is 8% composition of expanded graphite and phenolic resin. So we can achieve, we can claim that it will be a good absorber, provided it will also give you some lightweight, because most of the material we have vectored because of the perforation. Already we have taken out the material via perforation, which will give an effective permittivity as well as it will give a broad banding. So within a particular thickness. Here the thickness is 4.5 millimeter. No doubt it's a higher one, but still it is good as it is very lightweight. Already expanded graphite is very lightweight. This is how we have just giving out the small glimpse of the whole work. It is found to be 3.5 gigahertz absorption for minus 10 dB bandwidth in the X band. This is the reference. So thank you.
We would like to thank the speaker for the wonderful presentation, and we would like to see if there is any questions. We may take one question at most. So I don't think that anyone is putting any questions. So I would like to thank once again. Thank you so much, Jyoti Prasad Professor, for your wonderful presentation. And moving on to the next, we have the next speaker, Gyanankur Bora from the Nagaon College, and he will be speaking on the topic detection of honey adulterations using linear regression method. So may I request Gyanankur to kindly share your slides and take your time.
Thank you, ma'am. Am I audible?
Yes, you are audible.
Okay, I'll share my screen now. Ma'am, is my screen visible?
Yes, your screens are visible, and you may kindly put on full screen mode and start.
Okay. So, good morning, everyone. I, Gyanankur J. Bora from Nagaon College, Autonomous, am here to present my talk on the topic detection of honey adulteration using linear regression method. So, this was my project work in my 6th and final semester under the guidance of my guide, Dr. Banasri Saikia. So, in this talk, we'll learn and discuss about what is honey adulteration and how I use machine learning programming, namely linear regression method, to detect adulteration in honey samples. So, without further ado, let us begin my talk. So, as the abstract I have written here, so what I did is I used a portable spectrometer and linear regression method and used it to detect adulteration in honey samples, and it was found that my model was 78.64% accurate in detecting adulteration percentage. So the objectives of my work are, as I had mentioned, to collect spectral data and then analyze those data using machine learning programming, and then evaluate my data for model accuracy. So first, let us understand what is honey adulteration. So it is the process of mixing pure honey with substances such as sugar syrup, thereby reducing the cost by compromising the quality and authenticity of honey. So as we all know, that honey is revered as a sacred product in a country such as ours because of its many medicinal uses. So this adulteration process can lead to distrust between the producers and the consumers. So our study uses linear regression and ultraviolet to near infrared spectroscopy with AS7 to 65X triad spectrometer. This is the name of the spectrometer that I have used to precisely detect an adulteration in the honey samples. So the mainly two principles were used in my project. So firstly is spectroscopy, or to be specific, Beer-Lambert's law, which suggests that different substance in a solution absorb different wavelengths of light. So this can be further analyzed for their identification. And secondly, second principle is a linear regression method. So this is a statistical method which best fits data points for further prediction and analysis. So in the right side, you can see the formula for linear regression method. Y equals to beta naught b naught plus b1 x1 plus beta 2 x2 plus dot 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 up to n terms, and then we have epsilon. So this is the determination constant or coefficient which calculates the error in the model. So we'll understand it later on during the result of my model. So now let us move on to the methodologies or various processes that I used for my project. So firstly, what I did was I prepared some adulterated honey samples. So this was done by mixing pure honey with sugar syrup at various ratios. So the various ratios are highlighted in this in here. That is 1:1, 1:2, 2:1, 1:3, and 3:1 ratios. So and then I made these ratios each for 5 molarity solutions. That is for 0.1 molar, 0.5 molar, 1 molar, 1.5, and 2 molar solutions. So basically, what we did was we created a data set of 25 samples, adulterated honey samples, and then we put those honey samples in we put those honey samples in this sensor, this red color sensor, which is AS7265X triad spectroscopy sensor, and it is paired with an Arduino Uno device, which collects the spectral data of those samples. So from this, we are able to obtain spectral data of each sample. So the apparatus, as you can see here, this is a handmade device that I have made using a wooden box, and the chip and Arduino paired are paired using wires. And this is the honey sample. And the box is covered for minimum external interference. So, and next what we did was we prepared the model, that is linear regression model, with the help of the data sets. Now here one question arises that I have written here 2600 spectrometer data samples. So, but I have previously mentioned that 25 sets of data were only used. Actually, what we did was for each data, we took 100 spectral data samples for each ratio of each molarity. So from that we get 2500 and remains 100 still. So that remaining 100 is for the pure honey sample, which we use to train our model. So, and also during the model preparation, we use a technique called tenfold cross validation. So to summarize in short, what it does is it iterates our data by splitting into training set and then test set. So basically it splits the data in 10 sets. That's why the name tenfold. And it takes 9 set of data as training set and 1 as test set. So then it iterates another one and another one next after
Sorry
next.
for the interruption. Kindly
Yes, ma'am.
complete your talk within 1 minute.
Okay, ma'am. Okay, sure. So lastly, what we did was model evaluation. These are basically the errors that we need to calculate to evaluate our model. So mainly what we are interested was in coefficient of determination. So this value will correctly predict our model accuracy. So then coming on to the results, we see that the error that our model is 78.6% accurate in predicting actual percentage of the constituent elements, that is honey, water, and sugar. So down here I have presented the graphs which shows a linear variation between the both predicted and actual values, and these are some outliers which explains our error in the accuracy. So to summarize and conclude my presentation, I'd like to say that the importance of portable spectrometer and machine learning algorithms in purity determination processes is of extreme importance, because it is a very cost-friendly way to check purity in substances. And also, I would like to point out that that my model was not accurate to the degree of say 90% or 95% because of the lower number of data that was being collected due to the unavailability of pure honey sample during the period of my project. So these are some of the references, and I'd like to thank my guide, Dr. Bonasri Soikia, and my lab mates. And also I'd like to thank the organizers for giving me this opportunity to present my talk. So thank you all.
Thank you, Gyanankur, for highlighting with your research. It was very interesting to learn about your research using the linear regression method, which I have not thought of so far. So we'd like to see if there is any question from the audience.
Hi, Gyanankur.
Yes, sir.
Hi, a very nice talk. Okay, that's really appreciated. So I'd like to ask two questions. Okay, so why did you choose linear regression model only? Why not any other model? What was your motivation behind?
Sir, basically programming languages are three types: supervised and unsupervised. So in supervised model, we cannot calculate the percentages of stuff. We can just verify whether it is adulterated or not. Means just it will give us the probability. It will not show the actual percentage of how much it is adulterated. So this was a work carried out by my senior. So I took his reference. So then I moved on to unsupervised machine learning programming. So using that,
I completely understand that. Yes, but why the linear regression model only? Why not any other?
sir, basically we use a program called Orange 3.0 software. So in that we can means in that software these models are already created. Just we need to input the data to check how much accurate is our model. So firstly I use other models using my data. Suppose say other regression methods are also available there. So but using the specific amount of data that I have said, that I have only 25 sets of data, right? So using that much data, the other models were not very accurate according to that software. So it is a very nice software that we can use. And the highest, at least it showed 99.99% accuracy, it showed using linear regression method. So after that, we use machine learning programming to create this model, actually.
Okay, and okay, thanks. Okay, and there's one more question. So for the fitting evaluation, so you check the R square, right? Coefficient of determination, right? So
Yes,
have you checked any chi-square fitting for this? Have you checked the chi-square fitting thing?
Chi-square fitting, sir, unfortunately not, because I didn't have got that much time. This was the last thing that I did.
Okay, maybe you can try the chi-square fitting and then check the results. Yes. Nice talk.
Yes, sir.
Nice talk.
Thank you, sir. Thank you, sir.
So we'd like to see if there are some more questions from the audience. Okay, so since we are out of time, since there are no questions coming up, if there are any questions, you may kindly contact Gyanankur Bora directly. Sometimes later also, I suppose he will be happy to answer that questions. So moving on to the next, we have next speaker Satya Sadan Daura from University of Petroleum and Energy Studies, Uttarakhand, and the topic of his presentation is investigation of piezoelectric beta phase in PVDF rice husk hybrid films. So may I request Satya Sadan to kindly take your time and share your slides.
Hello, good morning. Am I audible?
Yes, you are audible, sir.
Okay. I'm sharing my slide now. Is my screen visible?
Yes, your screen is visible. You may kindly put in the full screen mode and start your presentation.
Okay. Just a minute. Okay. So good morning, everyone. My name is Satya Sadan Daura. I am from UPS Dehradun. I'm a research scholar here at Department of Physics. So the talk I'm going to give on is on my work, which is the investigation of piezoelectric beta phase in PVDF rice husk hybrid films. So currently we have observed a trend in harvesting of ambient mechanical vibrations that are associated with various day-to-day activities like walking, running, or etc. And the energy associated with these activities can be harvested and maybe used to power some flexible devices. So this trend has been in the current research scenario. So for this harvesting of mechanical energy from the ambient vibrations, we require piezoelectric materials. So these piezoelectric materials work on the piezoelectric effect, which is whenever we generate or whenever we press any material which should be crystalline in structure, that mechanical vibration or mechanical deformation, it gives an electrical output. So this is the piezoelectric principle, and materials that are fabricated for this special type of application, they are called as piezoelectric materials, and the piezoelectric nanogenerators are the final product of these piezoelectric materials. So these piezoelectric materials can be used to power flexible electronics, and thus these can become like a civil and battery-free or self-powered source. Thus, this is a complete waste to energy conversion. So whatever energy that we have on the environment, we can harvest that and we can use that to convert it to some useful electrical output power and power flexible devices. These are the 4 classes of piezoelectric materials: the single crystals, ceramics, single crystal ceramics, composites, and polymers. So all of these materials have their different properties, and depending on the type of application that it's required, so different permutation combinations of these materials are done for fabrication of piezoelectric nanogenerators. So my interest is solely on piezoelectric polymers because these are carbon-based polymers. These are flexible, lightweight, non-toxic, and biocompatible. Though the output from these piezoelectric polymers is slightly less as compared to the other piezoelectric materials like single crystal ceramics and composites, but the polymers are the non-toxic and biocompatible, and hence they can be used for flexible sources, flexible devices. On the other hand, the other piezoelectric counterparts like single crystal ceramics and composites, these may be hard or brittle, although the output power from them is high as compared to polymers, but these are mostly non-toxic and are not compatible. So that's why we cannot use them to harvest the energy associated with human body movements like walking, running, hand movement, twisting of the wrist, or even the heartbeat from our heart. So thus these polymers can be used to synthesize flexible power sources for running flexible electronics like sensors, displays, circuits, etc. So these are some of the applications of piezoelectric polymers. Like they can be used for health monitoring, like heart rate monitoring, pulse monitoring. They can be used in flexible circuits. They can be used for synthesizing or fabrication of flexible displays of flexible electronic sensors, like pressure sensors, respiration sensors, etc. A new class of piezoelectric materials that have gained interest are those of piezoelectric biomaterials. Biomaterials, like these are readily available everywhere. So biomaterials are mostly the biopolymers like cellulose, 3%. These are found in plants, shells, fungi, etc. Collagen, which are found in bone, skin, muscle. These were found to have inherent piezoelectric effect in them. So research on these materials is in current trends. So now I would like to briefly discuss about PVDF composites. PVDF is a polymer. It is called as polyvinylidene fluoride. So I would like to give a brief introduction of what PVDF is. So PVDF is a semi-crystalline piezoelectric polymer. It lies in 3 phases: alpha phase, the beta phase, and gamma phase. Out of this, the alpha phase is non-piezoelectric. So we don't need this alpha phase for device fabrication or energy harvesting applications. But the beta phase and the gamma phase are piezoelectric. And between these two, the beta phase has the highest piezoelectric coefficient. So that's why it is highly desired for energy harvesting applications. So there have been various mechanisms of converting the alpha phase in PVDF films into the beta phase. Like we can stretch the films, we can fold the films in a particular electric field, or you can use a suitable polar solvent while synthesizing the PVDF films. Fillers like nanoclay and graphene oxide can also be added for this alpha to beta phase conversion. And most importantly, biowaste like orange peel, fish scale, or onion skin, they have also been are reported to have been used to convert this alpha phase into the beta phase. So in this literature, here PVDF and nanoclay has been used to convert the alpha phase into the beta phase. In the left, you can see this is the XRD profile. This black one represents the PVDF film, not PVDF powder, PVDF film. And this insert represents that of the PVDF film. This is a PVDF film insert, but it mostly lies in the alpha phase. But upon polling, this PVDF film, this gets slightly converted to the beta phase. So this is the characteristic profile of the beta phase. So you can see this profile of the PVDF film and this profile of PVDF cold film is significantly different. So that's why we can see that the beta phase has been induced. This represented by the red bar. Beta phase has been induced, and we can see the beta phase, alpha to beta phase transformation. Now, the moment nanoclay has been added at 10% and 15%, this beta phase increases further. So the PVDF and nanoclay hybrid shows significant conversion of alpha to the beta phase upon adding certain amount of nanoclay. So here the beta phase present was 79%. And in this research, here the first one being that of pomegranate peel. Here also we can see the distinct XRD profiles of pure PVDF powder and that of PVDF pomegranate peel hybrid. So this pomegranate peel has cellulose, and as I have mentioned earlier, cellulose is a piezoelectric material. So due to the synergistic interaction between the PVDF and the pomegranate peel, the phase conversion from alpha to beta is evident. So here the beta phase was present.
Time.
Yes.
Talking.
Yeah. The beta phase was found to be at 50%. Similarly, in the axial membrane case, here also we see that upon addition of axial membrane and nanoclay, the beta phase has been significant. Here also we see the beta phase to be 80%. So now coming to my work, which is on bio-waste, PVD and bio-waste, I'm going to discuss. So here I have used PVDF as my polymer, DMF is my solvent, and the bio-waste that I have taken is cellulose with rice husk. So this is the typical synthesis route of my PVDF film synthesis, PVDF rice husk films. So here we dissolve the powder in DMF solvent, and following this route, we obtain this PVDF RH film. So we made this film at RH concentrations of 0 to 28% of PVDF, and we used PVDF to DMF ratio of 1:4. These are the XRD and the FTIR plots of our samples. So in the XRD profile, you can see the PVDF powder lies in the alpha phase. Then the moment we convert this make a film of this PVDF powder, we see that these profiles are very distinct. So as I've mentioned earlier, the role of solvent is also very essential. So we have used a dipolar solvent, which induces beta phase in the PVDF powder when converted into films. Now here we have added rice husk, and we can see that the beta phase is evident. Similarly, in the FTIR, the lower represents the PVDF powder, the upper the next one represents the PVDF film. Here also we see the distinct phase transformation from the alpha phase to the beta phase, that is non-piezoelectric to the piezoelectric phases. And the moment we add on increasing the rice husk, we also get a beta phase. Thus, we see the piezoelectric beta phase peaks at 20.4 to 20.8 in the XRD. For FTI, it lies at 473, 510, 600, and 840. So these are the typical deconvolutions that we did to quantify the presence of beta phase in our films. This is for the pure film without any bio-waste. So here we assign 3 peaks corresponding to amorphous alpha and the beta phase. We deconvoluted it, and we found that the beta phase present in the pure film was 74%. So in the hybrids, what we did is that we added an extra rice husk peak corresponding to that of crystalline. These are the results that we have obtained. So here we see the beta phase in the pure film was 74%, but the moment we added 0.4 weight percentage, 0.65 weight percent rice husk powder, this beta phase rose drastically to 87%. So this can be attributed to the synergistic interaction between the cellulose of rice husk and the beta phase of PVDF in the P1D4 RH0 film or pure film. But the moment we kept on increasing the content of rice husk, we saw that the beta phase has decreased considerably. So, we can say that due to the formation of agglomeration or upon addition of rice husk, the agglomeration formation has been taken place, due to which it reduces the crystallinity of the samples. So the crystallinity has been reduced in the rice husk hybrids, And that's why we see this decreasing trend of the beta phase. We did optical microscopic images of our sample. So this is a pure film. Now in all these films, the rise husk has been increased. So from 0.625 till rise 10%. So we see that the agglomerates formation is more.
I would
as
like
we
to request Satya Sadan to kindly put
yeah.
your concluding remark because we are.
Yeah, I'm just
time.
one slide is left. Just one slide. We see that agglomeration is happening. So that's why it is decreasing beta phase. So this is the mechanism. So in a pure film, PPDF rise pure film, the beta phase is evident at 74%. Now here we have added rice husk. This is the hydrogen bonding between rice husk, cellulose, and PPDF. This converts to the 74% beta phase in the film to 87% in the hybrid. So and this is the reason why we see this huge jump in the beta phase. Now I have tried to show it more schematically. So this is the PVDF. This is the rice husk that interacts to hydrogen bonding with PVDF. And this is the stage when this increase is happening from 74 to 87%. Now, the moment we add on rice husk, due to the mutual interaction of rice husk, the agglomeration is happening. And the mutual interaction among rice husk is far more than the PVDF rice husk interaction. So that's why agglomeration is happening, and we have seen that this decreases the crystallinity of the films. So summary, that intermolecular hydrogen bonding between PVDF and DMF converts the alpha phase into beta phase in the PVDF field. Synergistic interaction between rice husk and PVDF increases beta phase fraction in the PVDF rice husk hybrids from 74 to 87. The higher beta phase fraction is observed at lower RH concentration due to synergistic interaction and more crystalline orientation of the beta phase. And decrease in the beta phase at higher RH concentration is observed due to the reduced crystallinity or amorphization in the sample. So formation of clusters we have seen. Lastly, I would like to acknowledge UPS for giving me PhD fellowship, UPS seed grant of my supervisor, Dr. Parshajit Kalika, UGC DA CSR project under him, the CIC R&D and the chemistry lab of UPS, and finally Professor Ashish Mathur of Interdisciplinary Research for helping us to carry out the optical microscopy. And most importantly, I would like to thank the organizing committee of Physics Frontiers, Bhawanipur Anchalik College, for providing me this opportunity. So this is the basic summary, or you can say the overall work that we have been doing here. So here you see the piezoelectric mechanism is this one. These are the various materials, polymers and bio-waste, and these are the hybrids. Thank you so much.
Okay, thank you, Satya Sadan. Thank you very much for your wonderful talk.
Thank you.
I would like to see if there is any questions. I have one question personally.
Yes.
I'm not an expert on your topic, but I just have one question. You have mentioned something about like piezoelectric biomaterials. I would like to know what is the application of those piezoelectric biomaterials?
Mostly the application, the current scenario of these piezoelectric biomaterials is that of energy harvesting only. So these piezoelectric biomaterials can be fabricated into some nano generators that generally give an output at nanowatt to microwatt range. So these are very miniature devices that can be synthesized out of these piezoelectric biopolymers or biomaterials. Of course, there is a huge, you can say, processing of these biomaterials before being integrated into these devices. So the current scenario is that these are used for piezoelectric energy harvesting only. There are many other applications of these biomaterials like wastewater treatment and all, but in terms of piezoelectric effect, these are only used for energy harvesting only. So this is the current trend. Yes.
Okay, thank you so much. And I would like to see if there is any questions from the audience. All right. Thank you so much. I would like to thank the speaker once again. And moving on to the next, we have now Amitav Khandelwal from the University of Galway, Ireland. And he will be speaking on the topic bioelectrochemical systems, current status, and future perspectives. So may I request Amitav Khandelwal to kindly take your time and share your slides. Amitav, are you there?
Okay, we can see him with the participant list, but maybe some technical problem might be. Okay. to save some time, can we go to the next speaker, Chairman,
Yeah,
Madam?
sure. Yes, sure.
Okay,
So
sure.
then our next speaker will be Dipankar Bora from Bholanath College. He will be speaking on machine learning assisted microwave metamaterial absorber for X-band applications. So may I request Dipankar Bora to kindly take your time?
Hello, ma'am. I am audible.
Yes, you are audible. Kindly share your slides.
Is it visible?
Yes, please, sir. Your slides are visible.
Good afternoon, everyone. Myself, Dipankar Bora. I am from BN
Sir,
College.
can you please share the slides in full screen?
Is it visible now?
Yes, it is visible.
Is it full screen right now?
Yes, sir. You may proceed.
My title of my talk is Machine Learning Assisted Microwave Metamaterial Absorber for X-band application. These are my presentation outline. Basically, I'll skip the absorber part because the speaker already talked about this absorber. However, I will give a little bit introduction to the metamaterial absorber, then machine learning approach and metamaterial, then design and simulation of my proposed metamaterial absorber, then the simulator result, then to the conclusion. So, meta means beyond nature. This means metamaterials are not necessarily occurring material; they are engineered material. They have very unbelievable electromagnetic properties. For example, negative refractive index, negative permittivity, and negative permeability. And because of these properties, they find defined applications like electromagnetic observers, sensors, antennas, super lenses, energy harvesting devices, etc. Here, I will mainly focus on electromagnetic observers. Now, what is the advantages of metamaterial observer? The first one is there is a large design options for impedance matching and high attenuation of electromagnetic observers. Secondly, they have in-plane geometry that reduces the thickness significantly. And we can, here in this figure, I have shown some unit cells of metamaterial observers. By sensing the structure or dimension, we can sense the frequency. And since there is no inclusion in the substrate material, therefore the weight is very low. But what is the challenges? The challenges is the most of the metamaterial observers are fabricated on the rigid substrate, like FR4. Secondly, they are fabricated by copper, gold, and which is corrosive and costly, and they provide narrowband absorption. And mostly the designing of the metamaterial observer is a trial and error process. So what we do, we incorporate machine learning in metamaterial observer design because, as I already told you, that it is a trial and error process. Therefore, there is no correlation between this structure design and the required spectra. So in the machine learning approach, we train the machine so that we get a desired relationship between the dependent function and the independent function. So, and from the data set, they automatically analyze, they obtain the loss from the data, and they predict the unknown data. Unknown data here is the basically the structural design. So this is the unit cell design we have simulated here. This is a three-layer unit cell. The first one is the expanded base conducting layer at the bottom. Middle layer is the LLDP substrate, and the top layer is again the expanded graphite base layer. Since LLDP is a flexible, so our is a flexible substrate. So the whole design or whole absorber we can say is a flexible metamaterial absorber. So these are the design parameter of our proposed observer. Here you can see there are 7 design structures for this proposed observer structure. And since this is a trial and error process, so for optimizing this structure for each simulation, it takes around 5 to 10 minutes. So it's a time-consuming process to optimize this structure. So what we do, we optimize this data in the machine learning process. Now, from the CST simulation, here is the result. Before going to the result, let us give you brief important parameters of metametric observer. One is reflectance, another one is transmittance and absorbance, and they are related by this formula. And this figure 6, in this figure 6, this is the magnitude of the reflection loss. Here we can see that we are getting around 1 GB of bandwidth for this proposed structure. And in the figure 7, this is a magnitude of the absorption and reflection. Here figure 6, it is presented in dB scale, and in figure 7, it is presented in a linear scale. Now, this is the simulated electric field distribution at the 2 resonant frequency. Here we can see that the electric field is mostly concentrated over the split of the square paths. Again, we vary the substance of the observer for that 5 different values, starting from 0.5 mm to 1.5 mm. Here you can see that as we increase the substrate thickness, the reflection loss spectra is mainly tends to the lower frequency and the bandwidth is increasing. Now, what is the importance of this thickness variation? Main importance of this thickness variation is we are basically collecting the data for training the machine. So this is the flowchart of the machine learning approach for our purpose. Firstly, we'll collect the data. Main data is collected from this substrate thickness process. For one spectra, we have 10,000 data. Since there are 5 spectra, therefore, for our training purpose, we have 50,000 data. Then we prepare the data in a single sheet, and then train the model, and then evaluate the model and deploy the model. While we training the model, we separate the dataset into training dataset and testing dataset from 40% to the 70%, and then we evaluate the data and we deploy the model. Here, for the comparison of the regression model, we basically calculated 2 errors. One is MSME, mean square error, another one is root mean squared error. Here we can see that as we increase the dataset testing size, the error is increasing. This means that at the higher side of training data, this 0.4 is the testing data. That means 0.6 is the training data set. So if we have the higher range of data set for training purpose, so the error is very less. And as we increase the data to the training data or reduce the training data, so error is justifiably increased. So we can say that that for the higher range of training data, we can adopt this regression model. We are basically using random forest regression model for our this unit cell purpose. So in conclusion, we have designed a broadband metametric observer for X-band application. Then this proposed observer shows 1.2 gigahertz bandwidth for X-band frequency range. Since observer is fabricated on LLDB substrate, therefore this observer is flexible enough to use in conformance services. And then this unit cell is designed using expanded graphite, which is a non-corrosive and can be used in a high temperature application. And since the geometry is fourfold symmetry, so this provides the polarization insensitive behavior. With this, these are the reference. I conclude. Thank you.
Thank you so much Dipankar Bora for your wonderful presentation. And before moving to the next presentation, I would like to see if there are any questions coming from the audience side. Anyone wants to ask any question? Okay, I have one question, sir. You have said something like these are like corrosion free and then can be used for a very high temperature. So, sir, how far is it, like up to which temperature it is tested?
Yeah, there are two different aspects. One is substrate is LLDP. LLDP goes up to around 300 degrees Celsius. However, if we talk about expanded graphite, the conducting substrate, it goes around 1200 degrees Celsius.
Thank you so much. So thank you so much once again for your wonderful presentation. I would like to move to the next speaker. We have Jagat Dupendra Rai from Bholanath College. The topic of his presentation is investigation of the deformation of Earth's surface induced by surface mass loading. So if Jagat Dupendra Rai is there, you may kindly start your presentation.
Thank you, Madam Chairperson. So I'll share. Am I audible?
Yes, sir, you are audible.
Okay, so let me share the screen. Is my screen visible?
Yes, yes.
Okay. Is it visible? Okay.
Yes, yes, you are visible, sir. You may
Okay,
start.
so my topic is regarding the investigation of the Earth's surface that has been induced by surface mass loading. So this topic actually transacts the realms of various subjects that includes physics, geophysics, geodesy, and geoinformatics. Hope I don't be an outlier in this conference. So yeah. Before moving to discuss the results and discussions, so let us have an understanding about what are the surface loads actually that actually affects the Earth's surface. Yeah. Well, these are the overall spectrum of the surface mass loading that has been the precipitation. We can have the surface runoff. Then we can have a evapotranspiration. This all are parts that forms the hydrological cycle, and that actually mean the bulk of my research topic to understand the hydrological cycle precisely by using some geodetic sensors. Well, apart from hydrological cycles, we have some coastal fluctuations from oceans. Then we have the mass balance in the Antarctica and this polar regions. And we have the isostasy. Perhaps there is a term called glacial isostatic adjustment. Well, these are all that actually defines the surface mass loading, and that has their range of frequencies, and their impacts and amplitudes are varied in the time scale and also in the frequency scale. Well, this all surface mass loading, why we study? Well, this all impacts our surface, and that impact the overall. Sometimes it has been found that actually impacts the overall microseismic events over the regions. And the region that I have considered is in Gangetic Plain. This near to our Himalayan mountain range, and also there has been report that there is an hydrological stress that has been observed in 2009, and still the stress is going on about the groundwater issues. So whether any kind of geodetic sensors can provide a tool or to understand how this hydrological cycle we can have an study. Well, the answer is the satellite geodesy and GNSS. Well, the GNSS stands for Global Navigational Satellite Systems. We all use the mobile apps having the GPS enabled position we get, and the GPS is basically from the USA, and GLONASS from Russia, Beidou from China, Galileo from European agency, then QZSS, Quasi Zenit, this is from Japan, and our own Indian Regional Navigational Satellite System, also known as NAVI, actually these satellites transmit the signal, and we get our own what is called position. Apart from position, and other satellite geodetic technique like VLBI, which stands for Very Long Baseline Interferometry. We have SLR, stands for Satellite Laser Ranging. Then we have LLR, Lunar Laser Ranging. we have DORIS, and in India we have the GNSS predominantly, started from around 1998, 1999, initiated by few CSR labs like CSR Fort Pradham Institute and CSR National Geophysical Research Laboratory. And now the India is going for a big project on the FLBI called Very Long Baseline Interferometry. Hope we'll soon get, this is another huge project apart from the LIGO that India is now looking for. Well, the overall, what is the geodetic scenario of my research topic? So we have surface mass loading. Suppose hydrological load, we all know this is any weight. If you put on a surface, it will depresses. So if we have a geodetic stations or GPS station nearby, it will depresses when the surface is high. And if the surface loads removes from the surface, it will be on the upside. So you can see this is a station that I have taken to show from a Nepal Himalayan station. So you can see a clear annual cycle. So when the stations we have a higher seasonal surface mass loading, it will go down, and then it is goes up and goes down and goes up. It continues. Well, this kind of signal can also be obtained in our plain region, like Ganges region, Ganges basin. So we have few of the GPS stations located in Gangetic plain. Like in Lucknow we have, then we have in IIT Kanpur. So this is just to show a schematic share of a GPS station located in IIT Kanpur. And this GNSS data actually transmits some phase data about various satellite signals. Then we need to use this phase data. There are two kinds of data it sends. One is phase pseudo range and one is pseudo range. So we use the phase data, and that has been processed by a few scientific softwares like Gamete, Globke, and Barnis. Gamete has been developed in MIT and Barnis in the University of Bern to obtain the position by using this satellite GNSS data. This data can be combined using other information like orbit informations, reference plane informations, and then that all together put into a filter called global Kalman filter to obtain the deformation time series. So this is called the observation that we can have in our land. And about the model is about land surface discharge model. This is actually of a global model that I have taken, but this global model needs to be tuned with some what is called regional influences because this global data set actually have some sparse stations and sparse data. So we need to tune this data. Research is going on how we can actually tune and have some modified hydrological model. So this is has been developed in GFZ Postdom that I have used. Well, so the results that I have obtained, this is some sort of pilot study for how can an observation on hydrological model can be used. So we can have a clear seasonal cycles that has been obtained from both GNSS station and hydrological load. And we can have a clear up and down signal, and the phase is almost matching. We can have a clear depression and clear elevation from the both the model and as well as from the observation. And to obtain the what kind of periodicity lies in this signal, we have simply used a method called paraspectral density. Yeah, so this is also we can find the power of the signal is maximum at the annual periodicity. So both this confirms the presence of annual cycle. So this annual cycle and annual periodicity actually due to the monsoonal rain and the monsoonal surface load that actually India and Southeast Asia receives. The more stations and more geodetic infrastructure will be helped to decouple all the signals that actually prevails in the Earth's surface, and studies are going on in India too. Well, so this is the some pilot investigation we have done, and the future studies are going on. So overall discussion and conclusions, we can have the GNSS actually can sense the what is called hydrological signal, and considering the fact that GNSS actually sense the hydrological signal, And particularly, in fact, when there is a agency called Survey of India that has initiated a program called setting up the course network all over the India, which contains around 700 GPS stations all over India. So all the stations can be summed up to have an overall model. We can have a observed hydrological model by using this GNSS station. So it is soon be realized when all the stations have their data at least up to 3 years. Well, so this is just a single research that demonstrated that GNSS station can be used to sense the surface hydrology to some extent, with some limitation of course. Some more future studies and more calibrations in the terms of model validation and observations are needed, which will be undertaken. Thank you. So, and the last acknowledgement for the Nevada Geodetic Laboratory from University of Nevada, Reno, and I acknowledge the data that received from NASA Jet Propulsion Laboratory and the service that has been provided by International GNSS Service. Thank you.
I would like to thank the speaker for the wonderful presentation, and it was very informative and on the topic like deformation of Earth's surface. We'd like to see if there are any questions from the audience side. Let me repeat once more. If there is any questions, kindly put forward your question.
Okay.
Okay, seems like there are no questions. So thank you so much, speaker, on behalf of the organizing committee. So I'd like to request the next speaker, Dr.
Excuse me,
Yeah.
Chairperson ma'am. So I just got the information that Amitabh Khandelwal, Dr. Amitabh Khandelwal, he has resolved the issue of his internet of the. So Amitabh Khandelwal, are you there?
Yeah, I'm here. Can you hear me now?
Yes, I can hear you. Then kindly share your screen.
Okay, just a second.
Yes, can you do it in full screen mode?
Is it visible?
Yes, it's visible.
Okay. Thank you so much, Dr. Thapa and Dr. Sumitra, for providing this opportunity to me. And apologies for earlier, my mic was not working. So myself, Amitabh Khandelwal, and the work I'm going to present here was actually the work I conducted at IIT Jodhpur, IIT Gandhinagar, and University of Galway overall. So basically, I will be talking about microbial fuel cell or bioelectrochemical systems, which are a device to treat wastewater and resource recovery and bioenergy production. So before going into the deeper, we will be learning what microbial fuel cell actually is. So if you can see on the screen, I'll try to get my pointer. So basically, microbial fuel cell is a two-chamber device, and both of these chambers are divided by a middle proton or cation exchange membrane. In the left side, it's the anodic chamber, and in the right side, it's the cathodic chamber. In the anodic chamber, we feel wastewater or waste, which is having ample amount of organic matter. So these waste is degraded by special bacteria. We call them exoelectrogenic bacteria. I'll explain why they are called as exoelectrogenic bacteria. So these bacteria degrade this organic matter, and because of that degradation, there is a production of CO2, protons, and electrons. These protons travels through this middle proton exchange membrane to the cathode, and the electron travels through an external wire or circuit, and these are captured in the cathodic chamber by an electron acceptor species. It can be oxygen or any artificial electron acceptor mediator. So you can either make it aerated by external oxygen pump, or you can grow microalgae in the cathodic chamber, which by the photosynthesis reaction gives rise to oxygen as a byproduct. So what is happening here is, like in the anodic chamber, there is a degradation of organic matter, emergence of electrons, and these electrons are captured by the oxygen. So simultaneously, we are treating organic matter or wastewater, and we are recovering this small amount of electricity in the form of bioelectricity. So these are the reaction associated with both the compartment. In the anodic chamber, there is a degradation of waste, and in the cathodic chamber, there is oxygen is getting reduced, and we are getting bioelectricity. This is a basic concept of microbial fuel cell or a bioelectrochemical system. These are the challenges. I will not go into the details. So what we have done here is there are various applications of microbial fuel cell, such as wastewater treatment, different wastewater, let's say domestic or industrial wastewater, and also in the bioenergy production. So what we have done here is in order to scale the technology up or commercialize the technology, we scaled it up using the low cost material. And for making it with the low cost material, we used rock phosphate blended clayware as an anodic chamber, or polythene bag, low density polythene bag as a cathodic chamber. So the volume was 1 liter for anodic chamber and 10 liter for cathodic chamber. For the electrode material, we use graphite felt because you need electrode as a current collector in both of the chambers. And this assembly was installed in outdoor in sunlight. Like there was no external control of pH and temperature, and we just wanted to see like what is the performance in outdoor conditions. And the other thing is rock phosphate was blended in different concentration in clay to fabricate these anodic chambers. So as we can see, like here, we got the maximum energy output from 5% rock phosphate blended microbial fuel cell. That was equivalent to 11.53 kilowatt hour per meter cube. And both the voltage and current density was higher in this 5% rock phosphate MFC. What we here observed is like because of the blending of this rock phosphate, we blended this rock phosphate in order to make the cation exchange membrane more conductive in terms of ion exchange. But we didn't observe that. Instead, we observed more algal growth because of the blending of the rock phosphate. What was happening there is the rock phosphate is basically calcium, magnesium, and phosphate silicate and phosphate. So there was a slow release of phosphate in the cathodic chamber from the membrane side, and because of that, algae was growing higher. So the overall output was power density 1.2 watt per meter cube, current density was 8.5 ampere per meter cube, and the total energy, which was a summation of electrical energy plus algal energy, was equivalent to 11.53 kilowatt hour per meter cube. And this total assembly we could fabricate at the cost of only $11. So the next project which we carried out, it was for the uranium removal from the nuclear waste. So as you know that in the nuclear waste there are uranium, thorium, and there are a lot of radioactive elements which, if they are not treated, they can leach into the water, and it can create a lot of diseases to both aquatic system, plant, and humans. So what we have done here is like we try to precipitate uranium into its less reactive form, that is uranium-4. So uranium is hazardous in uranium-6 form, but if you can precipitate it, you can just remove it from wastewater and you can treat the water. So the precipitated form is uranium-4. So what we have done here is in the anodic chamber, like it's similar as before, there is a treatment of wastewater. In the cathodic chamber, we put denitrifying bacteria. These bacteria can convert nitrate into nitrogen. Nitrate is also a big problem for water, so we need to remove that also. So we are here simultaneously removing nitrate as well as uranium. So what is happening here? These denitrifying bacteria were provided glycerol 3-phosphate as a carbon source. So these bacteria were using this glycerol as a carbon source and releasing phosphate from the glycerol 3-phosphate. This phosphate was combining with uranium-6, and because of that reaction, it was converting into uranyl phosphate, that is uranium-4. So this is how we were getting rid of uranium from the water by precipitation reaction. So these are the key results from this study. There was 90% of uranium removal and 85% of nitrate removal. And if I talk about the power, we got 2.91 watt per meter cube of power density using this strategy and assembly. The next study which we carried out is removal of raw textile wastewater. You all know that textile industry produces tons of textile wastewater, which is having a lot of toxic dyes, and they should be treated before this effluent goes into the mainstream of water. So here we also use the clayware, but no, without rock phosphate. And in the cathodic chamber, as a cathodic chamber, we use just a plastic bucket. So these are the result of this study. Here we compared the degradation of dyes with both bacteria and microalgae. As you know, in my last slide, that in the anodic chamber there are bacteria, and in the cathodic chamber sometimes we use algae. So here in this study, we compared that what is the degradation of textile dyes in both of the chambers. So here you can see these are the data before treatment, and this is the after treatment from anodic chamber using bacteria, and this is after treatment from cathodic chamber using microalgae. So you can see that in the anodic chamber, the system was the dye water was almost colorless. Initially, it was greenish blue, and COD was almost gone, 250 to 81, and in the cathodic chamber, it was 26. This is the summary of all the results we got. The color removal efficiency from anodic and cathodic chambers were respectively 89.5%, and in the cathodic chamber, it was relatively low, around 40%. And the power density and current density from this system was 2.1 watt per meter cube and 8 ampere per meter cube. So in the next project, these are three projects I showed the application of microbial fuels and in wastewater treatment, both domestic and industrial wastewater. Now we will see some biogas or some bioenergy production using microbial fuel cell. So you all know that there is a increase in interest in biogas production from all the solid waste like food waste or dairy wastewater using anaerobic digestion. But what happens when you generate biogas? When you generate biogas, biogas is essentially biomethane. So, but when the biogas is generated, apart from methane, there are a lot of other gases like CO2, H2S, ammonia, etc. These impurities should be removed before you take this biogas in any other application like fuel or anything else. Because if you take this biogas as raw, it's very corrosive, and it will corrode the engines, and it's not good for your application. We need to remove this. So we use the same strategy in this problem, and we found out that our system was able to get the biomethane in the concentration of 85 to 93% without any trace of CO2, H2S, and ammonia. So the rest of the composition was mainly oxygen, and we captured CO2 using microalgae. And because of this capture, microalgae biomass production reached to 6.8 gram per liter. And the power and current density we obtained from this study was 17.3 milliwatt per meter square and 170 milliampere per meter square respectively. The overall energy recovery from this process we obtained around 71.54 kilowatt hour per meter cube. And this is my research thing. And these are some of the courses which are running in University of Galway for both MSc and PhD. Anywhere is interested, they can go to the website, and if they want to enroll, they are welcome. So this is from my side. Thank you so much. If you have any question, please let me know.
Thank you so much, Amita, for your wonderful talk on the applications of bioelectrical systems. And before asking to the audience, I have one question from my side.
Sure.
You have said something like the conversion of uranium to uranium in water. So,
yes.
Yeah, it was converted, and how thereafter, how is it removed from the water?
Yes.
Yeah.
So it was removing, like we were removing in the precipitated form. So you can just, remove uranium selectively from the water.
Thank you so much. So we'd like to see if there are any questions from the participants. So it seems like there are no questions. Once again, thank you so much,
Thank you so
for
much.
your
Thanks,
wonderful presentation.
Thanks a million.
Thank you so much for your time. So
Thank
moving on to the next, we have the next speaker.
Sorry to interrupt, madam.
Yes, sir.
Dr. Bhattarai, madam. The next speaker was supposed to be Nayana, but he is not available right now due to some issues. So instead of him, Rasmi Bhattakur will present.
Sir, there is Priyanka Das in my list. Priyanka Das is also there. Is she already?
Okay. After Priyanka Das, then it will be Rasmi Bhattakur.
Yeah, yes, sir. So I would like to request Priyanka Das, if you are there, you kindly share your slides. She is from Salwari College, Assam, and she will be talking on the topic applications of smartphone-based sensing tools for analysis of agricultural soil parameters.
Good afternoon, everyone. Am I audible?
Yeah, you are audible.
Let me share my screen. Is my screen visible?
Yes, please go ahead.
Good afternoon, everyone. Myself, Dr. Priyanka Das. I am an assistant professor in the Department of Physics, Salwari College. Today, I will be discussing on various smartphone-based sensing tools that are used for analysis of agricultural soil parameters. So as we all know, the importance of agriculture in our day-to-day life, agriculture is a very important sector because it provides us food. It also increases the capital income of a country, and it is a major employment source. So crop yield is basically depend on soil fertility. As we all know, India is a agricultural based country because more than 50% of India's total population is engaged with agriculture. So soil's fertility is basically determined by the soil chemical or physical parameters. So physical parameters means its texture, its humidity, etc. And chemical parameters means its pH level and other chemical contents. So already there are various existing techniques that can be used for determination of the soil quantity, but these techniques need various sophisticated instruments that are very costly, that consumes large amount of electricity, that needs high computational power, and also expertise persons are needed to operate these tools, and these are very bulky in size, and also communication facility is lacking in this sensing tool. Hence, there is a need for alternating soil quality monitoring tools so that we can regularly test the soil and we can improve the soil fertility. This is a picture of a cartoon that is published in 1926 by Carl Arnold, a visionary cartoon that is showing everyone in the street is carrying a mobile phone. Now in the right side here, we are in the reality where everyone is carrying a smartphone in their hand. This is the in the left side, this is the first image of a first mobile phone that was demonstrated in 1973 by Martin Cooper by the company Motorola. Nowadays, smartphone has been penetrated worldwide, as we can see from this figure 2. In 2024, there are 7,074 billions of smartphone users in the world, and India is the second country that contains 492.78 millions of smartphone users. Keeping the mind of the importance of smartphone, we have used smartphone as a sensing tool for estimation of pH level in soil. Here in this work, I will only discuss the instrumentation part. I will be not discussing the chemical part. So if anyone is interested for the chemical protocol, they can refer to this paper. So in the design of this smartphone-based sensing tool, the detection principle that is used, that basically it is a interaction of electromagnetic spectrum and the matter. That is when we incident a light beam and it will pass through a sample, then the white light passing through a prism or any dispersive medium will get dispersed. And if we collect the dispersed spectrum passing through a sample, we can have the information about the absorption wavelength. This principle has been used to design this setup. So here we can see that this is a schematic diagram of this setup. Here is white light has been incident on this sample. This white LED has been powered through this smartphone by using a OTG cable. The light from the white light is allowed to fall on a plano convex lens. This will create a parallel light beam which will be falling on this sample, which is placed in a cuvette. Then the transmitted modulated light beam is allowed to fall on a cylindrical lens. The use of this cylindrical lens is basically to create a line beam, which will the line beam is allowed to create on a grating element, and the grating element will disperse the light beam, which is focused on the dispersed spectrum will be focused by the smartphone camera. So here in the photo image, the dispersed spectrum has been shown. So this is the photo image of the design setup. All the components, optical components, has been organized in a 3D printed cradle. So these are basically 3D printed compartments, and all are assembled in this. All the optical components are assembled in this compartment. Now, to basically the grating elements are the commercial grating elements are high in cost. So to cut the cost, we have used a DVD as a grating element. As we all know, DVDs are basically line spacing. So if we cut a small piece of DVD, it can act like a dispersive element. Here, this is the SAM image of the DVD in figure 4, and from this SAM image, we have calculated the track pitch of the DVD, that is found to be 0.74 micrometer or 1351 lines per mm. So clearly, we can use DVD as a grating element. Now, to analyze the data, first we need to calibrate the device, because in the smartphone camera we can have the information in pixels. Now we need to convert it to wavelength. So this is how we can convert the pixel to wavelength. For conversion, we have used two laser sources. One is green and one is red. These laser sources, the wavelength of these laser sources have been already known. Now these known laser sources, known wavelength laser sources have been the green intensity pixel spectrum has been extracted from these laser sources by using a spectrometer, standard spectrometer. And here we can see that the gray pixel intensity and the wavelength intensity, the spectrum gives us the relation and also the pixel information. Now we can correlate this pixel and wavelength information by putting wavelength in y-axis and pixel in x-axis. And here we can see that there is a linear variation of pixels and wavelength. And from this linear fitted graph, we can obtain the wavelength and pixel conversion equation. That is, wavelength is equal to 0.221 pixel plus 370.49.
Sorry to interrupt, Priyanka. You have
Yes.
1 minute left.
Sorry?
Yeah, please go ahead. You have 1 minute, 1 more minute left.
Okay. Sure. So this is the design smartphone sensor data. As we can see that as the pH level of the sensing system has been increasing, the transmission intensity has been decreasing. And this data is correlating with the standard spectrophotometer data. As the pH level is increasing, in the standard spectrophotometer also the transmission is decreasing. At this peak intensity, if we plot the normalized transmission data with the pH, we can see a linear fitted curve, which gives us the relation between the pH level and the normalized transmission intensity. So if we capture the normalized intensity data of an unknown sample by putting in this equation, we can obtain the pH level of the unknown sample. And here is the pH 5 sample. As we can see, there are not much variation in the sampling data. Another work is we can use is colorimetric based sensing for detection and quantification of phosphate in water and soil. Basically, this work is based on the working principle of color model, that is HSV color model. Here we have used HSV color model because this is more intuitive to human eyes. Basically, B is the brightness of the color, that is how bright the color is. We can know by the value component of the HSV color model. Here some phosphate samples has been used. As we can see, as the phosphate in the sample is increasing, the color of the samples has been increasing, and by taking the photo image in this sensing setup, so basically the sensing setup consists of a USB powered LED, which has been powered from the USB OTC cable of the smartphone battery, and the light from the LED is allowed to fall on a plano-convex lens. This will allow the light to make it parallel, and it will fall on the diffuser placed in this in front of the sample. This diffuser is basically is used to avoid the bright exposure of light into the sample. So the diffuse light is allowed to fall on the cuvette, and from the cuvette, the image of this cuvette has been captured in the by the camera of the smartphone. So basically two apps has been used to analyze the data. One is STAN-XY and another one is RGB color detector. So STAN-XY is used to calculate the variation of V parameter and the concentration of the sample. So in the app, if we plot the concentrated concentration of the samples and the value that has been calculated from the samples, if we plot it, then we can get a linear fitted graph, and from this linear fitted graph we can have the linear calibrated equation. And after getting the calibrated equation, if we put a soil sample,
I would like to request Priyanka to kindly put your concluding remark, because we are running out of time.
Basically, this is the flow chart of the smartphone applications. So here, as the phosphate samples, phosphate in the samples is increasing, we can see that absorbance is increasing. So at this 80 nanometer wavelength, we can correlate the V channel value and the phosphate concentration. So here, this is the calibration equation. Here, if we put the value component of an unknown sample, we can get the phosphate concentration of the unknown soil sample. So to conclude my presentation, I can say that smartphone cameras can be widely used to quantify various agricultural soil parameters. The usability of the smartphone can be demonstrated by using it as a detector, and also smartphone can be used as a computational devices for sensing investigation. Not only soil, but also there are other parameters related to water and also plant that can be investigated by using the smartphone camera and also the computational power of smartphone. There are some other works that shows the smartphone can be used to detect the nitrate level in water and soil, and also the chlorophyll content of tea leaves. I would like to acknowledge my PhD supervisor, Dr. Professor Pavitra Nath, to giving me the opportunity to do my PhD work under his guidance. And I would also like to thank the organizers of this conference to giving me the opportunity to showcase my research, and also the audience for your kind attention. Thank you.
Thank you so much, Priyanka, for your wonderful presentation. And I believe that this must be the best use of smartphone, what we can do for the agriculture purposes. Yeah. So moving on to the next, we have Rosmi Bhattarai. Before that, I would like to remind all the participants that we have 8 minutes for your presentation and 2 minutes for Q&A session. So we are like running sort of time. We will see if there are any questions on the Priyanka's presentation. So can you can please put forward your questions. Okay, fine. So I think there are no questions from the audience. So we will move forward and we'll listen to Rosmi Bhattarai's talk. Rosmi, you may kindly proceed.
Hello, good afternoon all. I'm myself, Rashmi Bautakur, from Assam, Downtown University, Guwahati, Assam. We work together with Dr. Nayan Talukdar in Assam Downtown University, and our work now today I am going to present on the study of trace elements present in natural quartz. At the very beginning, I want to introduce our work first with the sample that we used in our work and the technique that were adopted in our work. The quartz mineral sample which we had collected from the 4 parts of a northeast region in India. This quartz mineral is, everybody knows that it's a pure silicate mineral with chemical formula SiO4. It is, though it is pure stable mineral on the earth crust available in all three types of rocks, but it is found that due to some atmospheric changes, external, both in external and internal, that is in change of pressure and temperature, as well as some chemical processes during formation, a small amount of impurities are present in the collected samples. And the structure of the quartz mineral is shown in the diagram. It is found that the silicon in a tetrahedral structure at the center of the tetrahedral structure, tetrahedral, where the 4 ions are located at the corners of the tetrahedral. Each tetrahedral is joined to the neighboring tetrahedrals in a 3-dimensional structure, and this silicon oxygen bond of the silicate minerals is though very strong, but due to these atmospheric changes of pressure and temperature mainly, and due to some chemical processes, some impurities are found in the crystal lattice. Now, in our work, we adopted infrared spectroscopic method, which is widely recognized tool for characteristic study of quartz, as well as the associated trace elements. In infrared characteristic studies, we must get 4 characteristic peaks in quartz in the tetrahedral structure, and this frequency corresponding to this peaks obtained in the infrared spectra is near 778, 695, 1080, and 464 centimeter Weinberg. And they are classified as Nu1, Nu2, Nu3, Nu4. And when the mineral material absorbs infrared radiation, the oscillation of the minerals, vibrational motion of the mineral changes, and when the frequency of the chemical mineral is equal to the frequency of the infrared radiation, they absorb electromagnetic radiation, and the peaks are obtained in the spectra. And it is found that the peak near 778 centimeter is almost found in all silicates minerals, but the peak near 695 centimeter in that, which is due to the symmetrical change of bond angles, is only the diagnostic peaks for quartz mineral, crystallized mineral. And other 2 peaks observed near 464 and 1080 is due to the asymmetrical stretching vibration as well as asymmetrical bending vibration. In stretching vibration, there is a change of bond length when the mineral absorbs the electromagnetic radiation. The basic objective of our work is first is to investigate the natural quartz of Northeast India, and after taking the quartz minerals, we determine that any other trace elements present in the samples, and these are analysis by using the infrared spectroscopic method and taking the OH region, that is in between the 3700 centimeter inverse to 3300 centimeter inverse of the infrared spectra. This region is very good absorber of infrared light. The methodology that are adopted during our work is, first, we collected the samples from 4 sites of Northeast India. That is, first is the central part of Nagaon district. Second is the northern part of Karbi Anglong Hill district. Southern parts of Arunachal Pradesh and Khasi and Jaintia hills of Meghalaya. After collecting the samples, these samples are cut into small pieces and then cleaned and then grinded thoroughly in a mortar. And after grinded, and this grindation again mixed with the potassium bromide to get the good spectra. This proper potassium bromide is used as a catalyst in these preparations. Then after taking these samples in a desiccator for creating a small samples, these are then loaded into infrared spectrophotometer for analyzing the spectra. After taking out, then we analyze the spectra, and using the available literature, we find out the trace elements found in the samples of the which are collected only from the northeast region of India. Now we have got the results of all samples. Here we have highlighted only the FTIR spectra only for 3 samples, but we have collected more than 10 samples, and we have summarized the results in the next slide in a tabular form due to lack of time and space. Here the characteristic peaks are found near 464, 695, 778 and 1080 centimeter inverse in all samples, and this intensity is measured in the percent transmission that are obtained from the spectrophotometer. Here and the other samples, it is seen that all the characteristics peaks are found, and thus these samples we can confirm that these are all quartz minerals collected only from the northeast region. But the peaks, absorption peaks within the range OH region, these peaks are slightly different in each samples because due to the present in the trace elements of different types. And now we are highlighting the results of all samples in a tabular form. In the first column of the table, we have shown that the sample numbers from S1 to Sn, and in the next column we have shown the range of the peak position, and in the third column we have exact peak position from the infrared spectra in the samples, and in the fourth column we, using the available literature, we assign the trace elements present after taking the peak position from the infrared spectra. The reference we have.
Ma'am,
yes.
Can you? Yeah, ma'am. Sorry to interrupt. You have 1 more minute to complete.
Okay, I will finish. These are the references we have used. Now we have come to our conclusion briefly of the work. The number 1 is the associate trace elements in 9 samples were determined from OH region between 3400 to 3750 centimeter inverse of the iris spectra, and with the help of available literature. And the assigned elements are found as sodium, potassium, lithium, aluminum, copper, silver, boron, and hydrogen. And out of this aluminum, potassium, and sodiums are the dominant trace elements, as these are found in almost all samples. And this aluminum is considered as the most important trace elements, as it can be used to differentiate between different types of quartz minerals. And finally, after assigning the elements, we group the elements into chemical groups, and it is found that most of the trace elements are metal and alkali group of elements. And finally, we can say that these elements are very much useful in agricultural geology and mining. In agriculture, some plants require for their growth of these trace elements, and in geology and mining in ore deposit for separation as well as for procession, these trace elements of quartz are widely used. This is the references we have taken in our work, and thus we concluded my presentation, and thank you. Any question? If you can ask me.
Thank you so much for your wonderful presentation, ma'am. It was a very nice presentation. Ma'am, I have one question. Like you have taken samples from various states like Assam, Meghalaya, or Arunachal Pradesh.
Yes.
I would like to ask one question. Like, is there any difference between the trace elements present in the quartz that is available in the Meghalaya and in Arunachal Pradesh? Were there any geographical variation? Because of this
Yes, the
geographical
trace
variation?
elements are different, but as we have collected as a whole, therefore, due to the geographical location, we cannot differentiate at present, but there must be some different trace elements at the different geological positions. We have collected only in the random way, not only in a particular GIS position.
Okay, thank you, ma'am. Thank you so much. So I would like to see if there are any questions from the participants. So I see there are no questions. So I would like to thank the speaker, ma'am, once again. Thank you so much, ma'am, for your wonderful presentation. Moving on to next, we have Prof. Sharma from Cotton University, and he will be presenting on the topic bamboo-derived biochar as an efficient sorbent carbon nanomaterial for organic water contaminants. So I would like to request Prof. Sharma to kindly take your time.
Yes, ma'am. Okay. Ma'am, can you, I am unable to share my screen. Hello?
Yeah, we can see your screen, but you're again disconnected. Can you share your screen again?
Okay. Let me try once again. Is it visible, sir?
It's not yet.
Okay.
It was visible before, but now, okay. Okay, yes. Yeah. Just go to the presentation. Full screen.
Is it visible, sir, now?
Yes, it's visible now. You can, yes.
Thank you,
Yes.
sir.
Please proceed.
Good afternoon, Chairperson, ma'am. Good afternoon, everyone. At first, I would like to thank the organizing committee of this national conference for giving me the opportunity to present my research. I am Prof. Sharma, a research scholar in the Department of Physics, Cotton University, under the supervision of Dr. Midula Baruah. My presentation is about the absorption of methylene blue dye by bamboo hydrochar. These are the outlines of my presentation. So, dye contamination impacts. So, what is dye? Dye is a very harmful contaminant that are widely used in plastic, cosmetic, and textile industries. It has some adverse impacts in our environment. It reduces the light penetration and disturbs the aquatic ecosystems. Besides that, it has also some adverse impact in human health. It causes skin irritation, allergies, and even cancer also. Some common examples of dyes are methylene blue, crystal violet, and methyl orange. These are some properties and applications of biochar. First one is high surface area. The porous structure of biochar provides the larger surface area. abundant functional groups. Oxygen containing functional group on biochar and hence its chemical interactions with dimolecules. Biochar is eco-friendly also. Next one is environmental stability. Biochar is resistant to degradation, making it a very long-lasting solution for dye removal. So on the application part, we have used biochar as a adsorbent for methylene blue contaminant. It has also some applications in carbon dioxide capture, catalyst, and energy storage systems like supercapacitors. So bamboo hydrochar. So bamboo carbon, which is synthesized by hydrothermal treatment in our lab. So it can be termed as hydrochar. It has a porous structure and abundant functional groups, which make it as a good absorbent. These are some steps of hydrochar synthesis. First, we collect the bamboo feedstock from village area, wash it properly and grind it to prepare fine bamboo powder. We take few grams of bamboo powder mixed with zinc chloride in high temperature and pressure in a hydrothermal autoclave. After the filtration and the drying process, we obtain bamboo hydrochar with very high surface area. Result and discussions. The first image shows the XRD pattern of raw bamboo, which has peaks at 1622 degree, indicating its crystalline cellulose phase. The second image shows the XRD pattern of bamboo hydrochar with a growth peak around 22 degree. It suggests the amorphous carbon structure of bamboo hydrochar. Any absence of sharp peaks indicates the complete conversion of crystalline to amorphous phase. These are the surface electron microscope images at different magnifications. Clearly we can see the porous structure of bamboo hydrochar, which is good for adsorption and catalysis. And one important point is that during the carbonization process, the hierarchical structure of bamboo is preserved. This is the index spectrum of our hydrochar. Carbon, oxygen, nitrogen can be seen in index spectrum with different weight percentage. We have tested our hydrochar for adsorption of methylene blue. For that purpose, 5 different tubes are prepared, each with 10 ml methylene blue solution. 5 milligram of hydrochar is mixed with each of the methylene blue solution tubes. The total contact time between methylene blue and the hydrochar were taken as 7, 12, 18, 24 and 31 minutes. After that, each sample is filtered such that hydrochar is completely separated, and the remaining methylene blue solution was taken for absorbance measurement using a UV visible spectrometer. Clearly, we can see the absorbance of methylene blue is decreasing in different time frames. From the Beer-Lambert law, we can say that the concentration of methylene blue is decreased with increasing contact time. So our bamboo hydrochar is
Parthapatim, a gentle reminder, kindly complete your talk within 1 minute.
Just 1 minute. So our bamboo hydrosar absorb the methylene blue from the sample. So these are some conclusive remarks. Due to high porosity of bamboo hydrosar, methylene blue is almost absorbed in a very short time frame. Hierarchical structure of bamboo carbon makes it a good absorbent material. Optimizing the synthesis process of bamboo hydrosar, other researchers optimizing the synthesis process of bamboo hydrosar may help the other researcher in future prospects. These are the reference of my research. Acknowledgement. I am deeply grateful to my supervisor, Dr. Midula Boro, whose expertise, insightful comments, and encouragement were invaluable throughout the research process. I would also thank Kotor University for their financial support. Special thanks to MSc student Hakon Gairi Nikhil Ranjan Nath at Department of Physics, who provided me assistance in this work. Finally, I extend my acknowledgement to NECBH, IIT Guwahati, and Optulab in Department of Physics, Cotton University for characterization of my research work. So thank you everyone for listening me.
Thank you, Parthapatim, for your nice talk. Since we are running out of time, so we will not be taking any questions now. So if there are any questions, kindly contact Parthapatim directly. His email ID will be shared in the group later. So moving on to the next speaker, we have Jamuna Majumdar from the Guwahati University. She will be speaking on the topic investigating the antimicrobial effectiveness of polypropyl silver nanocomposites against some harmful human pathogen bacteria. So I would like to request Jamuna to kindly take your time.
Yes, ma'am. Am I audible?
Yeah, you are audible. Kindly share your slides.
Okay, ma'am, I am sharing.
Jamuna, please unmute yourself and share your slides.
There's a small announcement. So after the session, after Jamuna Majumdar's talk, we will be moving to the plenary's talk by Professor Debajyoti, and then the remaining two talks by Jyoti Ocha and Fumila Brahma will be rescheduled after the talk by Pranjal Pratim Gogoi. Okay, that is okay. So after Jamuna Majumdar's presentation, we will move to the next speaker's talk. Thank you.
Thank you, sir. Is this visible?
Yes, it is visible.
Okay. Thank you. Myself, Jamuna Majumdar. I am currently working under the supervision of Dr. Sulochana Dev, Guwahati University, Assam. Today, I am going to present my talk, and topic of my talk is investigating the antimicrobial effectiveness of polypyrrole silver nanocomposites against some harmful human pathogenic bacteria. These are the outlines of my talk. Coming to the introduction part, polymers are one of the most used material in modern world due to its insulating nature. It can used from making container to clothing. But the view has changed after McDiarmid, Ellen G. Hickard, and Hideki Shirakawa in 1976 discovered conducting polymer. Conducting polymer are those materials that can conduct electricity. Apart from polymers, the main conditions for conduction in conducting polymer are they should have conjugated double bond and polymer system has to be disturbed. The properties of polymers can be enhanced by forming nanocomposite with other noble metal like silver. In this study, antimicrobial effectiveness of polypyrrole and silver nanocomposite have been studied. The conducting polymer, mainly polypyrrole with positive charge, binds to the negatively charged bacterial membrane, due to which it can show antibacterial activity. Also, silver are highly effective as antibacterial agent. So the combined effect of polypyrrole and silver have been taken as an antimicrobial agent under study. To study the activity, there are mainly two human pathogenic bacteria is taken. One is Escherichia coli and other one is Bacillus tropicus. To study the experiment, in vitro agar well diffusion techniques have been adopted. This is the experimental details. The materials used for the preparation of the nanocomposite. To prepare the polypyrrole silver nanocomposite, a simple interfacial polymerization method have been adopted. In this method, a interfacial layer is formed between two immiscible phases. One is a organic phase and another one is aqueous phase. And the interfacial layer is nothing but our polypyrrole silver nanocomposite, which is dried and taken for further characterization. These are the characterization techniques. Result and discussion part. From the to study the morphology of the nanocomposite, FESEM field emission scanning electron microscopy technique have been adopted, and these are the micrographs. First one is for bare polypyrrole and second and third one is for nanocomposite. Here in second one, this one is for polypyrrole with 30 millimolar silver concentration, and third one is polypyrrole with 50 millimolar of silver concentration. In all the micrographs, we can observe that the nanocomposites shape of the nanocomposite is spherical, and also size reduces as we go from bare to nano. Also, we can calculate the size. It is around 400 to 600 nanometer. And also density increases if we go or increase the concentration of silver in the nanocomposite. Also, to confirm the presence of silver in the nanocomposite, EDS spectra is taken. From this elemental analysis, we can confirm that there are almost equal amount of silver present in the nanocomposite as we used during the preparation time. So to study the optical characteristics, UV visible absorption spectroscopy is taken, and we can see there is a peak around 230 nanometer. This suggests due to pi to pi star transition band of polypyrrole being present in the nanocomposite. But here we cannot observe any SPR peak, maybe due to the core cell structure formation of the nanocomposite. To study the phase present in the nanocomposite structural analysis, XRD pattern is taken. From XRD pattern, it is confirmed that this one is for polypyrrole and red and blue one is for nanocomposite. So from the polypyrrole, there is an board peak around 26 degree, which is attributed to the amorphous nature of polypyrrole. Along with polypyrrole, there are some other peaks. Other peaks at around 27 degree, 32 degree, 38, 46, and 76 degree. This may be attributed to the due to the diffraction from planes 226, 264, 111, 200, and 311. 311 planes of FCC structure of silver. So, XRD pattern confirms the formation of silver along with polypyrrole. Coming to the main part, antibacterial effective study part, here we have taken in vitro agar well diffusion techniques. These are two plates for two bacteria. First one is for Bacillus tropicus and second one is for Escherichia coli. In this method, agar medium is prepared in a plate, and on this plate some wells are made, and bacteria is allowed to spread on that plates. On these wells, our solution, that is silver, polypyrrole silver nanocomposite solution, is put, and all the systems is incubated for 24 hours at 37 degrees centigrade. And where bacteria is allowed to grow. After 24 hours, the scenario is like this. We can clearly see that there are some regions around these wells. These clear regions are known as zone of inhibition. That means in these zones, the bacteria cannot grow. That means our samples act as an antibacterial agent. The effect is for polypidal also, and also for polypidal silver nanocomposites. This is also zone of inhibition can be visible from these histograms also. We can see from the figure that antibacterial activity is higher when composite is formed than the bare polypidal. Interestingly, polypidal silver act as an antibacterial agent for both gram-positive as well as gram-negative bacteria. Since gram-positive is more difficult to penetrate, but our samples do the activity for this bacteria also. And
A
zone of
gentle reminder,
okay, ma'am.
for your time is almost up.
Okay, ma'am. Zone of inhibition increases with silver and can be calculated from this table. From this table, you can clearly see that the zone of inhibition increases with the increase of concentration of silver respectively. Conclusions, we have successfully synthesized polypidal silver nanocomposites, and it shows a strong antibacterial activity. Incorporation of silver improves the antibacterial activity of polypidal. Also, concentration of silver here presents the most relevant parameter for the antibacterial effect. The main mechanism of antibacterial activity is the electrostatic interaction between the bacterial cell and the nanocomposite. So the entire study can lead to the development of highly effective antibiotic that can protect human from microbial attack. This is all about, ma'am. Thank you for your kind attention.
Thank you, Jamuna Mazumdar, for your wonderful presentations on the antibacterial
Thank you, ma'am.
effectiveness on this topic. So we will see whether there are any questions. We will quickly see from the audience. So if there are no questions, I would like to thank once again Mazumdar for your nice presentation.
Thank you.
And I'd like to thank the Physics Department, Bhawanipur Anchalik College, for giving me to chair this session. Thank you so much, organizer, and congratulations for organizing such a wonderful and informative session. Over to you, Dr. Thapa.
So thank you so much, Madam, Dr. Bhattarai, Madam, for your time and being with us today in this session. So thanks a lot, Madam.
Thank you, sir.
So moving forward to our next session, session number 3. So for this session, it's time for a plenary talk, which will be delivered by Professor Jiban from Gautam University. So I welcome you, Professor Das, sir, for your time and accepting our invitation. Hello, sir. Are you there? Hello, Professor Das, sir. Are you there?
Sir, excuse me, sir.
Yes.
Myself, Sikha. I have a confusion regarding the my presentation. In the beginning of the
Yes.
session, it was mentioned that we will be delivering our presentation just at the end of the last speaker. So
Yes, so actually the thing was that so because we are running late and the plenary speaker was waiting, so we reschedule yours and Femina Brahmos presentation just after the plenary speaker talk. Actually, that was the Professor Das, are you there? Yes, so yes, sir, you are not audible. You have to unmute yourself. Just you have to unmute it from your end.
So kindly unmute your mic and yes,
Yeah,
yes,
okay.
Yes.
Now you are
Yes.
audible.
Okay. So I don't see the share button.
Yes, you have to share the.
Maybe
the slides?
No, I am not seeing the share button here. Screen share button is gone actually. It was there. Maybe the previous speaker has to take out. Is it
Actually,
somebody's
sir,
speaking?
the previous speaker has already withdrawn the shares in
Yeah,
the screen.
I don't see the I don't see the share screen button here. It was there previously.
Okay. So yeah.
To me, share to me.
Okay, then let's do one thing. Then let me share the screen.
Okay.
And then you can just it will be a bit difficult, but okay,
Yeah,
let me
actually, I
share
don't
this.
know why the button is it was there. Share screen. Let me.
Okay, so can everyone see my screen? I guess it's
Okay,
yes.
now I see the share screen. Okay. Now
Yes,
I
okay,
am seeing.
so
Yeah, let me
yes,
upload it.
yes, please can just speak and then let me know
Okay,
whenever.
yeah,
Okay.
can you see my screen now? Share
Yes.
screen. Okay.
This is the screen that I have shared, so you can just speak. I can and just let me know, and then I'll change it
You
accordingly.
cannot share screen while other participant is sharing. That is the comment I am getting. Maybe you have to disable your share.
Yes, let me just Now can you share your screen?
Okay, let me try. Yeah, that is the command coming in. I don't know, it is not okay. Share screen.
Yes, we can see your screen. Just go to the PowerPoint presentation and then it's
okay.
Yes.
Can you see the screen? Yeah.
Yes, we can see your screen, sir.
Okay, I'll just make it
Before moving forward, I'd like to request our convener sir to kindly introduce our plenary speaker to the audience. Convener sir, over to you.
Yes, yes. So thank you so much, Professor Das sir, for being with us today. So Professor Jiban Das has received his PhD degree from Delhi University in the year 2008. So he has also served as scientist C, D, and E from Nuclear Science Center, New Delhi, where he has received Best Scientist Award in 2003. He has also served as visiting scientist, Joint Institute of Heavy Iron Research, Oak Ridge National Laboratory, USA. He has got the postdoctoral research fellowship from UNIRIB Center of Excellence for Stewardship Science in Radioactive Ion Beam Studies, Oak Ridge National Laboratory, USA. During his staying at USA, he has run different research projects related to nuclear physics and particle accelerator. So till 2021, Professor Das has 54 research publications in different prestigious journals. So presently, Professor Das is working as a professor in the Department of Physics at Cotton University, Assam. So, so over to you, sir.
Thank you. Yeah, thank you very much to the organizers, and also I really appreciate giving me this opportunity. I am also actually very happy to see our young stars are organizing this workshop in such a nice way. Uh, our students are always bright, and I'm going to show some work done by them. But again, to start with, this itself shows the capability of our students. So the first thing, of course, the name of the workshop. I am essentially today, of course, going to talk. This northeastern region of India doesn't have an accelerator, and so this is a very fundamental tool of modern research for discovery. And you can see like there are 25 Nobel Prize in physics and 24 in chemistry using accelerators. All the new elements are discovered using accelerator and so many other things. It also has applications. India also has so many accelerators, but at the same, somehow our northeastern region is not got any, and that is what we are trying to develop in this region. So anyway, but I think it really, my talk, really, I'm really happy that this topic is the bridging theory and experiments. So this is what I'm I think I'll try to do justice to this workshop, that how do we bridge theory with experiment. I will show some of the latest theories which we are trying to do already at our place. But the bridge is essentially for the subatomic world, the bridge is accelerator. This is the bridge which lets you, theory is very unclear at this level. You need a lot of experimental data, and to explore this, like to say you see a microscope, you see small molecules or whatever you are trying to see. Similarly, these accelerators allow us to see the much smaller level, at a very minute level inside the nucleus, or the very subatomic level, and what is happening. And if we see them and we see their properties, then we can understand. Many basic questions are still unanswered. And so this device is essentially the, for this workshop, I would say that this is this accelerator. And so these are very sophisticated machines. So, and then it needs a lot of training and understanding to do research using such machines. And then I will try to see what we are trying to do. Even if once we get the accelerator, even working with the accelerator needs enormous amount of trained and skilled youngsters. So we are fortunately, I am from this region and I have happened to work all my life in accelerators. So I am trying to just now, one of the prime motivation is try to pass what I have learned to our new generation. And so whatever I am going to talk today is essentially what is done by our PhD students. They're still doing, because only 3 years the first student is completing, and then our PhD students as well as our dissertation students, what kind of work they are doing and how we are trying to carry this mission forward. So we essentially want to build an accelerator, and that is, I would say, is the breeze that this workshop is telling in this subatomic domain. Of course, we have a very large collaboration because the accelerator is a very huge project, and typically our papers will have 2 pages of names. So you can see how many people are working here. And this, of course, is entirely for the northeastern region. The whole region we're taking as the 7 sisters, and this each of these sisters is a part of this. So we are trying to work together so that our children, for future, they get their sons to truly develop their potential, because these accelerators are discovery class accelerators. And already I will show what our students are achieving. We can say our region may be backward, but our students are not backward. They are as good as anybody else in the world or in this country. And that is what I will try to show from the results which I show today. This work is entirely done by the students. Even the slides were made by them because they should know what to make, how to present their work. I should do some correction, but even everything is done by the students, and that's what I am going to show now. So, and I see that our future is in right hand, including this workshop that is organized by these youngsters, shows the capability of our younger generation. And I'm very happy about that. So we got that started is called the IQAC, Cotton University Particle Accelerator Center and Northeast. This is a collaboration we have formed to jointly work for our region. And we want to develop an accelerator. And for the first accelerator for the region, we are working whatever way. This is our dream and trying to fulfill it. And so, but in the meantime, what else we are doing with this for the accelerator, we will show and say our basic research, each of this field is actually, we can say, the first in India. Whatever we are doing in these specific domains, it is not done in India. Because we are proposing an accelerator, which is again not there in India. And so this will be nation's first of its kind. And also it will do research. This, of course, we are already, this research items, we are already working on these things. I'll show the results. These are the type of part of my results. So, and these are all done by our students. This is PINS, is the positive ion mass spectrometry. It is the latest technology in the carbon dating. One of the way to think about is the okay. So this is the it is not there in India. It is first thing has come out the day I have joined Cotton actually. So it is a patented product. So we have entirely developed. Our student has entirely developed it from the scratch. We don't know it's a patent. Nothing is known inside this, but nothing is known about this. But what we think it should work. So we have made from the first principle basis. So this development is now complete. We have just started testing it, and DAE has given us a project because they understood that what we are trying to do, even if it is not known. So similarly, this is ADB entity, accelerator-driven boron-neutron capture therapy. This is the latest form of cancer therapy. In a normal cancer, what happens is that treatment, the radiation, it treats the cancer, also kills normal cells. So this is a new form of cancer therapy, the latest in the world. Again, this can only kill the cancer cells, sparing the normal tissues. It can also say they have cancer. So if the radiation is high radiation is put, it can kill the all brain as well as the eyes maybe. If it is near the other side of the head, the radiation will go through. It does not distinguish between normal and cancer cells. But this is a technology. So those cancers are not treatable now. So this is the latest technology which can deal such cancers. And similarly, the nuclear astrophysics, we have, so these are our focus, and this is again, India is very new to nuclear astrophysics. It is a very advanced instrumentation. So we'll show what we are doing here and what we are doing for this nation. And of course, fifth heavy-handed materials, this is reasonably done, that accelerator-induced material science. So this is our core research, and I will just going to show what we are doing here. But our fundamental aim is that we want our future generation to train them in these technologies so that if and when the accelerator comes, they can actually take up this research in a full-fledged way. So this developing the manpower is the slowest step in this whole process of accelerator. So I will show, I mean, I'm very proud of our students actually. So how we are progressing with that. I think it is a 4 years we have put on this, and now we can claim little success, I would say. Of course, for you to judge it is a success or not, but at least I will show their results and you can judge. So we say that Cotton, of course, it is for the entire northeastern region, but Cotton, we say they will get the brightest of all students from the state. This year there are 6 students with a qualified grade, the highest number in a single year from Cotton. So we are teaching them that way. They are capable actually, and our aim is to harness their potential. And the way we are working right now is that we give a dissertation project to a student in one of these topics. Whatever we do, it is a part of our future. So they will choose a topic for them, and then they do their dissertation, and almost all of them so far is continuing their PhD in the same topic. So, and our dissertation students will teach some of the technologies that is required as an accelerator center, accelerator physics, or even modern, very high precision physics, because we actually want to develop the instrumentation, everything. So they learn CAD, they of course learn Excel in the part of their dissertation, vacuum systems, detector, etc. But once they go to the next level, they do these advanced topics, how an accelerator works, how the detector will be actually designed and simulated. These are gas targets. These are all first in India actually. First time we have done such things in India. And then of course we do the simulations and everything here. And then we would send them to the national labs, India University Accelerator Center at Delhi, or UGCD CSR Kolkata, or Bhabha Atomic Research Center. So where, of course, we are working for them. Some of these models they cannot develop actually, which our students did. So those things, of course, will be used there. I will show the results, and then that will be that's how they get their hands-on experience, and also our research is progressing. And then this is, I'm going to show essentially our students' work. Of course, I don't want, I have already talked about it. This is the entire northeastern region. So every dot you see, we have Sikkim, we are still not having a member, we are looking for that. Every state has a, I have shown in the first slide also, that they are all part of these different research projects they are trying to do. So our first thing I'm going to talk about is PIMS. This is the positive mass spectroscopy. This is the latest mass spectroscopy technique in the world. And as I said, this is a patented technique. And we have almost going to work on the, finish working on this. So, and we are going to test it very soon. Okay. So you can see there. So this is actually a technique where in the conventional mass spectrometry, they use an accelerator with a negative ion beam coming in and then make it positive ion. But this is latest technology is very different. It is a positive ion that comes in and it is very negative ion with a gas cell. It's supposed to have some very major advantages in terms of results, but I don't want to go into that. But this is the latest technology, and this is the world. If it comes to us, this project will be world's second, actually, and India's first. But anyway, so this is the patented part of the technology which we thought should work. So, but I don't want to go to the detail, but you can see all these designs and drawings. CAD drawing is first made, and then this is actually made. All these are done by our student. The student who has done his dissertation and working for PhD or visit. So you can see that everything, all this, you see, this is the model of this CAD model, because everything here we have to make with high precision. It has to work exactly the way we think. And so this is this you see here, this is that is made. So every model, this is the model you see here, and this is the thing we have made. So, and this has to be all done with high precision and accuracy. And so this chamber is made, and this cell is inside the chamber. So we first design everything, the student design, then we get it mixed in workshop, and then the assemble and testing goes on. So you can see the full setup here. So this is our, and this is India's first windowless gas cell. We have developed for PIMS, and we are now, you can see this is a complete test setup, the way we have tested it. So we can say we don't do theory, we verify the theory with experiments. And we means these are our students. These are the younger generation for our future. And so they can do such precision machining, starting from the very basic physics principle to actually designing the instrument, making it together, assembling it and testing it. So this is the whole cycle we want to generate our new, these are called accelerator pieces from our state. And so this is a, I don't want to go to again. So these are the design simulation that we should perform. So let us say think like that, but this is a little specialized thing. And of course, this is the results that agree with our design. So this is our, let us say that India's first windowless gas cell. It has very many applications. So I will show something else also right now. Okay. So this is our, an entirely done by student. Similarly, we also want to enhance the skills of the student. Some very high-tech electronics, nuclear physics, nuclear accelerator is very high-tech electronics. We need hands-on training. So I'm just showing here. This is our. This is a very high-density electronics. You can see these things. This is a preamplifier which is used in nuclear signal processing because signals are very weak. You have to amplify it many times. And so, and these electrons are very high density. You can see you can see the finger probably in one of the things, and you see that this is a finger and this is the electronics. So these are all assembled, soldered, and put together by our students. And they made 3P amplifiers, and similarly they made CAD drawings for the mount of a detector. These things are like $1,500 a piece. These things if you buy, and this we have got 3 of them. These 3 students made in 2 weeks in the summer. So this is a new generation of our youngsters who can develop this high-density, sophisticated electronics. And this thing was tested at IQAC, and it was shown to work as good as the imported one from EGNG or Tech at US. So that is, so we are also trying to import substitute, you can say. So those things, we don't want to spend money in buying something $1,500 a piece, and you need probably in a modern experiment you need 100 of them. So that kind of thing, we can, our students now, they can, if our accelerator comes, they can develop those things. We don't have to import them, and these things are working as good as the imported. The next thing I am showing is the heart of our machine is the accelerator optics, how the accelerator works. This is again, the entire work is done by Rasna. She is working with us, again, one of the brightest students we have. And then working on these things. We are so fortunate actually, we get the best students, they are very motivated. I always tell them, this is your accelerator if it comes. So whatever you are doing for that. And I am trying to just see whatever I know to pass you on. So you do, you work to the best of your ability. I think that motivates them. So they are very sincere, and I'm really happy about it. Anyway, so let us see that this is the accelerator, the way we are going to build it here, the way we are proposing. India doesn't have this accelerator. This is some unique advantage, but basically accelerator is something, you have a high voltage here. So high voltage, if you put a, say, you know, if you have a charge, put a potential, it will attack the negative charge, will be affected by the positive. So our positive charge will be repelled by the positive. So this is here, we put a positive 5 million volt, 5 megavolt. And then this charge, this ion source, just sit at the terminal. So this is a positive ion. When it comes up, it is positive ion. This because the voltage itself is positive here. It's 5 MeV is charged at 5. We'll get 25 MeV energy, and Q into V. So that gives the energy. And this, so that is how our accelerator is going to work. And this accelerator has a very modern ion source called electron cyclotron resonance ion source. So, and then this kind of things is not there in India. So this is the ion source here. Resonance ion source here is called super nanogun, and then that gives the ions, which will of course accelerated here. This whole thing, this sits inside the high voltage. So that positive voltage repels the positive, and it comes up with the energy. So when an accelerator gives beam with an energy, we need essentially to, of course, beams are essentially like a light, but you have to bend them or focus them to use lenses. So bendings are typically magnets. So this one you see is a magnet. It's a vertical accelerator. So beam is coming vertically. So you make it horizontal, putting a 90-degree magnet, bend 90 degree. So, but this thing all has to be designed and work exactly. This accelerator works with a micron precision. 0.1 mm the beam has to go through with a whole device like the light, and it has to go through parallelly. Otherwise, like a light coming out at divergence, it will get lost, the flux. So this has to be handled by what is called accelerator optics. So this ECR source, Rasna designed these optics that for the IUAC, the ECR source with a nanogun. And for a beam line, she has designed this, didn't have this optics done before. So this is the first optics. We have done it for the, of course, it will be used in the beam cell, and we are going to test this. So you can see that all this beam comes out with an ion, it gets accelerated. Then of course, as I said, we have to make them focusing, otherwise beam will go away divergence wise. So we use different lenses to make them see, just focus, and transport from one point to other, so the beams don't get lost. So this is like the beam coming here, it will go far away. So that is how we transport beam far away, focusing. This time, otherwise beam will be lost. We don't do like laser, the beam is parallel, so that is far more difficult. So we have to do it, but typically this is how we transport beam. And this is for this beam line at IUAC, Inter University Accelerator Center at Delhi. This is like the first time it is worked out, and it is worked out by us now. Similarly, this is another part of our accelerator is here. We don't have the accelerator yet, but we have to understand it. So we wanted to talk with Saharia Institute of Nuclear Physics. They have an accelerator, new accelerator. And then we said that let us see how do we, that accelerator, if you can reproduce, our students can reproduce the simulation. So this accelerator is for FRANA at Saharia Institute of Nuclear Physics. So this is again done by Rasna, the entire accelerator optics. Actually, in my life, I have not seen anybody in India. We have so many accelerators. A PhD student able to do this accelerator optics, how a accelerator actually works. I haven't seen it. I have given this presentation to several places. I asked this question, did anybody do? Even scientists cannot do the such things. And this shows the capabilities and motivation of our students. And these are our future. They are going to, once our accelerator comes, they know how to run it, how this works, that in our theory. So this is the entire, for this accelerator astrophysics program, this is the entire type of transport optics she has developed. And this is the beamline actually for the nuclear astrophysics beamline, it is called. So it is a very special optics like these ones. And we have actually, there will be global tendering, and Rasna is now writing the specifications. How we will buy this element, how this will work, what should the company give when we buy these. So this is again, it's a very good training for our students and our future. And finally, I come to here, nuclear astrophysics also need very special optics. You need like a laser like parallel beam. You can see here for our experiment. And that is what she has developed here. You can see this. So, and this is the entire beamline we are developing. This whole, she has worked out the whole optics from whatever you have seen up to here. So this part we are essentially designing and developing. And then we are asking now for the price of this. So this is the BRC SINP project and now DA project, but Cotton is now giving this core expertise in this. So you can see that. That's why we are very proud to say. So this is the facility will be called the BRC Cotton SINP Nuclear Astrophysics Beamline. This is India's first nuclear astrophysics, and we can say our shows the capability of our students. So that is our first thing. So next I want to talk about is the design of the beam shaping assembly. Again, I talked about accelerator-driven boron-neutron capture therapy, and so that because we are again India's first to propose this success facility, but we are also doing the R&D, so that if we have submitted a project, if it comes, we are saying that there will be a commercially one beamline will be there, one treatment facility, but a second treatment facility we will develop entirely indigenous. Everything will be made here by our students. And so that is, this is that approach. So this design is done by our student. So, but anyway, let me say this is essentially how this works. What is the latest technology? So what happens that there is a neutron beam comes here, it is a neutrons. So these are boron, this is the element boron 10. If neutron falls, it breaks up into groups like fissions into two, helium and lithium. So now these are, you see here, these are blue ones are cancer cells, green ones are cancer cells, this yellowish color is a normal cell. So you can always see that like cancers always have together normal and all cells are not cancerous. So this boron drug is given to the patient, then what happens is it has some specific chemical properties are like that, that this only absorbs the cancer cells only take the borons. Normal cells don't take. So when this neutron beam is now patient is irradiated, it breaks up these borons. That gives these particles, alpha and lithium. They kill these cancer cells. But their range is like that, so small, they just go equivalent to these two, equivalent to the diameter of the cell. So these will not go away. They will only kill this cell, but these neighboring cells will remain healthy. They will not be destroyed. There is no unnecessary destruction, but the cancer will be killed. So you can see that is in this shown. So this is the boron there, neutron beam is killed with all the cancer cells, and the normal cells survive. You can see this is what we are showing here. This is the head cancer. Say if you put normal radiation, what will happen? It is not neutrons. Right now it is gamma sources. Say the gamma will go through all the way. It will kill everything on the way till whatever distance it goes. What a proton therapy is the same thing. But this new technique I discovered, we described, in this will put neutron boron compound there. So only those cells will be killed. Neutron don't interact with any of these. So very little, well, maybe 1 in a million. 1 million of a time will be damaged, but that is negligible. So this is why this is the latest form of cancer therapy, and it's the latest discovery, you would say. And then we are the first one in India to propose this. And then, of course, so this is the accelerator we are proposing for that. And but the main point here is that these neutrons, of course, has a very specific property to treat a patient. You cannot get them from accelerator directly. You will produce with the accelerator, and then we will make a device. This is called the DSA, what Dimple has done. So, so this was entirely she developed this model, the simulations, so that if as and when our facility comes, we'll have a second beamline. This is completely indigenous. We'll make it ourselves with our own design. And so this is, you can see, this is how it is going to look like. As I said, our students know CAD drawing. They know the modeling or the physics with the Sayan 4 modeling they use. So we design everything. And then, of course, like our previous examples you see, once we get the project, it comes, we'll make it ourselves, every part, like the one you have seen. So anyway, this is the more details about that. This is how they do the simulations. You can see they are using Sayan 4. And so we have to again develop the entire expertise at Cotton for this kind of research. So now we have finally got, this is a very complicated code. I think we have finally got it running, but we are still calibrating our results, because first time when you run something, our results are true or not. We have to do a lot of calculation and compare with other data to verify that what we are doing is correct, and that step is going on. And that is why it is a very slow process to teach a student, so that they can, if they are like a walking, and baby is walking and then able to stand up and actually run. So that level takes the longest time, and I think we are in that state now. We are slowly making progress, and these are, we are also generating the young stars who will take care of our future. So these are some more detailed simulations. I don't want to go into those details. As I said, I am only talking about students' work. So this is our now neutron source strength AGB stars. Yeah, this is a prime example of this workshop, the theme of this workshop, connecting theory to experiments. So essentially, the idea is that, say, we know all the elements in the earth, so we see carbon, aluminum, how are they formed? So when a star is formed, the star is formed, these protons fuses to give deuteron, then tritium, like heavier elements are forming. So each time it captures a proton, because you know proton has got one proton, helium has got two protons. So to form heavier elements, you have to essentially capture a proton. That is the only way you can get more heavier atomic numbers. So, but what happens when a proton is forming on a proton? So it will be repelled, because when a proton comes near it, because both are positive charge, it repels. But the nuclear force is very short range. So the proton and proton to actually touch, so that the nuclear force takes over, which is charge independent, it become a state of a 2 helium, some other composite system, let us say. But to see the nuclear force, proton and proton has to be so close that the nuclear range of the nuclear force is a Fermi. They have to be within a Fermi, but there is a huge repulsion, so that essentially prevents it. So that's why we need accelerator to study. But even then, what happens? So if proton potential from heavier elements like carbon, nitrogen, oxygen, like that, it goes on. But you can show that it gets heavier, say beyond aluminum. You cannot form by proton, because this repulsion between the proton and the aluminum is so heavy that you cannot, so huge that this proton will never see the nuclear field of the aluminum. It cannot come that close. So stars also doesn't have that mass energy, because we are modeling a star. So what happens there? So this is called a neutron capsized star. So, but neutron has no charge; it has no Coulomb barrier. So aluminum 27, say, will capture a neutron; it will become aluminum 28. But then it will beta decay, will become say magnesium, aluminum, yeah, 28. This is the process. These neutrons start playing a role in forming these elements. But where does this neutron come from? And what rate they are coming from to produce the elements, like we see R 58%, whatever element percentages we know, 70% is oxygen, 8% is nitrogen, about I forgot this number, I think 20% is oxygen. Similarly, R trust has some specific ratio for different elements. Where did it come from? This all depends on how this neutron strength is there in the star. So that is, and this accelerator will create these stars on the Earth, and then we study this reaction exactly what is going on. So this reaction is one of our prime research projects. Now again, a PhD student is worked out. So it essentially to how this universe, as we believe now, how the neutrons are coming out. So that shows how many neutrons are emitted per second is the one we are trying to find out. And then we can do the modeling of the stars, saying that whether that is correct or not. So this is one of the prime focus, and that is what we are bridging this gap in theory now with an experiment. Of course, this is a very advanced experiment. I think it is one of the top 11 experiments in science that has to be done. So what we are planning to do, this whole thing, of course, I think you all know about is this HR diagram. So this is the mass of the star compared to the solar mass. One is the sun, and then the log essentially you take. And this axis is 1 upon temperature, the temperature of the star. And these are called the main sequence stars. These are called the main sequence stars. But then say all the hydrogen, the fuel here is burned up, which gives the energy of the star. It starts cooling down. So right hand side, this is 1 upon T. It becomes, T is becoming smaller, I mean this is getting bigger. So this is star, but there's nothing to happen. So the mass remains constant. The y-axis is constant, so it moves there. And that is where this is happens. These AGB stars, asymptotic giant branch. And this is where these reactions are believed to be occurring. And this is what we are trying to recreate in our lab. So this is one of our projects. This is our student Bhargav Baruah, again one of our brightest students, have done these simulations. So we have done all these calculations, so to say, the simulations that detector geometry. And then this project is funded by IQAC as a beamtime for this experiment. And then actually this experiment has a long history. This is tried. It is also being directly quantum mechanics into play actually. So what happens is in the star, neutron captures a 13 carbon captures a neutron to give 16 oxygen plus a alpha. So this experiment is you can see like A plus B going to C plus D. This Schrodinger equation is time reversal. If you take T to minus T, it can just go back in time. And that is what we are trying to use as a theory to do this experiment with neutron beam. Actual oxygen is alpha plus 13 carbon giving 16 oxygen. We are giving the reverse of this, neutron plus 16 oxygen giving 13 carbon plus alpha. It's called time reversal. This technique was actually proposed by CERN. Again, the year I joined Cotton, this experiment was done at CERN, but they failed. Because this is a very complicated experiment. And then, of course, we got into this business. We have proposed a new technique. And then finally, we were able to get a beam time. And then they are also collaborating with us through the Italian groups, which is essentially now all the Italian names you are seeing, they are joining us because they think it's a, we don't know this kind of level. We can never say that this is going to succeed. Once we do, we'll find out what are the problems. But they say your theory is at a very robust basis. The theory we propose to overcome the CERN problems to do this experiment in India. So this was funded and as I said, this is the highest priority experiment. And this is the only way we are going to, this is the bridge we are doing now. The theory is there, this experiment we do will bridge that gap. That what is the strength with this stars modeling that is actually not happening? That needs measurement. You cannot do just predict with modeling. You need data now, and that is, of course, the global priority. And we will hope we will succeed. We don't know. We don't know. At this level, we cannot say what we will get. But at least the way we are proposing to do is correct. We don't know the end result. This you have to learn by doing. And of course, I don't have to learn anything. I am too old. These youngsters will learn. And in future, they will be able to do more challenging experiments. You know, that basic technique we propose is actually very simple. This is high school physics. So this neutron beam essentially dealing with such a problem that you cannot count it properly and it gives background. But if you think about two billiard balls, say one billiard ball is coming here, a second billiard ball, both goes away. So say one of the billiard ball is invisible. Then even if you, but it has a, say it is some magician has made it invisible. But by knowing this, by conservation of momentum and energy, you can always predict. If you measure one here, you know exactly at that angle there will be one. You don't have to see that. So, and similarly, if you measure its velocity, you know its velocity. So this is the theory you are applying. Neutrons are invisible. Or it is visible, but they are very detecting is so difficult. This is actually that is where the error is coming. We say these neutrons are coming with a reaction like this. So why don't we measure the other particle? And with that, we will be able to. This is invisible, but we can exactly get it from our high school kinematics. So this is the new theory we have given to overcome that problem. And I think people are thinking that your technique is very robust actually. So anyway, this is the basic theory we are applying to this experiment. So that is going to be India's fundamental contribution if it succeeds in a modern bridging the gap in this theory of AGV stars. Similarly, again, of course, this I have already told. Another student is working on this phantom. So when we in cancer patients, we don't directly put the beam on the cancer patient because it can do harm. So we make a dummy device which is called a phantom in which we do all the experiments. So for our neutron therapy, India doesn't have it, so we have to do everything from scratch. So our students have designed all this machine now. We are going to make it now. This is funded by IQAC. We are going to test it. It is not theory. So our theory is that development is over. So you can see again every part, like you see all these drive, nuts, bolts, everything. I say every student to make everything. You have to make these holes, everything, whatever is needed. So that when we do it, it comes back, you assemble it, and it will work exactly the way you think. And these are skills they are learning. How to make things, how to model things, how to put together. So this is the phantom design. So this is the Dian 4 simulation they are trying to do. And then I just say that I don't want to go to the details, but you can see that yes, this whole thing, all the results, the way it will work, we have now predicting, simulating. Again, this is India's first. So we are going to get it working. So we think that once this is designed properly, and this is a PhD student youngster who is designing, so in future he has a whole life to work on. So when our things come, even if it fails now, something, you will understand where it fails. Next thing will work. Even if next thing doesn't work, the thing after that will work. He is young after all. He has all his life to try. So I think that is one of the part of our experimentation. This is always the most challenging task to a youngster. Well, I am old, too old. I have nothing to try actually. So they will try. They will learn the basics. Now I'm teaching them what I know, and then they will apply their own mind, and they will build it up. And they fail. They will understand why it failed. Then they will try to make the next one, and that way it will go on. So now this is another thing I am saying is about that. These are our dissertation projects. Our students are doing it. Just I want to give an example. As I said, everything here, this talk is done by our students. So nuclear astrophysics is our primary topic. We said the Dixit, he made this gas jet target. Again, this is India's first. Ananya has actually, I think this is like one of the brightest students actually. We are very proud actually we get these students. So actually I also use it that way because you get the brightest one, give them the toughest task. They will do it because you say that you can do it, you can do it. I keep telling them because I know they can do it. So eventually they end up doing it. So this is again theory and experiment gap. You know about that carbon is formed in the universe. Carbon is all our body everywhere. But how carbon is formed? It is not experimentally verified. We know 3 alphas in different ways combined together to give 12 carbon. But this is not known. The 2 alpha first actually it happens. It is at one of the scenario we believe is the 2 alphas combined together to form a 8 beryllium excited state like this, which has a 3 MeV gamma ray. This is a resonance state. It lived only 10 to the minus 15 seconds. So in that time, it captures the 3rd alpha and forms 12 carbon. But this state is still not measured. There is a theory only. And so we are bridging this gap. We are trying to bridge this gap by Ananya did all the simulation for this experiment. That how will we do? We will be planning to do it at Prana, that Science Institute. So this modeling we have done. India couldn't do such experiment before because this alpha we talked about, both alpha means helium. So one is a beam, but other one will be gas. India didn't have a gas target. So there is no way it could ever have been done in India before. But we have, proton is now we are developing, as you said, the first windowless gas target. That is what is required for this. So this experiment will use this. So this is what, but again, this is the theory that all the theory about alpha picking up going to 8 beryllium and the resonance state which lasts only for 10 to 1 femtosecond or less around that. In that time it captures a third alpha and forms the carbon, which is so we are all made of carbon. This is the theory. Hopefully, once we maybe it will take another 5 years or 6 years. It will not be on anesthesis, I told her. So this will be the experiment. I think we will again bridge this gap, and that is why we need accelerators. And of course, we also need young people who will work on this because they have their life to work on. If it takes 5 years, 7 years, fail 3 times, they have their whole life to try and succeed and give a name to our state, give a name to the country, like that. So this Dixit is again a very motivated and capable student. He developed this windowless gas target, and these two essentially have worked on our second field, the accelerator driven boron neutron capture therapy. These two have developed with a neutron target and how to monitor the dose of the neutrons falling on a patient. See, these we have our strategy is very clear. Whatever they work, if our accelerator comes in future, this will be a part required. So they are completing one project of that. So it is not just random. It is that whatever they are doing is we are learning from them, and if it comes, it will be directly used there. And of course, these are India's first. So this is the gas target which is designed. So you can see just I want to show the general theory. So this is a pump which runs at about 40,000 RPM. A certain thing that is rotating at 40,000 RPM, and similarly this turbo, this is called loose blower. Similarly, a turbo pump which also run at I think again 50,000 RPM. You see that like a turbo pump, a turbo jet planes, that fans they are run at that speed like these pumps. So these things has to be when you make them things like that together, it has to be accurate within microns. Otherwise, these things will just you cannot just make such a thing. So all this is now Dixit design. He has designed everything. We will get the model from the company. He put it together in CAD. It's a very advanced level CAD, and put it all together. And again, this is India's first, and we are now making the cost estimate to such a device for BRC. So this is this is our students, and then of course how much space it will take and beam all everything we have to design. So I mean he has designed. He's a MSc student, and I think it was an amazing task actually. You can see also these are all 3D modeling of the gas target. Everything is done with precision and accuracy that is required for such sophisticated instrumentation. And then this is what is actually he has made. I am actually very happy that I feel proud that our youngsters can do such things. I show them it because it is good for me. I go to show in a meeting in Delhi. Last week I have given a talk. I showed these things. People are, oh, your students do this. Yeah, we give them a lot of galis, so they do it. But anyway, so this is our future. Okay, these are our future. These are our future projects, and these all will make them. And now this will be developed at Sayan Institute of Nuclear Physics and BRC. Will make it. It will be called Proton system. And then, of course, when our accelerator in future comes, same things are required. So even if we have made a mistake there, we learn there. Our thing will work better when it comes. But these things you cannot make. See, they could not make it last 20 years. So this time, so even if you have an accelerator, you can buy the accelerator, but you cannot do any physics with this. Because these things. And this is like a baby step. We have to teach a student because India does not do such things. I have, of course, was fortunate enough to learn these things in US. So I am now passing it on. So they are learning, they are doing. So once all these things we develop once, make it, get it working, I think our students will, our accelerator will also be in a great shape, and this will give us name. That country will have more faith on us, our youngsters. I will not be there, but they will be there. They say, well, they have got this thing made, they have got it working. So I think their accelerator will work. So I think that will also help us. But it is our main mission of training our younger generation. It's what we are devoting our time. So finally, this is the Ananya experiment. I already told the physics of that, how the stars, this carbon is formed. This is still a mystery, which is still a theory. that data, this breeze, and this is the gas target we have just seen in the previous thing. So this is the gas target Ananya is planning to use for doing the experiment. And you see, this is the because we could not have done it before because we didn't have such a system. In another 5 years, we hopefully will be able to complete all this development and then do this experiment. Maybe 5, maybe 7, I don't know. These things take a lot of time to make, and because again, I told them I will do nothing. Everything that is done will be done by students. Whatever time it takes, it will take. I always say them, there will be no hurry because I also think that if I do something, it's a waste of time because I will not be there. I mean, these ones, even if they fail, they learn, they will be there in future. And I think long run for our region, our cotton and the Northeast, I think this is the way our students have to be able to do it, not me. So our projects, I always tell them, even if we are slow, don't tell us. But 20 years no one has done anyway. So I think so. And similarly, the other dissertation students done on the neutron target for the our new ADB&CT facility we have proposed. So again, this will be useful when if the facility comes for an indigenous beamline, we are developing this indigenous treatment facility, all the simulations. I think this is the code they have to write in Sayan code. Similarly, this is the neutron dose monitoring. Again, a new technique that is done in Italy. So I should, because they are building up their facilities coming up next year, this ADB&CT facility. We also want to build with the rest of the world together, and India is first. I don't know what government does, but if it comes, so this is the how the patient dose is monitored. So we have already our student is modeling there, so that we will compare our results, so that we have a basic understanding of all the basic processes before we actually make the things. I think it is very important to understand theory. That's what we are doing, and then so these are all you see MSc students modeling using Sayan 4. Just to, I don't want to go to detail, just you can see how those things will work. They have modeled it. Of course, we are still calibrating our results. I am not saying these answers are accurate. We are still in the learning curve. There are many steps we have to learn because we will test all our results with published results and see where we are making mistakes. And that way we will calibrate our code and then we will actually develop the new things. But these are like time consuming when you do it youngsters. So we all learn together. So that is what is going on. And I think so summary, I want to finish my talk here now. So QPAC ANI of course is proposed accelerator facility. This ANI students in accelerator, that's what we are trying to do that. Then PIMS, ADB&CT, these are major research topics I have already discussed and our students are working in this. We are already showed that investigate PIMS, positive and mass spectroscopy. India is very fast. We are essentially breaking a US European patent now. If this succeeds, we'll just break the patent. I think it will happen this year. But you have seen what is every nut and bolt has to be developed ourselves because this is a patented product. You don't know what is there. So everything you have to develop from theory to the final machine. So this we have, I think, completed. I believe it will work. I mean, everybody believes that nobody knows is this is the word patented or not. But I think funding agencies has funded us, so they also believe our logic is correct at least. If we do and we'll see what happens, and that level is there. Then this is the neutron source for the AGB star, asymptotic giant stars. That is one of our major research project, and if it, I don't know, even if we don't succeed, at least if we can reproduce some earlier data, at least we have established a new technique. As I said, like a 2 billion ball hitting, the news that is called normalization in technically. The normalization of neutron flux. I think that we have established as a fundamentally new technique. Even if the main experiment we don't improve upon, we don't know. We have to do and see. But yeah, so that is there. Then this ADB&CT moderator and phantom, that we are working on these things. And as I said, the finally was many, if not all of these are first in the nation. Okay, and I can say actually that is what we are so feel good that our students are making us proud with their work in design and implementation and of these innovative ideas. Okay, so let us see some what happened, just to some results. So you can see that this is the India's called mega science vision of the country. The Prime Minister's principal secretary advisors published this report this year. early, I think, something I forgot. So what it does is that how the country should, what science, the mega science, means which involve hundreds of crores like the one we want to do. So those money has to be, of course, put proper use. So they want to see what is the idea and how this will be the national benefit from this. And then India, they make a roadmap. This is the Prime Minister's principal scientific advisor publishes this report. This is the Government of India report. So this is the vision of India, and you can see there, we are figuring there. I think this is the only university in the whole country. Forget about IIT, ISA, NISA, IIT, whatever. Nothing there except cotton. This is the vision as I described. These are the vision we have for this nation. We don't actually, we have for our state, our region and northeastern region, and it is also the part of the country's vision because this is none of this going on in the country. So it has essentially figured in the India's vision for 2035. So this is the science country would do. At least this office recommends to do. Ultimately, politics and budget, we don't know what happens. But pure science point of view, this committee is a pure science. The pure science, they say what we are saying, they summarize this what we are saying. I have given the talk here, which we have done, that how this country will benefit, world-class science will be done at Qatar. So this is our thing. Another thing I want to show, so I gave this talk a couple of years back at the DA National Symposium in Mumbai, in the Bhabha Atomic Research Center. In the summary talk, there were, I think, more than 400 talks or whatever. Is a summary talk, his experiment is 1 hour, maybe half of the talk are experiments. And you can see out of his 4 slides, 6 slides, he was the former director of the Bhabha Atomic Research Center Nuclear Physics Division. So he had some very nice word about our program, the way we want to do things involving students and the technology we are trying to develop. He has seen, see all these slides I have shown, those are essentially shown by him. In his summary talk, 8 slides, out of which I think 40. This is, but it has 400 speakers. Is our facility. So we can say that way that nation is also becoming aware of what we are doing. And I think I want to stop here. I think, yeah, this is the stop. So this is my talk. And well, any question? And I all request all of you, of course, that give the good wishes. We should have this accelerator. If you happen to meet with some your local MLAs or MPs, please tell this is for our region we are trying to do. Whatever place, because ultimately the decisions are taken by the politicians. So I think I request all of you wherever, because this is for our children, and you see how capable our children are. They will make us very proud. We have to just give them the right tool. And so I think everybody should, when if you get a chance, just tell that this accelerator is for all of Northeast, all of us. So please try to fund it. So you put your kind word towards so that this gets funded. Anyway, thank you.
Thank you so much, sir, for your wonderful talk about the accelerator. And it's a proud moment for all of us that the accelerator is going to be installed or established at Cotton University. So thanks a lot, sir. So it's open for any questions or queries from the audience. So at first, sir, I have a few questions. So firstly, the neutron that which will be emitting from the reaction proton plus lithium will give neutron and beryllium. So what will be the neutron flux in that reaction inside the accelerator, and how will you detect these neutrons? Because neutron detection is a very tough job to do, and there are very few detectors which can actually accurately detect the neutrons.
Yeah.
So
Okay. Okay, I think that's a good question. So let me, because so what happens is that these neutrons, we also rely very heavily on simulations in these experiments. That you have to say, that's why we are doing the simulation. So this time, this is the dimple has shown some data. I will just show, then I'll try to explain. So for example, so this we are going to put proton beam on lithium target. This is a water-cooled lithium target. And this kind of research needs typically 10 to the power 12 neutrons per second have to be there to produce to be able to treat a patient within, so about 20 minutes is the patient treatment time. So within the 20 minutes, to kill all the cancer cells that is there, you need about 10 to the power 12 neutrons per second. So this is why, so there's a beam, the primary beam that comes in. This is, so the proton beam we use, the proton beam energy we know. So that cross section at that, the probability that how many times a proton will get converted to neutron using lithium target is we know, assume to we know that because some measurements are there, but not at this stage. And so, and the target how it will behave. So these things, of course, then we have to go on simulation. So we say that we basic parameters we know, and then we can say that this much neutrons will come out, and that we believe the simulations. Of course, we can do some proportional measurements, 10 to the power 12 neutron per second. We can never measure, but neutron some part we can scale it out. So we can say if I measure this part, and then I can say, well, you know, this is just a scaling. I have measured 1 millionth of a part, so I have to multiply the total number by a million, or one like that. So there's just some amount of scaling depending on the modeling which is also involved. So this, but this is the state it is.
Okay, thank you, sir. And one more question. Because neutrons are very harmful for human and also for animals. So how will you shield the whole
So
accelerator?
again, our so we use the neutron shieldings are there. We have put a lot of time. So let me show our one of the project reports. I cannot show every part of it, but yeah, I think this is a good thing. Again, our students did it. Otherwise, if I have done, I would not show that. But it is done by our students. So I want to show what they are capable of actually. You know, yeah. So let us see. So we are talking about facility BNCT 227. Actually, this we are our optical ADBNCT release 2.0. Okay.
So high density polyethylene may also be used, I guess,
Yeah,
because
yeah, yeah. But
SDP.
it's not that, because that is there's a huge problem. There is that such materials are essentially also fire prone. See, this is also a lot of, you don't want anything to catch fire. It's a huge fire hazard. So you can see here, this is now the neutron facility. This is again developed by Rasna and Dimple. Actually, two of our ladies are leaders of our accelerator physics. I am happy about that. Actually, QPAC also has a principle. 50% of the anything, if you get a position somewhere, say we got some internship, 50% will be always girls. We put that way. If we have got fellowships abroad, always 50%. Me at least. It means if there are two positions are there, both could be girls, or at least one will be girls. So I am happy that I think India is also, the country is also liking our principle. So this is our adopted principle. So anyway, this is entirely developed by, to answer your question, this is the modeling they have developed it using CAD, and of course, a lot of the ANPO simulations are here. So these are essentially concrete, high density concrete. See, it shouldn't catch fire for the neutrons. So this thickness of each of these walls, this is again a whole accelerator of how the facility will look like. So these are designed in a way so that this beam is coming, proton, the neutron target inside, so neutron will inside. But once these walls, that is concrete, are there, neutrons will not come out. This thickness, and this had a mixture of iron and some other things. It's called high density concrete. It absorbs neutron very much. But your question is right. In general, many laboratory experiments we use paraffin, borated paraffin. But those you cannot use in the industrial environment. So this you know, this accelerator has got something like 15 kilowatt power. The beam is carrying 15 kilowatt. So 15 kilowatt in a couple of millimeter, maybe a centimeter spot. So if you see anything on the earth will melt at that and will catch fire. So these facilities, we must avoid fire.
Yes.
So this is how this is done, and this is done by both Rasna and Dimple. I don't know, one of them have done, or both have done together. This beam and everything. See, yeah. So I give them the order. You know, you have to come up with this design by this time. Then I see. So what they did, both of them did, I think. But anyway, so but I'm really proud actually. These things are happening.
Yes.
They are learning that what is goes inside. It is more important than the learning the basic tools to do things. And this is This is your question, and that is their answer.
Yes, sir. Thank you. One more last question from my side, sir. So, will it be the neutrons will be thermalized, or it will be the first neutrons?
Oh, yeah. Okay, good question. Yeah, that is a very that is why the major research we are doing now. So these neutrons, this is actually the neutrons you need. These neutrons you are talking about, they cannot be
Yes, for the
produced
BNC.
actually. Actually, I should show this full slide. This is little small slide. So you can see here, this x-axis here, how the neutron energy, this is the IEA spectrum. See, it is a for patient. We cannot do any trial with patient. So there is a very standard strict regulation. The neutron beam that you are putting on these cancer cells of the human patient has to be like this. This is the number of neutrons in the given energy. So you can see something like peak is at 1 milli-electron volt, 0.1 milli-electron volt. Yeah, 0.01 milli-electron volt. And the neutron energy, it should look like this to treat the patient effectively. Otherwise, you don't get certificate for treating patient, the patient certification requirement. So this is the kind of the neutron energy you need, but accelerator don't give that. This coming out of the accelerator is not like that, and that is why this is the accelerator. This is a dimple slide. So she is, of course, a medical physicist. So she all this stuff she medical wise she does. But anyway, so this is the device. The whole device, this whole simulation that is done, this device, it has got very different things, so that it will become this neutron that come out of the accelerator will have certain energy. So this will be slowly slowed down. At the slowed down also without loss, they will be also focused. Because otherwise, like this time they slow down also. You need 10 to the power 12 neutrons per second. If you don't have that, I do not know the exact number. I'm sorry about that. It is around there, but I don't know the exact number. It should be something like that. I should not be quoted the exact number. So you need that some number of neutrons which you produce from the accelerator. But if it is also slowing down, they are lost. They are lost. You cannot treat the patient. So this device not only slows down, which is thermalization, it also focuses the neutron back here where the patient is there. So in this, so this things he has shown there. I have a better figure in the past. So this device essentially will do that, and the head of the patient is here actually, and where we do the clinical studies. And I think this is the whole shielding and everything she is showing how the full place. This is the indigenous beamline for indigenous cancer treatment. We want to put the second treatment facility. If one comes imported, the second one is built by Cotton. So this is this design. We have finished actually designing this stuff. I mean, we have to, of course, we have finished the first generation of calculation. We are now going to verify our results with all known things before we say we have completed it. But yeah, we have at least with a step that it runs and gives results. These results are correct or not. That is the calibration of the code, what is called in modern physics. So we are at that stage. Yeah.
Okay, thank you, sir. So if any other questions are there from the audience, you may ask.
I'm really sorry, I might have taken a lot of time because if you're talking about students, I get little carried away maybe. I also want to explain actually. Yeah,
yes,
these are very new things. I mean,
yes, sir. I have one quick question,
sure.
if I may. Yeah.
Oh,
So thank you very much.
Yeah.
So thank you very much for the talk. So I have a quick question regarding the calculation of the symmetry energy parameter, like this new neutron skin thickness. Will that be feasible in the current facility that you mentioned? Is there any plans? Are there any plans for it?
Okay. Actually, that specific details of an experiment, we don't. We have not. We have not actually identified the domain and the basic parameters of the domain. At that specific level, actually, we have not yet looked into. But as you know, if that experiment is done in a similar technique with a neutron beam or a proton beam or a charged particle beam, certainly we will be able to do it because it's a much more powerful accelerator than that is ever in India actually. If India anywhere is measuring that, certainly cotton will measure it.
Yes. Okay. Yeah. Thank you so much.
That is it. Anything that is going on here, we'll be doing it at least 10 or 100 times better.
Yes, thank you so much. Thank you, sir.
Yeah, but if it is not going on, then I have to think more. But this is the general answer.
Yes,
Yeah.
I get it, sir. I get it.
So, is there any questions from the audience? If not, let us thank our plenary speaker. So, thanks a lot, sir, for your time and.
Oh, thank you so much. I am so happy our youngsters are you have organized such a nice workshop with such a title.
Thank
I'm
you,
very
thank you.
proud actually. I'm feeling proud of everybody who is there. I mean, this is the way we want our future generation to be. Thank you so much for giving me
Thank
the
you,
opportunity.
Thank you, sir. Thank you so much for your words.
Sir, sir, hello.
I have to stop
May I
sharing,
request-
right?
Yes.
Yes.
Yes. Yeah.
May I request you to share this session, sir? Only 2 students are there from
Okay.
nuclear
Sure.
radiation. So,
Yeah.
it's over to you, sir.
Okay, thank you. Yeah, okay. So I think I saw the titles.
Okay.
So
Sir, if
it is
you
now Priyanka Sudhuri, right? Yeah.
hello. Now it's
Hello.
Priyanka Sodri from KTH Royal Institute of Technology, Sweden. So, Priyanka, you can share your slides.
Hello. Am I audible?
Yes, you are.
Yes, yes, you are.
Okay, thank you. Okay, let me share my screen. Can you see my screen?
Yes, yes.
Okay. Hello, everyone. I am Priyanka. I am a postdoc at KTH Royal Institute of Technology. First of all, I would like to thank the organizers for giving me the opportunity to present my work. So basically, I work on the theoretical nuclear structure studies, specifically by using shell model and ab initio many-body approaches. So today I'm going to present my work on the beta minus decay of 46 and 47 potassium. So this is the outline of my presentation. Firstly, I will give a brief introduction about beta decay, followed by the formalism of beta decay. Then I will introduce the model which I have used in my calculations. And finally, I will present my results and conclude my talk. So this is the nuclear chart or nuclear landscape, which most of you are familiar with. So in this chart, these black squares represent the stable nuclei, and they form the value of stability or beta stability line. And when we move away from it, then most of nuclei are unstable. So they undergoes various kinds of decays like alpha decay, beta decay, proton emission, neutron emission, etc., etc. And today I will focus on the beta decay. And in this nuclear chart, more than 6,000 nuclei exist, and among them only less than 300 nuclei are stable. So these nuclei are formed through nucleosynthesis processes such as S process, R process, RP process. And now maybe you are wondering how beta decay takes place in the nucleosynthesis processes. So the answer is in this process, a nucleus captures either a proton or a neutron and form a heavier nuclei. And if the beta decay half-life of that heavier nuclei is shorter than the capture reaction rate, then it undergoes decay before it captures a proton or a neutron. So the precise measurement of beta decay half-life is essential for the nucleosynthesis processes. Today, I'm going to present the beta decay half-life for 46 and 47 potassium isotopes. And why have I selected these isotopes? Because this nuclei lies around Z equal to 20 shell closure. So they are very important for understanding the single particle proton and neutron shell structure around it. And they also set a benchmark for any nuclear model. And the most important thing is recent available experimental data with high statistics. So that motivates us to perform the theoretical calculations for it.
So there are three nuclear processes occurring in the nuclear environment, which are beta minus, beta plus, and electron capture. Today I will focus on the beta minus decay, in which a neutron converts into a proton with the emission of electron and antineutrino. And this process occurs in the neutron-rich side of the nuclear chart. And beta decays are classified into two categories based on the selection rule of the angular momenta of the leptons. These are allowed beta decay and forbidden beta decay. And to describe the beta decay theory, impulse approximation has been used. And in this approximation, the decaying nucleon feels the weak interaction at the moment of the decay, while remaining A-1 nucleons act as spectators. And only in the initial and final state, this active nucleons strongly interact with the A-1 nucleons. And the half-life for this decay process is given by this expression. And for the allowed transition, it depends on the BGT, which is the reduced transition probability, which depends on the nuclear matrix elements. And these nuclear matrix elements between the initial and final state is the product of single particle matrix element and the one-body transition density. And this one-body transition density depends on the model. So in my calculation, I have used the nuclear shell model, which is the most successful model to describe the nuclear structure properties to calculate this one-body transition density. So in this model, a nucleus is described by an inert core, which is made of closed shell configuration and extra nucleons in the valence space. And these extra nucleons will decide the properties of entire nucleus. And the Hamiltonian for a system of a nucleon is given by this expression, where this V is the residual interaction. And it is considered in this model that interaction takes place among the valence nucleons via this residual interaction. And in the past few decades, several ab initio approaches has been developed in which all the nucleons are considered as active, but these calculations are computationally expensive. So I have used this nuclear shell model to perform the calculations for potassium and calcium isotopes using SDPF-MU interaction. And for this interaction, 16 oxygen is considered as inert core, and the valence space consists of two major shells, SD and FP. So that allow us to calculate both positive and negative parity states for these isotopes. And first, I have calculated the spectroscopic properties to check whether this SDPF-MU interaction is suitable or not for these nuclei. Then I have used the wave function calculated from this adapted interaction to calculate the nuclear matrix elements, which are needed for the log-FT calculations. So here I have presented the energy spectra for 46 potassium and 46 calcium. And also compared with the experimental data and some previous results. So for 46 potassium, the experimental ground state spin parity is tentative. So our shell model calculation with this SDPF interaction predicted this ground state is 2-. And we can also see that our SDPF interaction gives better energy spectra as compared to the previous one. And also here I have shown the energy spectra for 47 potassium and 47 calcium. And one can see that this SDPF interaction gives the energy spectra, predict the energy spectra very well. So which means we can use the wave function from this interaction to calculate the log-FT values. So here I have shown the log-FT values for the beta minus decay from 2- state of 46 potassium to various excited states of calcium isotope, 46 calcium. And here I have also shown the mode of decay, and these are the experimental spin parity of the excited states. So we can see that some states has a tentative spin parity. So
Priyanka,
for example,
sorry to interrupt.
Yeah.
You have 2 minutes.
Yeah, I will finish. And a state at like 3.9 MeV, this state could be either 2+, 3+, or 3- experimentally. So I have performed the shell model calculations, and this predicted that this state to be either 2+ or 3-. Similarly, a state at 4.4 MeV, this state is predicted to be 3-. Similarly, I have done calculations for the beta- decay from 1/2- state of 47 potassium to excited states of 47 calcium. And we can see that there are many states which have tentative spin parity assignment. So I have confirmed the spin parity for these excited states based on the energy spectra and log FT values. And we can see that our calculated results are in good agreement with the experimental data. So I have performed the nuclear shell model calculation for these beta decay transitions for the first time. And this shell model study helps to assign the spin parity for these unconfirmed states. And our calculated log FT values agrees well with the experimental data. Thank you.
Thank you, Priyanka. Yeah, thank you, Priyanka, for the beautiful talk. I guess there is some technical issue with Professor Das' end. So the platform is open for quick questions. You can have 1 or 2 quick questions. And thanks a lot for completing in time. Yeah.
Thank you.
So do you have any questions? Okay, then if there are no questions, let's thank the speaker. Thank you, Priyanka. Okay, thank you. Okay, let's move on to the next speaker. We have Pranjal Putim Gogoi from Cotton University. Pranjal, are you there? Yes.
Yes, I'm audible.
Yeah, you are audible. Can you share your screen, or do you want?
Yes, I request you to share my.
Okay,
slide
sure.
on my behalf.
Yes, I completely understand that. Let me just. So. Yes. Okay, is the screen visible?
Yes.
Okay, so please let me know when to change the slide. I'll do it accordingly.
Okay. So respected Professor J.J. Das, sir, member of organizing committee and the participant present in this online platform. Now I'm going to present my topic, and the title of my presentation is Radon Exposure and Radiological Risks Insight from a Seismically Active Region in Assam, India. Please the next slide. Yes, first of all, the introduction. What is radon? Radon is a radioactive gas which is found in the decay series of uranium-238 as an immediate daughter product of daughter elements of radium-226, and it decays to its solid progeny polonium by emitting an alpha particle of energy 3.82 days. And it has three another isotopes, radon, thoron, and actinon. No doubt, radon and thoron are predominant in nature due to its comparatively longer half-life than actinon. Next. Why we are studying radon? Radon, that means the inhalation of radon and its decay products are when inhaled by human beings, they accumulate in the lungs and irradiate tissue, harming the sensitive inner cells or inner linings of the bronchiole and causes the lung cancer. In 1998, International Agency for Research on Cancer, that means IARC, recognized radon as a human carcinogen. And in 2009, WHO, that means World Health Organization, classified radon as a second leading cancer-causing agent after smoking. Furthermore, long-time exposure to radon, thoron, and its decay product or progenies can result major health problems such as leukemia, skin cancer, renal sclerosis, and other ailments. Please next. Now, why radon exhalations? Radon isolation plays a vital role. That means it gives an indication for assessment of high radonics area. Primordial radionuclei such as uranium, thorium, etc. are considered to be originated in the earth crust and are commonly found in the all geological sample that is present in the earth crust. The radium isotope, which is found in nature as a result of uranium disintegration. That radium isotope, when decays in mineral gain, it migrates from one place to another in the earth crust and seep into the environment through the appropriate avenues. The rate at which radon escapes from ground surface to upper atmosphere, it is known as radon exhalation rate, and it can be measured by two terms, mass and surface exhalation rate. However, a variety of factors such as porosity, grain size, and environmental parameters such as temperature, pressure, humidity, etc. affect on radon exhalations. The another diagram shows how radon enters a house. Radon enter the indoor environment through floor cracks, damaged floor wall joints, tap water, and loosely fitted sewage disposal system pipes. Radon, which is very radioactive, can easily be mitigated in open air, but radon concentration can rise to be harmful level if it is entered throughout the basement, through basement floor and is confined in the indoor settings due to the or suppose the home is not properly ventilated, then it becomes very harmful for human beings who reside inside the house. And WHO recommended that the recommended limit of radon in indoor setting is 100 becquerel per meter cube. WHO also indicates that concentration should not be exceeded worst scenario more than 300 becquerel per meter cube. Next slide, please. Okay, these are the factors that govern indoor radon concentrations. Primarily the local geology and meteorological parameters, building materials, ventilation rate, living style of the inhabitants, etc. are affect the indoor radon concentration. And it has also been reported that igneous rock compared to the sedimentary rock have higher quantities of radium. Next, please. Now the background of the study. Northeast India is known for its significant geological settings. This region is an agglomeration of many tectonic blocks, namely the Siang Syntactial Zone, Himalayas, Indo-Myanmar ranges, Mississippi ranges, Shillong, Mickey Hills Plateau, etc. These tectonic blocks have been producing mild to large earthquakes. For example, in 1897, the Great Assam earthquake of magnitude 8.1. In 1950, the Assam earthquake of magnitude 8.7. They caused many mortalities, property loss, and most importantly, changed the whole geophysical setting of the entire regions. Of course, now of late, intense seismic activity have been reported in the Kopili fault zone, which engulfed the Kopili lineament and distributed from the southern part of the Brahmaputra to the northern part of the Brahmaputra in Assam Valley, and to up to the foothills of Himalayas. Unfortunately, high incidence of cancers are recorded in Northeast India. Therefore, the utmost necessary arises to monitor and measure the radiation levels in the light of radiological exposure the people resides in this geologically sensitive area. In 2021, a series of earthquakes were recorded in the Kopili fault zone, whose epicenter lies in Dhekiyajuli region of Sonitpur district of Assam. On 20th April of 2021, a major earthquake of magnitude 6.4 was recorded, which caused many property losses, also two fatalities, as per the reported. Even in June 11, 2023, a mild earthquake was also recorded, whose epicenter also lies there in this Sonitpur district. That means Dhekiyajuli region, which lies again in Kopili fault zone. And it has been reported that there is a radon anomaly which is associated with the variation of region, seismic and tectonic movement. So this diagram shows the geological map epicenter of the earthquake, and that yellow is the shows the 28 April 2021 earthquake of magnitude 6.4. And these another photos which shows the wall cracks, ground cracks, and emergence of sand boil, liquefaction, etc. Next slide, please. Now, these are the materials and method we are using to measure the radon exhalation rate. And first of all, these devices are used to measure radon exhalation rate from the geological sample, that the samples collected from that particular region, which is soil, granite, gneiss, shell, sandstone, or coal. No doubt, coal not collected from that region, not found there. So I'll tell you later why I'm using the coal here. Now, the passive integrated technique, it is here we are using solid-state nuclear detector LR115 type 2. And after processing the sample, we have to put that samples for 30 days exposure. And after retrieving the detector, please next slide, we have to perform the etching in a constant temperature, but in a solution of 2.5 normality sodium hydroxide at a 60 degrees Celsius for 90 minutes for the revelation of tracks. And red tracks can be counted by using microscope and also spark counter. Next. Now for terrestrial gamma dose rate measurement, we are using this micro survey meter. That survey meter is by using this we can measure the indoor and outdoor gamma dose rate. Also the other parameter we can calculate it. And these are the symmetric diagram of the measurement devices. Next. Next slide, please. And the indoor radon and their progeny concentration, again we are using passive time integrated techniques, single entry pinhole dosimeters, bare DTPS DRPS, that means direct thoron progeny sensor, direct radon progeny sensor, wire mesh cap DTPS DRPS, that is again fitted with solid state nuclear tag detector LR115 type 2. And that detector we have to install for 90 days in the indoor settings of that means the houses of that particular locations, and 1.5 meter above the ground and more than 10 centimeter away from the surface wall. And after retrieving the detectors, we have to again perform all the same thing, etching, and after etching we counted the tracks, that means produced by the alpha particles by spark counter. Next. And these are the symmetric diagram of the single entry pinhole dosimeter and DTPS DRPS.
Hello, Pranjal, you have 2 more minutes.
Okay. And this DTPS and DRPS are made up of some solid-state nuclear tag detector and also some absorber and the aluminum absorber. Next. Next slide, please. The pinhole dosimeter available in our lab, and these are the results. Of course, next slide, please. The results and geological maps showing the sampling site and the pictures of some site visit at that particular locations. Next. And these are results. From these results, we can obviously see that EM means the mass exhalation rate, ES means surface exhalation rate, CR means the radium content, and is the effective dose rate. And these are the ranges. Next. And from that bar diagram, we can see that the soil possesses higher exhalation rate than the rock samples, which is namely the gneiss, shell, sandstone, etc. And the correlation diagram shows that there is a strong correlation between the radium content and the mass and surface exhalation rate. Next. And these exhalation rate means far from the coupling effulgence. We perform there from in the we collected samples from the vicinity of the coupling effulgence and also from the far from the coupling effulgence. Here we are collected granite and soil, no doubt. Other samples are not found there, so we perform granite and soil for far from the coupling effulgence. And next, please. And from the result, we see that granite shows higher exhalation rate compared to the soil. When we perform that means exhalation rate experiment, then we found that in far from the coupling effulgence, we found only in granite samples exhalation rate is more, but in the vicinity we found soil sample more. Next. Now a geographical map showing the locations where we perform the terrestrial gamma dose rate experiment. Next. And these are the results. That means that AED means annual effective dose equivalent, outdoor GDR means gamma dose rate, LED means lifetime effective dose, ELCR means excess lifetime cancer rate. All the parameters we calculate by using some UNSCARED, that means United Nations Scientific Committee on the Effect of Atomic Radiation, and ICRP, International Commission on Radiological Protection, they gave some formula. As per the formula, we calculated these parameters. Next, and these are the results and distributions. Next, statistical distributions. Next, and seasonal variation of indoor radon thoron and dwellings of northern Copperleaf Fall Zone. And from this table, we obviously see that that means the thoron concentration is more compared to the radon concentration. It seems that in the soil sample, no doubt, that particular position, maybe level of thorium is more compared to the radon. Next. This bar diagram shows that in the winter season, we found more radon and thoron concentration compared to the spring, summer, and autumn season. We perform, we put or we install dosimeters for whole year, including 4 seasons: winter, summer, and autumn and spring. And among them, we found our thoron and radon concentration more in winter season. Next. And we are planning to extend our work to another provinces of northeastern regions, and we are now performing there in Nagaland, which is belong to the Naga or Supan belt. Next. Also, we are performing work there in UGC CSR Kolkata Center for radium content and other uranium content, no doubt, radium content or thorium content and other for other purposes. Next. These are the conclusions. And the rate of radon accumulation we found higher, as I told earlier. Even in the terrestrial gamma dosage, also the places or the locations where liquefations or sand boil immersion, etc., were shown there in that particular diagram. There we found more indoor gamma dose rate or outdoor gamma dose rate compared to the other location. Next. Of course, a distinctive seasonal variation also we observed there from the bar diagram. Okay, next. Thank you.
Thank you so much, Pranjal, for the beautiful talk. So, since we are a bit behind the schedule, so we can take one quick question if there is any from the audience. You can just unmute and ask. Okay. So if I think there's no raised hand or question. So, okay. So you may also contact these presenters via email. We have already provided the email addresses in the abstract book. So you may contact them at any time, and I hope they will be able to answer to your queries. So, okay. Thank you, Pranjal, for the beautiful, insightful talk. So next we have with us Jyoti Ojha from IQAC College. And she will be speaking on Shikha there. You just stop still.
Yes,
okay. Yeah, so you're here, right? Okay. Can you please have your screen? Yes. It's not visible yet, but okay, fine. Yeah, thanks. Okay, so please proceed with the presentation. I'll give you a 8-minute warning. Okay.
Okay, sure.
Yeah, thank you.
So, good evening, sir, and everyone present in the session. I'm Jyoti Ojha. I'm working as an assistant professor in Department of Physics, Adhikari College. I'll be talking today on study of microwave constitutive parameters of strontium substituted barium ferrite NPR nanocomposite for microwave observer applications in X-band. Okay. So now what is electromagnetic interference? So we know that electromagnetic wave spectra is widely used in the communication systems, and the leakages of the EM wave in the communication systems lead to electromagnetic interference, which in return lead to malfunctioning in the electronic devices. So there are a lot of side effects of the electromagnetic interference. So some of the previous speakers have mentioned that. So the next one is, how do you reduce this electromagnetic interference? So for reduction of electromagnetic interference, some seals are used, and these seals are of 2 types, reflector and observer. In the reflector type, the incident electromagnetic wave is completely reflected back from the surface of the device without interfering with the parent device. And in case of observer type, the unwanted wave get attenuated within the device, within a shielding material before interacting with the parent device. So out of these two, the reflector type has a shortcoming, that is the reflected unwanted EM wave may affect the performance of other components in the vicinity. So that is why we have chosen the absorber type. So our study was conducted for application in the X-band. These are some important points, important applications of the frequency in X-band. And then the mechanism of microwave absorption. So in the figure itself, it can be clear that the microwave absorption mechanism require two main conditions, that is the low reflection at the absorber interface. So low reflectivity at the air absorber interface, so as all the electromagnetic wave incident on the device enters the material. And the second one is that it should be able to attenuate at least 90% of the wave that enters the device. So these are the two main conditions, and these two conditions require some very important parameters, which is explained by transmission line theory. Again, this theory was very discussed in details by some of the fellow participants in the earlier session. So from the equations shown in the slide, I will come to the main point. The main important parameters required here is complex permittivity, complex permeability, and then thickness of the absorber. So for this requirement, we have selected the material as barium ferrite as a ferrite in here.
Jyoti, can you please reshare your screen? Your screen is frozen a bit. I don't know. Please reshare your screen. I just share the entire screen. It's helpful.
Can you see this, sir?
Yes, please do it in yes, now it's fine. You can proceed. Yeah.
Okay. So should I repeat this, the earlier session,
No,
earlier slides? It's okay? Okay. So for the requirement, we need some material which are very lossy in nature, and it should have the material parameters, that is complex permittivity and permeability, such that it achieve the input impedance matching condition. So for that, we have selected barium ferrite as our inclusion. And because it has high saturation magnetization and high crystalline anisotropy, and for lossy material, these two parameters are very important. And then we have used base matrix as NPR, novel phenolic resin. And instead of bulk ferrite, we have used nanoferrite, and because nano-sized particles have high interfacial area, which creates a large interaction zone, which increases the interfacial polarizations, leading to a high value of complex permittivity and permeability. So we have synthesized the strontium substituted barium ferrite using co-precipitation techniques, using some ferrite, these iron and barium and strontium nitrate precursors. And these are material characteristics for confirmation of the hexagonal structure and the formation of barite, strontium substituted barite. We have carried out X-ray diffraction pattern as well as transmission electron micrograph. And the X-ray pattern shows that the reflection place shows the formation of hexagonal barium ferrite, as well as the lattice parameters also match with the JCPDS number. The transmission electron micrograph shows rod-shaped, extended rod-shaped, all the particles are extended rod-shaped hexagonal structure. The reason is mentioned here. The surface energy of barium ferrite is different in different directions of the unit cell, and it is preferential in the C-axis. So that is why we have some extended structures. These structures are also very beneficial for the absorption studies. Now, the next is the extent of absorption depends on interaction of the electromagnetic wave with the material parameters, as we have mentioned. So for that, we have prepared the nanocomposite using the mentioned polymer and the ferrite inclusion. And here we have maintained the weight as the 50 weight %. So the microwave characterizations were carried out using Nicholson-Ross technique, and these are some formulation of Nicholson-Ross technique, and these are some results. So in the complex permittivity and permeability results, sorry, I can see the, okay. So in the complex permittivity, strontium, all the samples are not showing any variation throughout the frequency range, but some marginal increase in both the real part of permittivity as well as the imaginary part is observed with increase in the strontium substitution. So the maximum value is obtained around, sorry, the maximum value is around, sorry sir, I can see the baseline.
The screen is visible over here on the screen.
Okay.
So you have like 2 minutes, okay?
Okay. So the maximum value of permittivity is around 8, and the loss is around 3, and the maximum is obtained for strontium ferrite. Similarly, for complex permeability, we have some natural ferromagnetic resonance pattern. And the natural ferromagnetic resonance frequency depends on the anisotropy of the material. And we know that strontium is more anisotropic than the barium. So with increase in the strontium ions, the anisotropic increases, as well as the frequency corresponding to the natural ferromagnetic resonance also shifts towards the higher frequency side. So these are the spectra for for dielectric and magnetic loss tangent. Magnetic loss tangent is very important. Here we have obtained 0.4 loss tangent for the dielectric part, and similarly for the magnetic part we have obtained 0.62. So depending upon these results, we have seen that because of this high lossy characteristics, the strontium substituted barium ferrite NPR nanocomposite can be a good candidate for microwave absorption studies. So for that, we have designed a single layer microwave observer using the transmission line theory. And these are the formulation used. Here we have to use the material measured material parameters, and this is the flowchart of the MATRE program, which is designed for the absorption studies. And here we have optimized the thickness of the composite from 1 to 4 mm. So one of our fellow participants has discussed regarding the Rosanov limit. So the Rosanov limit is 4 mm in our application condition. So we have kept the maximum limit as 4, and for the required thin absorber condition, we have taken the lower limit as 1. So in the results section, we have seen that the maximum absorption is obtained for the 2 mm thickness strontium substituted absorbers, and it shows maximum absorption of -61.2 dV, which is very high absorption, and it shows around 9.94 gigahertz. And it is matching with the resonance frequency. So because of the coupling of the coupling of the electromagnetic wave with the magnetization of the medium, the loss is taking place here. So from all these results, we can go for practical design of strontium substituted barium ferrite with the
Jyoti, can you please continue the conclusion? It's the time.
Okay.
Yeah.
So these are my conclusions. We have developed a M-type hexagonal ferrite inclusion, and the crystalline and particle size are determined from XRD and TEM respectively. And the design absorber shows very good microwave properties. Therefore, it is a good, it can be a good absorber. And the calculated study shows -61.22 dB of absorption with around 2 gigahertz of minus 10 dB absorption bandwidth. So that's all. Thank you very much for your attention. Thank you, sir.
Thank you so much, Dr. Oja, and we apologize for rescheduling your talk a couple of times. I'm very
No, it's
sorry.
okay,
Okay.
sir.
So the platform is open for questions. We can have one or two quick questions if there are any. Okay, so if there are no questions, then let's thank the speaker. Thank you, Dr. Oja. Okay.
Thank you so much.
We move on to the next speaker with Dr. Femina Brahma from CIT Kokrajhar, Assam. So Femina, are you there? I can see you in the participant list. Femina Brahma, are you there? Then there must be a problem in our technical end. Okay, so let's move on to this. Concludes the session 3 of. So let me thank our session chair, Professor Das, for his time and for his beautiful talk. Thank you, Professor Das.
Hello, sir. I am here. Yeah.
Oh, you're here. Okay. There's an echo on your end. Yeah. So can you share your screen?
Yes, 1 minute.
Yeah, please.
Can you see my this screen?
No, we cannot see your screen.
Okay, wait. I'm trying.
You have please note that you have to share entire screen. Okay.
Yeah, entire screen. Okay.
Yeah, entire screen.
It's taking too much time.
There's some problem with the bandwidth actually. That's yes. Now I can see. Yeah. So you can please go to the presentation directly. Yes. Okay. This is full screen mode and then please proceed for presentation. Yes.
Is it okay?
Yes. Okay. Please present again.
Good afternoon. Good afternoon, sir. Thank you for giving me the opportunity to present my work in this platform. Today, I'm going to present my work on comparison of multivariate behaviors of multifunctional solid solution of lanthanum doped bismuth ferrite and barium titanate at 2 different ratios. I myself is Femina Brahma, Assistant Professor, Department of Physics, Science College, Pokhrel, BTR Assam. So this is the contents of my presentation: introduction, sample preparation, results, discussions, then X-ray diffraction, dielectric spectroscopy, impedance analysis, polarization. And let us go for the introduction. Perovskite is a calcium titanate oxide or calcium titanium with the chemical formula CaTiO3. The mineral was discovered by Gautam in 1839 and is named after Russian mineralogist Count Lev Alexey Perovsky. All the materials with the same crystal structure as CaTiO3. CaTiO3, WiBO3 are termed as perovskites. And in my polycrystalline sample, I have taken the lanthanum, bismuth, iron oxide, and barium titanate in the ratio of 0.5 and 0.5 and prepared the sample. And in this presentation, I am interested in presenting the X equal to 0.25 and 0.05. So this is the mixed oxide solid state reaction route. It is just a map that I have prepared the sample. First of all, we have taken the high purity raw material in the desired stoichiometric ratio, then dry mixing, wet mixing was done with the help of ethanol in almost 4 hours. Then calcination takes place and after the grinding again. And we send it for the XRD and then cold pressing after sintering with maximum density. We have taken the characterizations.
This is just a simple instrument, or we can say that apparatus we have used for the preparation, and the sample was taken in the 1175 degrees Celsius for the preparation, the temperature, and sintered at 1200 degrees Celsius. Then this is the structural characteristics. As we have seen from the XRD, that this XRD analysis is a very significant analysis tool, significant tool for investigating the structure formation prepared by the samples, and it is depicted from both the figure that it is formed in a new phase, and it's a single phase new compound. And when we change the composition, it is also changes. The peaks are changing. Then we have used the Debajyoti formula for finding the crystalline size, and as it is the comparison of the two stoichiometric ratio. So this is the data we have got from our work, that we can see it clearly from the data that D is 23 for x equal to 0.25 and D is 55 for x equal to 0.5. Frequency dependent variation of dielectric parameters. We have taken dielectric characteristics. The large value of the 10 at low frequencies owing to the strong resistivity supplied by grain boundaries and the high energy necessary for electron hopping, but the value drops towards high frequency because less energy is needed for electron hopping. We can see the same pattern in both the samples. And when we did the electrical study, it was observed that the impedance pattern suggests a decrease in bulk resistance with rise in temperature. Negative temperature coefficient of resistance, that means anti-shear behavior, is depicted in both the samples. When we draw the IQAC plot, we are able to see that the temperature is confirmed. The importance of grain and grain boundary participant is demonstrated in this plot, and it's a non-divide type of material. Both are non-divide type of material. The multiperiodic properties is our polarization study. In the P loop, which we got from our samples, are slender in the form and indicating that they have strong ferroelectric properties. In compared to other rarer autoferrites based system in the literature, these 2PR values in both the samples are little bit higher. As it is the multiperiodic study, so we have to take the more properties in the sample. So this is polarization study, and next is the magnetic analysis study. So in this study also, we have come to that it is a non-zero value of the magnetic parameter, indicating that the sample possesses ferromagnetic behaviors. Both the samples possesses. This is the comparison figure of the two materials. The room temperature ferromagnetic feature for all the samples was revealed through image curve. Then the ferromagnetism was basically triggered through the exchange interaction and spin cyclone effect. The overall weak ferromagnetism was due to the involvement of antiferromagnetism channels as well as oxygen vacancy in the system. And this is the summary of my presentation, that both the samples gives us the anti-shear behavior and relaxation in the dielectric at low frequencies because of immobile charge, while higher range, which is quite less because of oxygen vacancies. Non-divide type of relaxation has been seen in the IQAC plot showing depressed semicircles. Ferroelectric nature of the samples are quite very impressive. Compounds show highest 2PR values than any available in literature. Good ferromagnetic nature sample is depicted from ME's hysteresis loops recorded for all samples where the dopants break the cycloid spin structures. And these are the some references. Thank you.
Okay, thank you, Sam, so much for the interesting talk. Actually, and for finishing on time, actually, before time, I suppose. Thank you so much. Okay, so we can have we have like a time for a couple of questions. If there are any, please unmute yourself and You can type in the chat box also if you have some difficulty in your microphone. Okay, seems like there are no questions as of now. Okay, if anyone has any queries, they can also meet outside the Zoom meeting via email or it's uploaded there. So, okay, thank you. Let's thank the speaker. Thank you, Dr. Brahma, for your talk. Okay, so I suppose this concludes session 3 of today. So I'd like to request Dr. Bhattarai, the convener of Physics Frontiers 2024, to initiate this session 4. Dr. Bhattarai, over to you.
Thank you so much. So this is the final session, session number 4 on the final day of this conference. So I would like to have the honor to welcome Dr. Sayan Adhikari, sir. Sir, are you there?
Yes.
Yes,
I'm here.
welcome. Yeah, welcome to this national conference. So I'd like to introduce Dr. Sayan Adhikari. Dr. Sayan Adhikari received his PhD degree in physics from Guwahati University. He spent almost 5 years developing numerical codes to analyze magnetized plasma seeds, and he spent 2 years as a postdoctoral fellow at the Center of Plasma Physics, Institute for Plasma Research, working on numerical investigation and analysis of seeds in communication back out of space vehicle re-entry. And in 2020, he joined Plasma and Space Physics Group as a postdoctoral fellow, the Department of Physics, University of Oslo, Norway. So currently he is working as a research scientist in the Department of Computational Material Processing at Institute of Energy Technology, Norway. So welcome once again. It's over to you, sir.
Thank you, Debajyoti. Thank you for your kind introduction. I know that it's quite late back in India, and I think everyone must be exhausted up to listening talks throughout the day. But I will try my best to bring some interest, and maybe we will try to enjoy. So it's not that heavy science talk. It's basically based on the understanding that you already have, and I will try to make sure that this is less heavy. So this is about a mission I was part of. I think the mission is still going on in the second phase. This is called Emirates Lunar Mission. So this is kind of part of this Artemis program that European Space Agency was running. And from Norway side, so we tried to contribute in development of this rover that we are supposed to send to moon. So there are a lot of things happened, and today I'm not only going to talk about the positive aspects of it, but also the what could go wrong and how we could manage, and how you can still continue the research that that you enjoy every day. So before going into the big thing, let's try to understand some of the small things that you need to figure out for what is going on here. So since we're talking about moon, we also want to talk about the lunar plasma environment. And if you're not familiar with plasma, so plasma is very simple in a way. We consider it's a fourth state of matter. And if you hit a gas with good enough temperature, then it could become completely ionized, partially ionized. The most important part is this ionized particle and the neutrals itself will act as an entity. There are a couple of criteria to call something as plasma, but let's just forget about those. Just think about plasma is like ionized gas. Now, what is different in lunar's plasma? So because lunar, moon doesn't have atmosphere like Earth, so it's very thin, so it gets exposed to the solar radiation very often, and based on the radiation, the things will be completely different. Now, what happens when you put anything inside a plasma? So if you think about as like a sphere or any kind of object, if you put inside plasma, because this plasma is made up positive and negative ions, mostly for negative ions, the electrons are the dominant species. So these dominant species will attack this surface and make it negative. So the general consensus is like, if you put anything inside plasma, it will be negative. But there are other ways of things that we need to understand. For moon, it's not entirely very general. So moon has one side that is exposed to sun, just like Earth, and then the other side will be, in the dark side. So we call it day side and night side. The side that is exposed to the sun is called day side, and the side that is opposite to the sun is called night side. So the night side, things happens extremely normal. So you have this surface of moon that gets negatively charged, and then we have this positive layer of charge, which is basically trying to seal this negative charge effects to the surrounding. But when it comes to the day side, since it's exposed to this UV rays, this actually triggers photo emissions from the surface itself. And because of this photo emission that is being kicked out of the surface itself, the surface of the moon starts to charge positively. So the basic and biggest difference in the day side, you will have positively charged lunar surface, and in the night side, the negatively charged lunar surface. And this particular change in this potential around the surface, or the electric fields in particular, there are a lot of different things happening, because when you are sending a mission to the moon, what you need to consider is like you are sending electronic equipments. There will be rovers, there will be other electronic equipment that you want to put there for human mission as well. We need to also consider the survivability of human there. So the biggest problem with moon is it's a very dusty place. So there are a lot of dust, and these dusts they are not that simple like our earthly dust. They are not neutral at all, because they are living in a plasma environment, so they get charged very easily. So what happens is, when they get charged, they will try to follow the electric fields near to the surface. And these electric fields are not very smooth. So they can be spiral, they can be inclined, they can be very complex. And this complex nature we really need to understand. Otherwise, since we're dealing with human life, because anyway we are trying to send humans and we are trying to build civilization there. So you have seen a lot of pictures of the astronauts, but you might not have seen this kind of pictures where the astronaut is full with dust. Like, we have seen clean pictures, but this dust, they're not simple dust. They are lunar dust, and they are very, very sticky. So we need to find a way how to prevent this, because this not only damages the suit itself, but also it interferes with this life support of the astronaut, because they're trying to breathe. Of course, we have oxygen cylinders, but you also have to exhale the air. And if the veins are blocked by this notorious dusts, then it could be very difficult for an astronaut to survive. Think about not only the astronaut, you have other aspects where we have this equipments, so the electronic equipments, and when you are putting charged dust, so you're also creating short circuits between different electrical equipments. So that could be another dangerous aspect. Then you have the solar panels, which is the primary source of energy on lunar surface. If they are starting to cover with these dusts, then you're also losing a lot of efficiencies of the solar cells. So there are a lot of things to consider when we are sending something on the moon. So we were sending moon to the if we're sending the humans to the moon, we need to send something that is less dangerous. So we always think of rovers. But what are the other problems other than dust? So there are like thermal environments. Since I already mentioned that the moon is not entirely similar like Earth, so it has like very thin layer of atmosphere. So it can be exposed to a lot of UV rays and a lot of sunlights as well. So what happens? The temperature is extremely different when the day side and night side. So from different missions, the Apollo 15, Apollo 17, we could have an idea. The daytime temperature could go up to 137 degrees centigrade, and in the nighttime it could fall down to minus 181 or minus 170, based on the time of the day or time of the year as well. Now this is very dangerous, because if you look, when you buy some laptops or computers or any electrical equipment, you could see the operating temperature range. So basically it could go up to -10, and off it could go maybe 100 or maybe 90. It depends on the electronics itself. But there are very less equipments that could survive this kind of temperature difference. So either we need to find a way how to reduce this temperature effect nearby these electronics, or we need to build some electronics that could actually survive this kind of temperature. So these are kind of challenge when you're sending something to the moon. Now let's talk about the mission itself. So the mission is very, it was part of Artemis mission that maybe you have heard about. So this European Space Agency, ESA, and NASA, they're trying to, build habitat on Moon. So they are sending a series of missions. They're called Artemis. So first few missions are basically to build a survival environment for the human, and then in the later phase we are going to send humans to spend some time, just like we do with this international space stations. So the main organizer, or I would say this control group for this mission, was US Space Agency. But the biggest player of this mission was also European Space Agency, which I was part of when I was working at University of Oslo. NASA was supplying a lot of telemetry data and communication instruments. JAXA, this is a Japanese space agency, they were also part of it. They were helping us to build the lander. And then you have this Canadian Space Agency, and they have French Space Agency, and the iSpace was the company who was providing us the lander itself. And then we have Team Indus from India, who were helping us building one part of the rover itself. And then we have IDLE. It's like a electronics company who were helping us build the electronic chips and this language probes that we are planning to install on the rover. And then we have this mission control company from Canada. So they were helping us to build a AI-based navigation system for the rover, because when you are there, it's difficult to control anything from Earth because there is a time delay. And you also want something, because since we have this large amount of data from other missions, we could also make this mission very successful when we use artificial intelligence and computer vision in a way. So there are a lot of people. That's the summary. So it started in 2017, and then it went on for a couple of years. Because you need to bring different players into the mission. You need to talk with people. You need to find partners. You need to find competent people who is expert in different subject matters. Because this is not when we think about the space missions, these are not just one thing. Because there are cameras, so you need camera experts. There are language probes, so then you need language probe experts. There are electronic chips, which you need to manufacture, because these are special chips that you need to manufacture. So you need people very competent in manufacturing semiconductor chips. Then you need very good material physicists who could understand the morphology of the surface of the moon itself, and how to survive in that kind of environment. Then you're also running several other experiments that needs several other experts. So this, if you try to study any mission, it doesn't contain just like one person or maybe 10 person. It contains like hundreds of people with different competence, and they have to be best in their fields. So this mission was launched December 11, 2022. Unfortunately, it was not a complete successful mission. It was like a Chandrayaan-2. So when we started to descend on the moon, the lander couldn't figure out the altitude by itself. There was some mechanical fault, and then the lander crashed in. But other than that, since the whole mission was really good, so we continued our journey, and we're planning for the next mission very soon. So this is the team that I was leading. I was leading the simulation team, at UIO, which consists of a lot of people from our university and from other universities as well. The mission director, Sebastian, was heading the whole program. So the mission is, segmented in three parts. So we are basically responsible for designing and development of this rover and putting instruments to characterize the plasma on the lunar surface. Then this rover was fitted into this lander from iSpace. And then this lander was put into this Falcon 9 rocket from SpaceX. So it was like 3 months and 5 weeks for mission, 3 months to reach moon, because we are using this low energy orbit to reduce the amount of fuel we could use, and the 5 weeks of operation on the moon lunar surface itself. And this mission, this is in terms of Earth, Earth days. And when you consider about lunar days, so the 5 weeks will translate into only 1 full day and a half of the day. So that's kind of an interesting aspect of it. This was a promotional video. I think I will just skip it anyway. I want to keep the presentation a bit brief. So there were a lot of scientific objectives for this mission. So first and foremost, it was to understand the lunar surface soil, which was a big challenge. We are not only collecting soil, because since you know that you can't bring back anything, so you have to set up a laboratory locally to understand these characteristics of the soil. And this is kind of a very common goal for any lunar mission when you're sending a lander. The next one is the thermal properties of lunar surface structures. So I already explained that there's a huge temperature range starting from the daytime and the nighttime. So you need to understand how this temperature impacts different lunar surface structures. And when you are sending instruments near to these structures, how they impact to the instrument as well. Then one of the biggest and the newest thing was to study the lunar photoelectron, which this is the project I was leading, where we wanted to understand how this lunar photoelectron will impact the rover and its performance itself, and how we could introduce new design changes to this rover to survive this environment and to understand the environment as well. Then there was different material testing with this adhesion testing. That means the one that I was talking in the beginning. So these dust are sticky, so they will stick to the surface. So I wanted to find out how sticky they could be based on the different time of the day and with different lunar plasma environment. Then we have mobility on lunar surface. Since there are teams who were very much interested to introduce artificial intelligence and computer vision to figure out the mobility of the rover itself in an autonomous way. So this was one of my big goals. So in technical specifications, this is a very small rover. We call it micro rover in a way. And this height, length, and width are extremely small compared to any standard rover. The biggest challenge when you are designing such a rover is, everything has to be very extremely small, and you have to be extremely careful what you put in. Like, let me just give you an example. Suppose you want to fit something into something, so you need 4 screws. But if there is a possibility, you can just fit into this machine, fit into this instrument to the main body with 3 screws. That would be a big achievement, because every screws, every gram is a big challenge. You need to reduce as much as possible so that you can fit in more things. The biggest important things were the instruments that were supposed to study things locally. So that was a big challenge. So for us, there were 4 different language probes placed at different altitude of the instrument, so that we could, study this lunar plasma environment spatially. So that's kind of one of the biggest goals of this rover. So to start with, we started modeling this lunar plasma environment in a pristine condition. That means we didn't want to put the rover first. We wanted to study the lunar environment first. And then in the next phase, we will try to put the rover. So this is basically, we have the sun, we have the moon, and we choose a simulation box that is big enough to, fit the resolution that we want. So we have this simulation box. As I told before, that we have this day side and night side. So day side, we're supposed to have a positive charged surface, and the night side we should have a negatively charged surface. So first we start with negatively charged surface. In the night side. So there is no sun, and this is the lunar surface, and we could see over the time, since the simulation is reaching a steady state, we could see this surface is charging negatively, and very soon we could see these numbers are very much in agreement with the literature that you could find on the internet. Now, why it is important? Since you're sending something on the moon and you don't know how things will be, so you need to simulate this kind of environment first. And benchmarking is one of the biggest important factors here. There are a lot of people who worked on this lunar environment, but since you're sending your instrument, you have to test your instrument in this kind of environment, and you can't ask other people who have already done it to make this happen, because there are a lot of secrecy around this kind of missions. You need to compartmentalize information to make sure that things are very much in set. So after the simulation, we could see we have a good agreement. Then we went to this side where we have sun on the other side, and there is lunar surface, and you could see this surface is charging a completely different way. Now, if you try to summarize this particular study here, with finite difference 3D particle cell code, we try to understand how the surface charging will be for different conditions, the day side and the night side. And we have a really good agreement with the literature itself, where the surface is charged negatively and the night side, and comparatively positive in the day side. But it also changes based on the amount of UV and the solar influx you're considering. The thing is, next, the biggest challenge was to model this in finite element 3D particle cell code, because when you want to consider this rover, and when you consider lunar surface itself, the rover is extremely small, and it's in few centimeters, right? And think about the domain size. It's 148 meters in length and height, and we have 37 meters each in other sides. And this is actually the real scale. So you could see this is just a point in the whole domain. But this rover is extremely important. We need to understand how the electric field, works near the surface. So we had to create a adaptive maze around this rover, and we ended up with this kind of structure for the maze. So this is something. So this is also the rover. This is lunar surface, and this is the whole lunar plasma environment with the lunar surface itself. So what we got? We got an extremely complex potential structure on the lunar rover surface. And this is very important to understand, because based on the value that we get at a different time of the day, we have to assume how much dust could be sticking to the surface, and if they're strong enough to disrupt the measurements or to interfere with any cameras or any electrical equipment. So this is what we try to help in design of this rover. So we came up with different rover design and try the feasibility and the survivability of this kind of instrument on lunar surface. As the time passes by, we ended up with a structure that actually could work. This was kind of the final structure. And so this goes back and forth. So what happens? The engineering team, they developed some CAD models of the rover itself. They send us some models. We design in a simulation based on that model, try to find the optimal condition, and try to identify the weak points of this design itself, and see if this instrument could survive when we put all the electrical equipments. And this goes back and forth a couple of rounds, goes for months. And particularly, even for the simulations, this kind of simulations are so big in compared to any kind of ordinary simulation. So using one of the strongest high performance computer in Europe, we ran it for months to have one particular set of results. So to run all of these cases, it took 6 to 8 months, and it was not an easy task. So when we finalized the design, we sent it to the engineering team at MBRSC, and they finally integrated the rover, which was then sent to this iSpace lander. They fit it into this lander itself, and they sent it to the SpaceX for Falcon 9 rocket. But everything was not that smooth. We did our best. We designed, and we delivered the instrument. But the problem was with the lander, it didn't work as intended. But this was the first mission as well, so we expected some sort of failure. So what happened when the lander started to descend on the moon's lunar surface? There was some error to determine how much altitude it is, and because based on the altitude, you have to control the thruster itself to slow down your land. And for some reason, it was not slow enough, so it crash landed on the moon, and that's basically ended the mission itself. So we couldn't operate the rover. But that was there was a lot of good things out of it. We got the second mission where we are going to build the same things with bit upgraded configuration, but we are going to send it anyway. So that's kind of a good thing. From the academic side, there's no end. At least we got a good publication out of it. So this publication will be out very soon. It's in Space Science Reviews. It's a very reputed journal in the space science community. And this will be out very soon. So I guess if you're interested, you could just read the paper. It's a big paper. It's a collection of paper, actually. It's a review collection. And you could understand all sort of things around this mission. So I think you will enjoy it. So I'll not take more time. So that should be it. If you have any questions, I'll be happy to answer.
So thanks a lot, Sayanda, for your wonderful and informative talk. I'm sure the participants will be inspired from your talk. So if there are any questions from the audience.
Thank you, sir. Thank you for your time and wonderful talk. Sir, as you have already mentioned about dusty environment of moon, whenever we say about dusty plasma, we always encounter three types of waves, dust anoacoustic wave, dust acoustic wave, and the anoacoustic wave. I just want to know, I always have this doubt, what are the basic difference among them in terms of wavelength or in frequency?
No, I think it's in the name, acoustic wave has acoustic frequencies.
Yeah.
So, and I think the difference is, do you want to understand the nature of the different kind of wave itself, or do you want to understand how it is important for the mission, or do you think this is any relevant to the mission? I just wanted to understand the question.
Differences are on the basis of like wavelength or frequency, the basic differences.
I think this is a very standard definition. You could also find it on the internet, but the basic difference is the acoustic nature of the wave itself. So that's how you differentiate a normal wave and the dust acoustic wave. And what are the other thing that you said? Can you repeat your questions then?
So actually, I want to know the basic differences between the dust acoustic wave or dust acoustic wave or ion acoustic wave.
Yeah. So the ion acoustic wave and the dust acoustic wave is so the dust acoustic wave is actually you can find it only in a dusty plasma where you have this quasi-neutrality condition satisfied between this dust, ion, and the electron. So you usually have this negatively charged dust. So the electrons are compensated by this negatively charged electron. So you have positive ions, and then you have negatively charged dust and this negative electrons. So this is basically the difference. And they, if they usually they are supposed to show acoustic signatures. So then you get this dust acoustic wave. For the ion acoustic wave, of course, you don't have the dust there anymore. So you only get ion and electron there.
Thank you, sir.
So, any other questions from the audience? So, Sanda, I have a question regarding
sure.
the Langmuir probe that will be used in the rover, the Rashid rover. So, what type of Langmuir probes will be used? I mean, the shape.
It's a cylindrical Langmuir probe. In general, that's the preferred. But there is the one big challenge. This is not a generic cylindrical probe because this lunar plasma density is extremely low. So the Debye length on lunar surface, it varies from 1 meter to 10 meter. So whatever you put there, you have the electron density is so low that you have to build a really large probe in order to collect enough amount of electron to get your IV curve. So that was the biggest challenge for NASA mission. They tried once to send this kind of big rods. The Langmuir probes are very thin wire, right?
Yeah, very thin. Yes.
Yeah, but to measure this electron density and the plasma characteristics, NASA last time they tried with this big rod cylinder. But the problem was, when you are sending this kind of instrument, it's always 50-50 chance that you will able to resolve or not. For NASA, it didn't work. Then we our University of Oslo, we got the contract because we already sent a lot of Langmuir probes to the International Space Station and also to different satellites. So we were already in the forefront of the run. So we got the contract. Okay, we need to build Langmuir probes for this rover and for the Artemis missions itself. So then we developed this kind of new probe, which is called MNLP, multi-needle Langmuir probe, where you don't have only one probe. There are multiple probes, and they're biased against each other in a different configuration. So they could understand the plasma characteristics in a good way. It's not only the probe and the standard thing. So you also develop the firmware around the probe. So you could develop and analyze everything on board locally. So you don't need to extract the data, the time series data or IV sweeps. You can basically do everything within the rover itself.
Okay, fine. The size of the probe is important because when it's much bigger than
it's bigger. It's bigger, and it has like also the several vibrational frequencies that you try, because after a certain time it will be covered with dust. So whenever it detects the amount of dust is too high, then it will just starts to vibrate to eliminate all these dusts.
Yes. So is there any other questions? So if not, let us thank our speaker once again. So thanks a lot, Sanda, for your patience, because we are a bit late today. So it was a very fine session.
I understand. It's always a challenge when you're hosting something online. People have technical problems as well. But I think I'm very thankful to you and to the organizing committee, just giving me the opportunity to say the word. Just one message to the PhD students and the young researchers. It's you can always ask for help to all of us who are working at different places. If you think that you need to understand something, just ask. Just send an email with your query. Just don't hesitate. Like just don't feel something like, wait, is it a stupid question? Because there is nothing called like a stupid question. Everything is a good question. Just ask. Okay.
Yes. Thank you. Thanks a lot, Sanda. Thank you.
Okay.
So moving forward to our next speaker. So it's another plenary talk which will be delivered by Dr. Kamal Saharia sir from Bhattadev University. So Sir, are you there?
Yeah, I'm here.
Yeah. So I welcome you, sir, on behalf of the organizing committee to this conference. So before starting your speech, I'd like to give a brief introduction of Dr. Kamal Saharia. So Dr. Kamal Saharia pursued his research work in plasma physics at Center of Plasma Physics, Sonapur, Assam. So he obtained his PhD degree in physics from Guwahati University. He has research publications in many national and international peer-reviewed journals. Dr. Saharia has an important contribution in the field of theoretical plasma physics. After PhD, Dr. Saharia has joined as an assistant professor in the Department of Physics at NERIST, Arunachal Pradesh, Assam, India. So currently, he is working as an associate professor in the Department of Physics at Bhattadev University, Assam. So welcome you, sir.
Thank you.
Yeah.
Thank you, Dorpan, and especially the organizing committee, Vivek, Kamal, to give me this opportunity to speak. And I will speak on very light way. Actually, as per instruction, I will just have an overview of the things. And my talk will be on prospects. Is it visible? Is my screen visible?
Yeah, yes, sir. Yes, sir. It is visible.
Yes, sir. Visible, sir.
Yeah. After this Sayan's talk, Sayan has given a very heavy, I think, heavy talk. This will be a very light one, and my aim is to just to attract our new researchers and students to the field of plasma research, because it has now lots of applications, as you will have to see. So let us first start with this: why we are studying the plasma and what it is and what is capability, what we can do with this plasma physics. So it's compared to this condensed matter physics or a simple astrophysics, you can say this plasma physics relatively new one or fast growing branch of physics, because earlier it was only the gravity. If we say space, it's gravity things, or astrophysics, we call this gravity things. Now for the 21st century, it is the plasma and electromagnetism which control or the dominating field. And another thing is the control thermonuclear fusion reaction. That's one of the prime interest present days, and which will be your plasma-based thermonuclear reactor. That I will cover a little bit. Then plasma physicists were among the first to open up the new development or in the nonlinear dynamics, chaos and nonlinear, because plasma is a highly nonlinear, because of its self-consistent electric field, it's a highly nonlinear. And the this nonlinear dynamics has got a boost over this plasma physics. Then industrial implications like diverse areas like IC fabrication, thin film, display systems, nanoscience, bioscience, and even in medicines. And in these sectors, it is now very much applicable. Present scenario demands a large number of scientists and engineers, as you have said, even in the lunar mission, we must have the plasma physics, because to have the parameters where the temperature of these ionized gases. So we have in various diverse fields, we require plasma scientists and engineers. Since that is why it is in our regular curriculum now, many universities introduced recent years. So, but even if it is a new field, but the fundamental these areas like electrodynamics, statistics, and kinetic theory, fluid mechanics, nuclear physics, these are the things that we have to include here in studying the plasma physics. And there's a basic flow chart how we can have the plasma. First, we may have the solid, liquid, gas, and then we have the plasma, and which will be an ionized gas. But we don't have ionized gas, but it has a difference from the gas property. In the main thing is that it has the collective behavior, and which is dominant over the short-range binary collision in case of a gas. So, and basic criteria is it has to be quasi-neutral, as you know. And this is a picture from a gas discharge tube where we can see the positive column as the plasma or ionized gas. And for a simple comparison, how it differs from a gas. And in a gas, it's a binary collision, as I told you, and here it is a collective motion. And it's because of its long-range electric and magnetic field. And it's a non-conducting in case of gas, but it will be highly conducting because it's a charged particle. And another important thing is that generally when we say in kinetic theory or in simple gas dynamics, we take them as a Maxwellian type. But in plasmas, it often deviates from the Maxwellian, non-Maxwellian, or you can say non-thermal, thermal, different deviations may be there. And in our research, in my domain of research, also deals with this non-Maxwellian type, or where the system or plasma behavior, the particle distribution deviates from the Maxwellian. And this is one of the very important, or you can say, signature of my research, our team research. And in the fluid, gas, then we treat them as a fluid. No? So it's a single fluid you have to treat. But in case of plasma, as it may be multi-component, that means electrons, ions, we can say positive charge, negative charge, but you may have the different types of positive charges, you may have the different types of negative charges. So you should treat them as a multi-fluid, and that is why we have to modify the equations accordingly. Then where from this a little bit of history. This is I'm just have a look on it. This positive column of the gas discharge tube, where from the tank this Langmuir and Tong gave the name the plasma. Plasma is a positive column region of the discharge tube with almost equal number of electrons and ions. This was the first introduce the name. They were the first to introduce the name plasma. Because it was earlier there in the gas discharge tube, always there the plasma protection is there, but the name plasma was given by Tong and Langmuir. And this plasma temperature and densities ranges from relatively cool to this very high, very hot. So this ordinary solid liquid gases, both electrical neutral or too cool or too dense plasma states. So we may have different ranges from cold to hot plasma, and from there we can have this diagram like the density and temperature, the two main parameter. That is for say fusion plasma, we have the very high temperature and very high density, 24 or 10 to the power 7, 8 electron temperature Kelvin. And then from ionospheric, it's a very we can say low density, low temperature plasma in case of space. But we have the fusion plasma, and the main parameters are the temperature and the density. And other parameters is another parameter that is for experimental or any theoretical purpose. We must stick to this parameter. This is Debye shielding or and represented by the Debye length, and then plasma oscillations. And all these parameters we can have from the Langmuir probe. In simplest probe was the Langmuir probe, that we can determine the plasma parameters. So now how we produce the plasma, this energy needed. Now some energy we must have to ionize, we must have ionized form of the gas. So we have to produce the plasma by means of this thermal, electrical, light. That way giving some extra energy, we have to produce plasma. And necessarily occurring plasma, that is why we don't have in our Earth, because they will quickly recombine to the natural gas, because our Earth is not so high. No, atmospheric temperature is not so high, but still we can have artificial produced atmospheric pressure plasma, which is in experiment application point of view, we have to produce them by giving some extra energy. So plasma research, this greater understanding, as I told you, is all more than 99% of the universe is a plasma state. So knowing the plasma in full, we can understand more and more about the universe. So it also provides many practical uses like new manufacturing technique, consumer products, prospects, and abundant energy that I will cover a little bit. Then nowadays, this plasma liquid interaction, or you can say any surface interaction, surface. Okay. Whenever we produce plasma in laboratory, it contact with the surface of the container, so that arises the seed, and lots of research were done on the seed, how to control the seed parameters to improve the confinement systems that way. But plasma liquid interaction is very less studied till now, and it's getting more and more attention nowadays for application ranging from water treatment, nanometal synthesis, polymer solution treatment, chemical analysis, food processing, and even agricultural products also, and then plasma medicine. So let us move. So this is all about some intro my plasma research and how we study them. There are two ways, that is, as always expected, this is experimental as well as theoretical. So in theoretical, we can have the analytical or simulation type, and all things has to be done to have a concrete knowledge of the system or configuration. So basically, in theoretical, as I'm doing my research, my team is doing research in theoretical one. So I can say on this theoretical a little bit, single particle and statistical approach to fluid, single fluid theory MSD, that's called MSD. And then for simulation part, kinetic simulation, which is done on the basis of class of equation. And then fluid simulations, MSD simulation or fluid simulation, and then hybrid, there may be mixture of PIC or fluid. So these are the equations that control these theoretical formulations: continuity, momentum, Poisson equation, class of equation, and along with the distribution function I am giving for particle distribution. But it may be different for different purposes. We may have to take different distributions. Okay. So why so important? As I told you, starting from the radio communication, we have to know the ionospheric electromagnetic wave propagation. So from that way, in the astrophysics, most of the university plasma state, so understanding astrophysical phenomena like sunspot, solar wind, star formation, etc., requires better knowledge of this plasma physics. And then creation, another important thing, that is your control thermonuclear fusion, as I told you. So it's we require an alternative source of energy, and that will be hopefully the thermonuclear fusion based reactor. And the thing is that it is not so simple as we think over it, because the confinement, main problem is the confinement, how to confine a plasma for a sustainable time, so that the more and more fusion takes place. And fusion this is trying to trap the plasma in the magnetic field, that is your tokamak type, and investigate problem of plasma instability, because this plasma is a highly nonlinear and it's always develops lots of instability. So the theoretically as well as experimentally, we always have to take care of these instabilities and thus boundary value problems. Then this is about the confined plasma, but laser physicists are also doing the same way. We are having a system like inertially confinement for fusion. So it's a laser plasma based one, and this can be also a very good project that is going on. And presently, plasma physics is challenging field of research in which exist many problems and few satisfaction is important. And that is why many researchers and technologians are interested in this field. This is a view of the aurora, that is naturally occurring plasma in our Earth. So, as I want to expose some different fields which can be taken by the students and researchers in this, if they are interested in this field. And then these are some, as I mentioned, basic plasma physics that includes the waves, instabilities, like things. Then beam interactions, there's a high nonlinearity. And then plasma diagnostics, plasma-based devices, plasma seed metal interaction, that is our interest of research basically. and even space plasma. Then plasma astrophysics, plasma-based fusion, magnetic confined plasma, inertial confined plasma. That is tokamak based, and this is your laser plasma. And then dusty plasmas. And why all this research? This is another figure that I'm putting. Why this we are heading or giving more stresses on the field of plasma in terms of fusion power. So because of our natural or non-renewable energy going to decay that will begin around 2050, but our consumption requirement will be high and high. So we must have an alternate way to harvest energy for our future generation to sustain. This figure indicates that. Then these are some basic research plasma field, but in technological point of view, technologically we can have the technology means, as I mentioned, some of them are plasma processing, thin film, plasma-based lighting system, plasma chemistry, plasma spray and bulk material, then display systems, environmental health application, material synthesis, switches related to the electronic uses we can have. And for that, let us define some terms like the thermal plasma, cold plasma. These are the two plasma that we require for your plasma technology. So these are basically artificial plasma, and natural plasma, that is, for example, we have from the sun, then our atmosphere interaction. This we can say natural occurring. But for tokamak or fusion reactor, or say we have the liquid plasma interaction, plasma liquid interaction. In that case, we have to produce the plasma artificially. And depending on the use, we may have the thermal plasma that can be used to destroy solid, liquid, and gaseous toxic materials or molecules, the general anti-corrosion, thermal barrier, etc. And cold plasma can be used for surface modification material ranging from simple topographic changes to creation of surface chemistry and coating that are radically different with respect to bulk material. So, but the thing is the complex interaction or in the interface. At the interface, there will be complex interaction between them. And for solid, it is the seat, but liquid, the seat will be a little bit different because there will be a chemical reaction network will be there, such that it will have electrons, ion, radicals, and photons will be generated, and in they will inflow, outflow will be there. So there will be a complex reaction network will be generated. Okay. How we can produce plasma in the laboratory? So these some of the methods is low pressure electrical discharge. That means we have mostly in the laboratory for simple experiments, we make use of this low pressure electrical discharge. Then RF capacitive discharge, RF coupled plasma, microresonator plasma. These are some methods to produce simple experimental plasmas in the laboratory. And the beauty of this is that the plasma parameter is highly dependent on the method of plasma production. Thus, depending on the method of creation, plasma may be high or low density, high temperature, low temperature, or steady state, transient state, stable, unstable. That way, we can have different types of plasma depending on the production. And but challenges is with the confinement. As I told you, you cannot confine a plasma. It will just recombine again with atoms or molecules. So confinement, we can have simple in higher secondary or degree, we have the basic plasma mirror systems we can have. This is the simplest idea that we can confine a plasma. And in laboratories, generally we use the cast type magnetic field, that is north pole, south pole. Currently we have in a cylindrical shape. We can have a almost uniform plasma in the core. And then in tokamak, we have the colloidal and toroidal fields across, and we have an almost uniform plasma circulating around this in the center. And for technology purpose or in applications, we have the plasma arc or plasma spray. That way, we can have produce the plasma by plasma torch or plasma arc or in plasma spray process. So for confinement, when we say confinement, sun is also producing the fusion reactor, but we don't have to confine here because the confinement here is a gravitational, one high temperature, so no problem. And but in laboratory we have to confine them magnetically or inertially. So here we can say gravitational, magnetic, or inertial confinement. That is laser produced plasma. We have the inertial confinement system we make, and to have the fusion reactor, we have to have the in the laboratory the deuterium and tritium reaction will do for our future fusion reactor, and for that we'll have the this magnetic confinement system only. And for future energy that and this why deuterium and tritium. Deuterium can be distilled from seawater because it's only isotope of water, and while tritium can be produced from lithium, but lithium is also limited in this volume. So since the ocean contains enough deuterium to power fusion for billions of years, this fuel supply is for all practical purposes unlimited. So energy security will be there. But what about the lithium? So for lithium, it is we can have as a blanket. So there is another way. Dissolute tritium will be self-produced by the lithium blanket in the this tokamak reactor or ITER project that I'm going to say a little bit, and then no greenhouse gas emission. So they are non-radioactive, and only when the reaction will be started, then it may be, but it will be no risk of the greenhouse gas emission, and minimum radioactive waste product will be there. And there are lots of many nuclear fusion projects are around the world going on, which are including the ITER. ITER is a International Thermonuclear Energy Reactor built in France, Cataracy, and we should say proud that India is also one of the contributing country in this ITER project. And the building or the assembly portion is almost done nowadays. ITER has completed with its structure, but still the first shot or plasma production we can expect around 2039 only, because it has lots of issues to be handled before first shot. But nowadays, probably a month ago, we have heard about the Chinese East reactor and HL2M reactor. They have reported the long pulse length. That means they can confine the plasma for a remarkable time, so that they are very much successful in confining the plasma for more and more time, so that the fusion reaction can be done with an appreciable time. And this is the schematic diagram of the ITER project. ITER. This is a very high building. You can say 7-story building height, and this is your donut-shaped magnetic coils are there, and inside it the plasma will be produced inside this plasma, and assembly part is already done. And next the shot they will take around 2039 only. And the purpose of this experimental reactor is to study whether it is feasible or not. Feasibility, mainly the feasibility study. You cannot say after making this we'll have the energy. It is only feasible, whether it is feasible or not, or how we can extract heat from the reaction. That all experiments will be done through this experiment. And main thing is that plasma, as we are in the Earth, so plasma will not occur naturally. So we have to give energy to produce plasma. And if we are giving energy to produce plasma, what will be the output? So output, we must have to give high Q value, then only it will be fruitful. So in ITER, it is 70 megawatt input and 500 megawatt output it is proposed. And around 300 to 500 seconds time of this fusion will be last. That is a proposal, and we must have a reactor which will give you more Q value. It means output power has to be more and more. Then only it will be a successful one. And then, as I told you, this lithium blanket here in the ITER project will be lithium blanket, and this will absorb high energy neutrons. So, and from fusion reaction to make more tritium fuel. So it will be tritium will be also a self-sustained one from the lithium blanket. So this is one of the another challenge to be successful in this experiment. They are doing on it also. Anyway, let's come to the next applications. So electronics and semiconductors, the researchers are doing more and more of this with this plasma-based technologies to have more enhanced applicability things. So just like plasma cleaning, so here it is decontaminating the surface with the help of this plasma-based systems, and when fabricating electric circuits, and then plasma coating. Plasma coating is ultra thin. If we require some ultra thin layers of different polymers deposited on surfaces, so we can use the plasma coating. Actually, here using plasma is the thing is that we can control the things very much precisely, and that is why plasma-based applications are more reliable in the microscopic point of view. And then plasma etching. So to need the if we need to remove some some metal from your surface, or then dry etching comes in surface etching on a molecular level approach, especially suited for semiconductor, medical, and painting technologies. And the for medical purpose, it is also nowadays very much popular. So here we use the cold atmospheric pressure plasma. So this cold atmospheric pressure plasma, generally it's a small torch type or arc type, you can say, and used for treatment of viable tissues, or does have become a focus in medical research for this present day. And plasma pen is a plasma pen. So this sort torch type thing, and used to medical applications such as treatment of skin fungal infection, accelerated healing of wounds, accelerated coagulation of blood. And then compact device can be highly portable, and emergency use we can have it. And this high temperature plasma are used for sterilization. So medical sterilization purpose, this high temperature plasma is also used. Then plasma display, you have already know this plasma TV and all this displays. And plasma thrusters, this is another very interesting topic nowadays, plasma thrusters, because we have the rocket propulsions nowadays, and we require more and more efficient rocket propulsion, so that it is more efficient and long lasting, and it can go beyond our horizon, say we can say nowadays. So this plasma based propulsion system, actually this is based on some we can say double layer type or helicon thrusters heard about. So this double layer type, so it's a particle acceleration will be take place, and this will give you some thrust on it. So this plasma thruster is another very important applications for nowadays for our future rocket propulsion systems. And I'm keeping a term plasma chemistry here. As I told you, the plasma liquid interaction, plasma solid interaction is a seed, plus plasma liquid interaction, it's also you can say in broad sense a seed formation, but here we can put them in a separate branch, that is plasma chemistry. And I have not done much on it, and I invite anyone, if anyone is interested in the field, so please help me, because I want to go inside this plasma chemistry, because plasma liquid interaction is very less attained field of research nowadays, but it has immense prospect on this field. So as I told you, water purification, decontamination, but for large scale, it is not implemented till now. And cancer, killing infected cancer cells, but they are not so advanced in the field of medical also. So there are lots of research needed in this field. So anyone interested, they can do research in the plasma chemistry field of research. And then in agriculture also, we can have it in enhancement of germination and growth of plant seeds. So they are basically this plasma liquid interaction is boundary interaction, but it will be reaction network will be there, and that has to be understand a lot on it. And to say some of my research domain, what we are doing or our team is doing. So I basically do some space plasma in my earlier work. I did some work on space plasma or space plasma related coherent structure. That you can say electron holes, double layers. Double layers means some charge separators which can accelerate the charges, and then electron holes, some vortices type things, solitons, super solitons, rogue waves. These my students were doing. Then plasma seed. So here I did some PASOP simulation where we can see the trajectories, how the some instability grow to have creation of some electron holes or double layers in plasma. Basically, we did in the space plasma related things, and we compared them with some satellite data. So this shows the electric field and magnetic potentials. This spike shows the electric field and potentials, and which matches with the observational data in space. This may be helpful in space observation. And as I told you, most of the cases, plasma, space plasma, as well as in some cases laboratory plasma, they may deviate from Maxwellian behavior. So what they can behave? They can behave as a high energetic tail. They can expose them as a high energetic tail because they have the high energetic particles are there, which doesn't fit in the Maxwellian behavior. So in that sense, we have to have some defined distributions. And Charlie's distribution, Charlie's non-extensive distribution, one of the finest one to deal with this type of non-Maxwellian behavior particles. And in our team uses this successfully and publish a lot of few publications on it also. And here another work, that is your seed. My work was solid and plasma interaction. So it is your seed, and we generally did on ion seed. Ion seed, that is, we have the electrons, ions in the plasma, but in the seed region, the ion density is more than that of the electron density. So quartz symmetry breaks, and this seed behavior, how we can control the seed, how the parameters dependence on the seed, that were our study in different configuration of plasma. So here are some of the variations, how we can vary the seed parameters or seed thickness with the parameter variations. Just like here we have took the results from 2 electron temperature plasma. That means we have the hot and as well as cold electron temperature plasma, and hot electron we took them as a non-Maxwellian, that is treated by the non-extensive distribution of plasma. So we can see the variation of different thickness of the seed with the parameters and along with the non-extensive parameters. And this work was done by Baruah, my PhD student. And this is another work that is done by my student Kamal, Dr. Kamal, presently working in your college itself. And he did some work on super solitons along with rogue waves, soliton supersoliton and rogue waves. And he also uses nonlinear Schrödinger equations and non-extensively also. So these are another findings, finding the ranges where the double layer will go from the soliton to double layer to rogue wave. That way he studied the different regime of the domain of these coherent structures. So finally, I invite all of you to do research in the field of plasma physics. And some of the institutes in India that you can go for is the IQAC, then Central Plasma Physics nearby, ISST, BRC, SNP, and many other universities. And also nowadays in Bhawanipur, Kamal is there, and in Darpan is there, and here in Bhattadev, I am here. So anyone can come and do research in the field of this plasma physics. Thank you. Thank you, Darpan.
Thank you, sir. Thanks a lot for your time and nice presentation about
Thank you, manager.
plasma physics. Yeah. So it is open for discussion, and if there are any queries or questions from the audience. So, sir, I have a question. When you talk about the plasma confinement or magnetic confinement and plasma fusion, so as we know that the Q value, that is the output energy per input energy, is not achieved more than 1 till now. So
yeah, not more than 1 till now.
Yeah. So
and morely it's a confinement time. In China, recently they have reported around 120 second time. No? But we more the time we can confine, more fusion will be take place, and our Q output will be high. That is the idea.
Yeah. Yes. So that was my question. What are the basic parameters which are dependent on the Q value, so that we can get more than 1?
What are the different parameters? Okay, that has to be optimized. That is why the construction is over. No, ITER construction is over. Still, they will took the first shot on 2039. Yesterday they have announced that they will take the first shot on 2013. Earlier it was just before month, it was 2035. Now yesterday they have announced it 2039. Why? Because they have to set all the parameters. I didn't did much on it. I just took a small project on it in my postdoc. That was scaffold layer. It is from where we can extract the heats and for our useful purpose. So I can't say much on it. What are all the parameters that confinement time will be increased?
Yes. Anyway. So yeah, so the plasma physics is going towards basically for the fusion thing, so that we can get energy out of it. So what do you think, apart from the magnetically confined plasma, are there any other possibilities?
Inner cell confinement, that has the also capability. National Center for So that they are also doing parallelly. Inner cell confinement, that is laser produced plasma. They are also doing parallelly on it. How we can fuse, make fusion, and that can be used for useful purpose. Because inner cell confinement, that is for inner cell confinement plasma. So they don't require magnetic confinement. They're laser produced plasma. So they are called inner cell confinement plasma. So I have not done much on it, inner cell confinement plasma. But there's two ways. One is your tokamak base, another is your inner cell confinement base.
Okay, sir.
Yes.
Thank you. Is there any other questions from the audience?
Thank you, sir, for your time and the beautiful talk. If there is no questioner, we can move to the next session then.
I have to answer my.
If you have time, I would like to request you to share the next session.
Yeah. Okay. Thank you. How to answer my screen? Just cut it or?
Yeah. Yeah.
Okay.
Fine.
Okay.
So moving forward to the next session, the participants. The next participant will be Debajyoti Kolita from North Guwahati College. So Debajyoti Kolita, are you there?
Yes, I am here.
Yeah, please share your slide.
Okay.
Okay, so I'll briefly mention the chronology of the talk now for this session. So Debajyoti Kalita will present first, followed by Biswajit Dutta. Then Hitendra Sarkar will present, and finally Prince Das and Krishanta Chutiboy. So this is the chronology. We have last 5 talks in this session. Okay.
Okay. Good evening, everyone. I'm Debajyoti Kalita from Bhattarai College. Today, I'm going to show you one of my ongoing work, which is the excitation of dust comets in strongly coupled astrophysical clouds. So these are my presentation outlines. So introduction is that dust meteor clouds, we all know that are the dense sides of interstellar medium, which is a mixture of dust and gases, and stars are formed in such DMC by a well-known process called gene stealing. If you consider a spherical cloud, because of dust grain cell gravity, gravitational force act in a inward direction. As a result, cloud get compressed and outer thermal pressure act in the outer direction. And when these two forces are balanced, we call this as hydrostatic equilibrium. If somehow this inward gravitational force overcomes this outer pressure force, then gene stability will occur and a protostar will be formed. And we can say that in that case, the mass of the DMC should be greater than critical mass, which is known as Jeans mass. Again, we know that dust to gas ratio in the DMCs differs from canonical ISM value of 1% to 20 to 30%. This is because of larger size dust grain present in the dust meteor cloud, for which the cell gravity comes into play. This abundance of dust grains, as a result, the abundance of dust grain varies locally due to various dust accumulative processes, and such denseness in a cloud can be defined by a parameter called dust fugacity, which physically signifies how compact a system is. And depending on this dust fugacity, this dusty plasma can be divided into 3 types: tenuous dusty plasma or low fugacity region, dilute dusty plasma, or moderate fugacity, or dense dusty plasma, which is a high fugacity region, or you can say high dense region. The fugacity for various systems are shown here. So what is a dust Coulomb wave? Since our aim is to see the excitation of dust Coulomb waves, so generally dust Coulomb waves are excited in a very dense system having surface dust fluctuation. If there is no surface dust fluctuation, we would not get this dust Coulomb wave. Here, what happens in such system when the dust intergrain distance is very much less than this detail length. In such cases, dust Coulomb interaction dominates over the this dust thermal pressure. In such cases, the restoring force is provided by this Coulombic pressure, and inertia is also provided by the dust grain. Another important properties of dust is the Coulomb coupling parameter, which is the ratio of dust potential energy to the dust thermal energy. And based on that, dusty plasma can be again classified into strongly coupled, weakly coupled, or viscoelasticity, where it shows the property of both the solid and the liquid. Various author has done studied this dust Coulomb wave in a weakly coupled plasma in the high frequency region, and they had found that this dust source dynamic excite dust Coulomb waves in the ultra low frequency region. But such modes are also reported to exist in strongly coupled laboratory dusty plasma, but theory of that has not been done for a longer period of time. Recently, the dynamics of the such dust Coulomb wave and dust frequency wave in cell gravity magnetic viscoelastic spherical DMC is studied both in the weakly coupled limit and strongly coupled limit. But complete analysis of such spectral stability properties of dust Coulomb wave is yet to be done, and our motivation lies at in this point. So we have constructed a physical model, which is a spherical DMC composed of electrons, ions, and negatively charged dust, and we consider these electron and ions to be weakly coupled and kappa distributed. And these micron sized dust grains are strongly coupled. At first, these neutral dust particles are in the sea of electron and ions. Later, this dust becomes electrically charged due to the continuous inflow of electron and ion current onto the dust grain. As a result, the dust surface keeps on fluctuating, and we get to see this dust column wave. And we also included here the effects of cell gravity, viscosity, and azimuthal magnetic field. And we consider these multi-fluids are initially in a hydrostatic homogeneous equilibrium. So, according to this, we have developed our governing equations are kappa distributed electron ion number density, and this is a continuity equation for flux charge density conservation, momentum equation for force density conservation, where this term represents this inertial term, this term represents the elasticity term, this term represents the viscosity term, this is the inertial term, this is the pressure. Electrostatic force term, this is gravitational force term, this is the Lorentz force term. Similarly, this is the adiabatic equation of state. This is the magnetic field of induction equation. It explains the evolution of magnetic field as it propagates through the medium. This is the Poisson equations relating the gravitational Poisson electrostatic potential to charge density field. This is a Poisson equation which relates gravitational potential to the mass density field. Again, the dust charge dynamics is explained by the charge current balance equation by this equation, where we calculate the kappa distributed electron and ion current by orbital limit theory, and is given by these two sets of equations. Then we do the radial wave analysis. We allow this relevant parameter of the system to undergo small scale perturbation F1, and we allow the perturbation to evolve as a spherical wave. Then we apply this radial wave analysis on the governing equation. Then we get this dispersion relation, where this CD is the dust acoustic wave speed, omega CD is the dust plasma oscillation frequency. This is kappa distributed wavelength. It is Jeans critical angular frequency. Is the Alban wave velocity, and del is the ratio of dust charging frequency. Then, since our interest lie in to see the excitation of dust column wave, we have to accept this assumption that is the wave frequency is very much less than the dust frequency. In the opposite region, if we consider the opposite case, then the dust surge will remain practically constant. Then we will not see the dust column wave, but only the dust acoustic wave will get excited. So under this condition, this dispersion relation is reduced to this form, and after that, in the strongly coupled limit, which is under this condition, reduced to this form. And since dust column wave excited in the high frequency region, for high frequency region, this is the condition, and we obtain this dispersion relation, where we see CDC is the dust column wave phase speed. It is interesting to know here that dust column phase speed depends only on the grain meter. Grain parameter.
Sorry to interrupt. You have 2 minutes more, Drupa.
Okay, I will make it short. Then, if we see these two relations, it is observed that there is no any deviation, but a new scale length appear, which is we know called the modified weaknesses radius, and it is given by this formula. Then we normalize the dispersion relation by using this normalization scheme, and we get this normalized dispersion relation. And from this dispersion relation, we can calculate this real frequency, growth rate, phase velocities, group velocity, phase dispersion, and group dispersion. And again, from this feature, we can see the stability of a system, and for that purpose, we do numerical analysis. These are for that we took these input values. Here we have some here, and then these are the results. Here we saw that the profiles of real frequency growth rate of the dust column with variation in weight number for different ZD values. We see that with increasing ZD values, this way omega R increases and omega decreases. This means that with increases, this means that and it shifts towards the low K region. This means only the long wave and gravitational undergo active growth. Again, we say with the increased dust charge, the Coulomb outward repulsion increases, opposing the inward gravity. So it tends the system towards stability. Again, from figure 2, we see that with increasing ZD value, this group velocity increases and shifts towards the low K region. This means the longer wavelength fluctuation travel faster than the weaker one. As a result, the disturbance that we have applied to the system get dispersed or dissipated. Again, from the group dispersion formula, we see that the negative value, the peak are towards the negative value. This negative value of this group dispersion implies normal dispersion. Normal dispersions means there is the dispersions of energy in the system, which leads the system towards the stability point. So from similar profiles are created by varying this electron number density, ion number density, magnetic fields, etc. And from there, the conclusion that can be drawn are the equilibrium electron number density, dust charge, azimuthal magnetic field, a case accelerating, stabilizing, and normal dispersive agent to the DMC stability. Similarly, electron ion number density, a case decelerating, decelerating, and enormous dispersive agent to the DMC stability. And such analysis can be extensively useful in the star formation processes behind in the dense RCCW 38 region of the dark DMC. Thank you. Hello. Hello.
Yes. Okay. Thank you for the beautiful talk. Dr. Saharia, if you have any comments, you can mention. Dr. Saharia, are you there?
Yes, I'm here.
Okay.
Darpan. Yes.
Yes. Do you have any
Okay,
comments
thank you, speaker. Any question from the audience, listener? To Debajyoti? Debajyoti? Yeah, Debajyoti. Any question? Okay, Debajyoti, just tell me, have you taken consideration this dust charge fluctuation in your research?
Yes, sir.
And how it affects your results? Dust charge fluctuations? Just in a simple way, just tell me how dust charge fluctuation affects your results? Or it may affect on how it may affect your results.
Dust charge fluctuation results. It results. So that is by including this through omega lambda r. If you see here, this dust charging ratio is there. By changing, if we change, then this parameter will get changed, and as a result, this omega will be affected. But I have not tried on it, but I have not changed this dust charging frequency till now. The result of that I have got till now, I have seen. But when we change the dust charging in term, then this equation will get affected through this lambda r only.
Okay. And that means it will affect your results. Okay, this is enough.
Yeah.
Okay. Okay then. Any question? More? Any more questions? If not, thank you. Thank you, Debajyoti, for your presentation. And our next speaker, Biswajit Dutta.
Yes, sir, I'm here. Am I audible, sir?
Yeah, you're audible. You can share your screen.
Yes, sir. Yes. Sir, is it visible?
Yes, it is visible. And you may please proceed. You can do it in full screen mode and then you please proceed.
Good afternoon, everyone. Before I start my talk, I must thank the organizers for giving me this opportunity. So I am Biswajit Dutta. So I'll be talking about Wakefield oscillations in complex plasma. So this is the outline of my talk. And to start with, dusty plasma physics or complex plasma physics. So as Saharia sir has already mentioned about plasma physics. Now this dusty plasma or complex plasma is a very important field of research in plasma physics since early 90s of the last century. So you can see it is very recent. And we can define a dusty plasma as a multi-component ensemble of electrons, ions, neutrals, and small particle of solid matter. Actually, this small particle of solid matter is also called dust. Now, whenever this dust becomes a part of the plasma environment, then the dynamics of the plasma system becomes very complex. Therefore, a dusty plasma is often termed as complex plasma. Now, these dust particles can be micrometer to nanometer sized. Some examples are silica, carbon dust. So actually, in most of the laboratory experiments, we use generally silica particles. And as compared to the plasma species like electrons and ions, these dust particles are highly massive. They are also highly charged. Actually, whenever dust becomes a part of the plasma environment, then they start showing collective behavior. And because of the constant bombardments of electrons and ions onto the dust surface, the dust particles will be eventually charged up. And at a steady state, it can acquire a very high amount of charge, up to order of 10 to the power 3 to 10 to the power 4 times of electronic charge. And since electrons are much more mobile than the ions, and therefore, this in a typical laboratory conditions, these dust particles will be negatively charged. Now, these dusty plasmas are quite ubiquitous in our universe. So, as we have seen in the earlier lecture, so these dust particles can be found in solar nebula, planetary nebula, circumstellar rings. Similarly, in laboratory systems also, excitation of various wave modes, then Coulomb crystal formation, then even in fusion reactors also, we can find dust particles. So, therefore, knowing the dynamics of dust particles in various environments is very, very important. So here, our prime aim is to calculate or see the influence of a transverse magnetic field on wave field oscillations around a charged dust grain in complex plasma. Actually, as we know, this magnetic field is a very essential ingredient of all this cosmic environment, starting from this interplay medium to the circumsolar rings. So the interesting thing is that in these environments, plasma, dust, and magnetic field coexist. So the study cannot be completed if we do not consider the effect of a magnetic field. So therefore, we want to see the influence of a magnetic field. Now, as Sir has already mentioned about the complexity of a plasma system. So dusty plasma in the same way is very, very complex. Now, in this complex system, the realization of correct and appropriate interaction potential is one of the biggest challenges, because in a dusty plasma system, all the time ionization is going on. The dust charge is not fixed. And because of the electric field present in the plasma chamber, there will be some flowing ions. Then we can apply some external fields like magnetic field. Now, in presence of all these physical effects, the form of the interaction potential will be very complex. Now, why we are interested to find the effective interaction among the dust particles is because here you can see various properties like phase tension property, then transport properties like transfer of mass, momentum, energy, then self-organized structures like void formation, lane formation, Coulomb crystal formation, then rheological property. Actually, in rheology, we study how matters deform under the action of different fields. So all of these properties can be correlated, or this can be controlled with the help of effective interaction potential among the dust particles. So therefore, here we want to calculate the effective interaction potential in a typical laboratory conditions. So this expression will give us the most simplest interaction between two dust particles. So it is also known as equipotential, and this is nothing but just the skin Coulomb potential. The skinning is because of the breakdown plasma particles. And now to calculate the final expression for the interaction potential in the typical laboratory conditions where all these physical effects are there, we use the general expression for potential due to a test particle in plasma. It comes from electromagnetic theory. Here QT is the dust charge and K is the wave factor for any electrostatic fluctuation in the medium, and epsilon omega K is the Dielectric response function. Now this Dielectric response function is very, very important. Actually, this means when we give some perturbation to our plasma system, then immediately the plasma particles will respond to it, and depending on that response, we'll have a plasma dispersion function. This plasma dispersion function can also be written in terms of different susceptibility, like electron, ion, and dust particles. Now, here we introduce something called ion wave or wave potential. So it comes from the flowing ions. Now, if we consider a laboratory dusty plasma system, then these ions effectively seal the dust grains and give rise to a skin Coulomb potential or equipotential. I have already mentioned about this. And if again I consider these dust particles are levitated because of the this balance between gravitational force and electrostatic force, then in presence of these negatively charged dust particles, these ions are flowing because of the electric field, the trajectory of the ions will be modified. Now, because of this modification in the trajectories, there may be some excess accumulation of positive charges just behind the dust grains. This excess accumulation of positive charges, actually here we can see in this diagram, this ion focusing region or excess accumulation of positive charges will act like a medium or will behave like a medium between two negatively charged dust particles. So now here in this diagram, we can see if I consider this full excess accumulation of ion focusing region with a single charge, positive charge, then the competition will be between these two force vectors. One is F of A, one is F of R. What is F of A? F of A is the attractive force between the positive space charge region and the negatively charged dust particles, and F of R is the repulsive force between two negatively charged dust particles. Now, when F of A exceeds F of R, then these negatively charged dust particles will be attracted towards this space charge, this positive charge, and then that's how, in a typical laboratory dusty plasma, some vertical cylinder structures can be formed. So now to explain this kind of vertical cylinder structures, we need the attractive potential, which is known as ion wake or wake potential. So here in this work, our aim was to calculate the effective wake potential in a typical laboratory dusty plasma system, and to also to assess the different factors and how these factors affect the wake field oscillations. So for that, we have considered a model. So in our model, apart from the plasma species, we have applied a magnetic field, and also we have considered the collisions, and flowing ions are also there in our system. So this will mimic the typical laboratory dusty plasma experiments. Now I will not go to the methodology part. So using fluid equations in linear response formalism and harmonic perturbation theory, we can find the daily response function. This is the final expression. So now we can actually, we have analytically, one part we have calculated analytically and one part numerically we have solved. And then I will come to the final result because of the time constraint. So now what we have seen that in a typical laboratory conditions where flowing ions are there, we have applied external field, and we have also considered these collisions among the different species. Then the effective potential among the dust particles will be the linear combination of these two terms. One is W. So here phi y is our well-known equipotential, and phi w is given by this expression. So now when we solve numerically this integral, then we have seen that we have actually this potential is oscillatory in nature. It is like damped oscillation, and also it is anisotropic and attractive in nature. Actually, this is the new thing up here. Now, Yukawa potential is repulsive in nature because between two negatively charged dust particles, we will have repulsive potential. But this wave potential is attractive in nature. Yukawa potential is isotropic, where here we can see R dependence, but wave potential is anisotropic in nature. So we have now further we have analyzed this. Actually, this Yukawa potential is this well known. Most of the
you have 2 minutes.
Yeah, sure. This Yukawa potential, actually in many authors, they have calculated this Yukawa potential, and they have most of the dusty plasma simulations were done on this Yukawa potential only. But here we wanted to actually analyze this phi w a little more. So therefore, we have actually seen the variation of this wave potential with Mach number, this normalized ion flow velocity, how with Mach number this wave field oscillation changes. So I will not explain all the detailed results. Then we have also calculated how this transverse magnetic field affect the wave field oscillations. Then again, in presence of collision, in presence of high collision, what will happen to these wave field oscillations? Now, actually coming to the result, the most important result that we have seen in our calculation is that the interactions among the dust grains can be tuned by controlling parameters like magnetic field and gas pressure. So this is very, very important. That's why we call the wave potential as a tunable potential. So that means we can tune or we can modify the potential with the help of this external field or neutral gas pressure. And because of this, complex plasma shows electrorheological and macrorheological characteristics. So now, as far as electrorheological characteristics concerned, this is very new to complex plasma. Research are going on. Now, electrorheological properties means by adjusting an electric field, we can tune the rheological behavior. Similarly, by applying a magnetic field also, we can tune the macrorheological characteristics. Now, because of this tunable nature, complex plasma may be used as a platform to study magnetoroheological characteristics of soft matter. And as I have already mentioned, this actually dusty plasma is a recent addition to soft matter. There are many properties of soft matter similar to this complex plasma. So, and there is a possibility of using dusty plasma as a macrorheological material in near future. So actually, as a smart material, we can be, this dusty plasma can be used in future. So that's it. Thank you for your attention.
Thank you, Mr. Sajid. It's a very nice presentation.
Very good. Thank you very much.
Any question from the audience? Any question from the participants? I have a question.
Yes, sir.
Why interaction potential generally we took always equa potential, equa type, na? what are the others and why it is preferable? Equipotential is preferable.
Yes, sir. Yes.
Interaction
Sir,
potential.
actually, when we derive the Yukawa potential, so then, sir, we do not we assume that these electrons are Boltzmannian.
Yeah.
Yes, sir. Sir, am I audible? Actually, my network connection is not stable, I think.
Okay, that's why the voice cut. Voice cut is there. Anyway, go on, carry on.
Okay. Okay, sir. Sir, this Yukawa, when we derive ions are Boltzmannian. So now, sir, you have already mentioned that the non-Maxwellian distribution of the electrons and ions. So now this is just an approximation, sir. This Yukawa potential is a very lame approximation of the complicated form of this interaction potential. So therefore, in a typical laboratory conditions, when flowing ions will be there, then collisions will be there, then sir, dust charge fluctuation will be there. So then we have to go for more complicated potential, like this wave potential or some kind of shadowing potential, sir.
Okay. Okay, good. Thank you. Any other questions? If not, let us thanks Biswajit. Thank you for your presentation.
Thank you. Thank you very much.
Next, we have.
We'll have next Interdisciplinary Studies from Guwahati University. So Sumitra, are you there?
Yes, I am.
Yeah. So okay, can please share your screen.
Interdisciplinary.
Okay, let me stop. Okay. So yes. He will be speaking on thermal instability simulation using fast electric transport.
Okay, is my screen visible?
Yes, yours is visible.
Okay.
Please proceed.
So good evening, everyone. Myself, Videndra. I am a PhD student at Department of Physics, Gautam University. So at the very first, I would like to thank the organizers for providing us a platform to share our work, which is thermal instability simulation using flux-corrected transport. So this will be the outline of my talk. Now coming to the problem, thermal instability. As you all know, large-scale condensations in our universe are a result of gravitational force, which is known as Jeans instability. But there is another process which can also explain some small-scale non-gravitational condensations in the interstellar medium, or say intercluster medium, or in the solar prominence region. This process is known as thermal instability. So basically, what happens is that the thermal equilibrium becomes unstable, leading to condensation of high density and low temperature, which are known as clouds or filaments, and these are known as the precursors of stars or other interstellar objects formations. Now, the figure actually shows the hydrogen ion abundance in the Milky Way galaxy, so that these bright patches are the regions where hydrogen is condensed, abundantly present. Now, coming to the governing equation, we have the fluid equations, continuity equation, then the momentum equation, energy equation, and this in the energy equation, energy is divided into two parts: the kinetic energy and the thermal part. And this is the this one is the ideal gas law. So basically, what happens in the energy equation? There is two terms added. One is thermal conduction term, and other one is radiation heat loss term. Now, this thermal conduction term Q is actually basically we all know that Q is K del T, and it basically takes care of the thermal conduction part. Now, if we do a linear perturbative analysis of these fluid equations, we come to two modes of instability. One is condensation mode given by the first condition, and second one is the wave mode. Now, the sigma k part in the conditions is actually positive, and if we do not consider thermal conduction, this sigma k part can be neglected. So it finally comes down to sigma t and sigma rho part, and which are basically directly dependent upon the L rho and LT at the bottom, you can see, and this it actually finally comes down to these two terms. Now, from our simulation, so basically, in this, these are the plots from our simulation, and the first plot is actually for the this is the normal waveform after perturbation, and where there is no thermal conduction and no radiative heat loss. So it goes like this. And the second part, we fix the, for the second plot, we fix the LT term and change the L rho term. And we can see in the second plot, the waveform is actually growing and becoming unstable. So this is actually the wave mode of instability. And for the third part, the condensation happens and condensation mode of instability is showing. The last, the fourth plot is actually for we are plotting actually for the effect of thermal conduction on plasma waves, and we are actually plotting decay versus thermal conduction coefficient parameter, and this is actually working as the benchmark of our simulation. As you can see, the blue line is the analytical relation, and these bright red points actually are the simulated points from our FCT simulation. Now, coming to the nonlinear part, nonlinear heat loss part, we are using the heat loss term prescribed by Inuska and Koyama, given by this, we can see in the second term net heat loss, rho lambda minus gamma. This lambda is actually basically the cooling function, and gamma is the heating function. And Q, we are using the thermal, Q is the thermal conduction part, and that thermal conductivity coefficient Kc, we are using the function used by, prescribed by Spitzer and Parker. Basically, the thermal conductivity coefficient is also a function of the temperature, as can be seen in case of interstellar medium. And the table actually shows the parameters for our simulation. Now, in this plot, actually, we are showing the density distribution and the temperature distribution for the initial time and after the instability grows. So at 800 million years. So on the left-hand side, the initial plot, this is actually, the first plot is the initial plot. We are basically using random perturbation. And the second plot is for, is after the instability grows and it is in presence of thermal conduction. And the last plot is only in presence of radiative heat loss and no thermal conduction. And in the right side, we are plotting the temperature distribution for the same cases as have been in the left. Now, one interesting observation is that the presence of thermal conduction actually reduces the instability. Thus, it counters the instability, thermal instability, and thus it reduces the number of condensations and their heights. Now, these are our two-dimensional results. So, in 2D, the density distribution of different at different time intervals are shown, like initially in 0 million years, and then 200 million years, 500 million years, and 1 billion years. So as you can see, after initially the perturbation is random, there is no condensation. Then after some time, in about 200 million, condensation starts to build up, and at 500 million years, like filamentary net-like structures are forming. And finally, after at 1 billion years, after the thermal instability saturates to a quasi-unstable, quasi-unstable state, the cloud-like formations are seen. So this, in the right-hand side, this 3D view is actually for the 500 million years plot, and at the bottom right corner, the plot is actually for, we are plotting the growth rate for the 2D simulation and the 1D simulation we have done earlier, and we can actually see the linear growth rate is about of the same order. So this is a simple animation from our 2D simulation. It's not playing. I hope it plays. Yeah. So as you can see, as time passes by, instability grows and thermal condensation begins, and it forms a net-like structure which later condenses more and then disperses like in like cloud-like forms. Yeah. So in summary and conclusion, we have basically observed two modes of instability, wave mode and condensation mode, as prescribed by GB field. Then we have found that the thermal conduction actually dampens the plasma wave, and it also reduces the number of condensation due to radiative heat loss. Then finally, in 2D simulation shows the formation of condensations into a net-like filamentary structure, and after it reaches a quasi-unstable state, it forms like cloud-like structures in the later part. So, thank you.
Thank you, Videndra.
Yeah.
It's a nice talk, probably a heavy simulation work.
Yeah, thank you, sir.
Any questions from the participants? Can I ask something, Hitendra?
Yes, sir. Yes, sir. Sure.
Just go to the basic governing equations slide.
Yes, sir.
Okay. This is basically a fluid simulation.
Right, sir. Fluid simulation. We are using constructed transport simulation. It is based on originally from Borisian books, and we have modified it and accustomed it to our need.
Can you just illustrate me the energy equation? I am not getting clearly. Energy equation.
This one, sir?
Yeah, yeah.
Yes, sir. So basically, in the energy equation, this is the actually we have changed it to to our flux corrected transport based based form. So it's generalized continuity equation form. So basically, this energy term, it is the energy into the species velocity, as you can say, speed. So this energy is basically thermal energy and kinetic energy, and this is kinetic energy and thermal energy. So this is it. And in the right hand side, we are adding the this is the heat loss. This is the heat loss, and this is the thermal conduction part.
Okay. And how you see the perturbation? How you see the perturbation?
Yes, sir. We are basically using for our case, first we have used a sinusoidal kind of perturbation.
Okay.
For these things to verify the two modes of instability. But later for this, we are using random perturbation, as you can see from here.
Yeah, I heard. Okay. Okay. And can't we see the electric field behavior?
No, actually, sir, because in ISM mostly hydrogen ions are present. So one species. So for ISM study, people usually do not consider a Poisson's equation electric field.
Okay.
Basically, one species plasma kind of thing, because their density is very small. Like the number density is like 1 to 10⁻² per centimeter cube. So this kind of things.
Okay. Okay, thank you.
Yes, sir. Thank you. Thank you, sir. Should I unshare my slide?
Yeah, sure.
Yeah, thank you.
Okay. Let us move then to our next speaker. Who's next? Darpan?
So the next speaker is Prince Das.
Prince.
Yes,
Prince.
Hello. Yes, you're audible. Yes.
You can start sharing.
Yes, sir. I have shared the.
Yeah, it will come. Yeah, it's visible. Good.
Good evening to all the respected dignitaries. My name is Prince Das. I am research scholar from Assam Science and Technology University in the Department of Energy Engineering. My topic for today's presentation is surface modification of polymeric membrane through cold atmospheric pressure plasma. So this is introduction, research case, objectives in sequence. Now coming back to the topic, we know that wastewater is a used water that contains pollutants, contaminants from domestic, industrial, or agricultural activities. Now, directly discharged to the environment can create hazardous and public health issues are also there. And at larger scale in industries, economic benefits are also there. So we have to treat this wastewater before discharging it directly. So to treat this wastewater, we have various methods are there, like physical, chemical, biological, and there is membrane technology. So in membrane technology, what we do simply there is a polymer membrane, which is a semi-permeable barrier made from polymers used to separate substances in a mixture. Now we use these polymers to treat with the wastewater. But the problem with polymer technology is that there is membrane fouling, and membrane fouling occurs due to various reasons like particulate fouling, organic fouling, biofouling, and inorganic fouling. So in the recent time, plasma technology is used to counter that fouling problem of membrane technology. And in this regard, cold atmospheric pressure plasma I have chosen to modify the surface of the polymeric membrane. Now, what is a cold atmospheric pressure plasma? So it is a type of non-thermal plasma, that is the electron temperature is greater than the temperature of ions and neutral species. It operates at atmospheric pressure, and its application is for surface modification, then medical treatment and environmental applications. Now, these are literature review. So the main components of cold atmospheric pressure plasma are reactive oxygen species, reactive nitrogen species. So reactive oxygen species are actually responsible for oxygen containing functional groups, which will increase the hydrophilicity of the membrane. And to reduce the membrane fouling, we need to have increase in hydrophilicity of the membrane surface. Then reactive nitrogen species are basically responsible for creating antimicrobial part. Then to create that cap plasma, we used the method dielectric barrier discharge. So here basically high voltage is applied across the electrodes. The gas between them ionizes, creating plasma. Now these are the normal ranges that is in our project. We have used the inter-electrode gap measure, that is 3.0 mm. Then pulse width is 30 microsecond and amplitude of 4 kV. So the membrane that we have chosen, we have fabricated the membrane in our lab. So this is the fabrication process. You can see that the polymer should be dried without any moisture in it. So it was placed at oven at 80 degrees centigrade for 12 hours. Then 5 grams of solvent, that is DMAC or DMF, with 2 grams of polymer were mixed to make 7 grams of 20% of polymer solution. So then the solution was inserted into stirrer so that the solution become homogeneous without any air bubbles. So after the solution was prepared, it was cast in a precise thickness by filming machine on a flat glass micrometer. Film applicator was used for this operation. So this is the final membrane that we have fabricated. Then the characteristics of the plasma, that is Langmuir probe and OES. From the characteristics, we have found that the electrode temperature is 1.39 EV and plasma density is 2.74 into 10 to the power 14. It is actually. Then the distinct peaks that is obtained from OES is at 724.4 nm. Then for oxygen atom, and for OH, this is 295.2 nm. Then from the FDR results, we have found that at 1708.78 cm, the carbon CO stretching is there. Now, one problem with FDR is that plasma penetration depth is higher as compared to the FDR. So in in the FTR diagram, the functional groups that we have obtained, those are actually at the surface of the polymer, at the polymer membrane. From the same images, you can see the enlargement of the pore, and from the AFM, we have seen that the surface roughness has increased by calculating. Significantly, the surface roughness has been increased. Now, after treatment, the polymeric membrane were stored at atmosphere and water, and we have measured the contact angle for about, say, initially 72 hours. And then we compared with that, what is the effect of aging on the plasma treated polymeric membrane. So in that regard, we have found that when we have placed the membrane in atmosphere, the hydrophobic recovery, that is back in that state to back to its initial state, is more in case of atmosphere rather than in case of water. Then this was the permeate flux for mud water, and we have seen that for plasma treated surfaces, the permeate flux has increased. So this is one of the reason for which fouling is there. So with plasma treatment, we have seen that permeate flux has been increased. So we can see that we can counter the fouling problem of the polymeric membrane. In conclusion, from the FDI results, we have seen the carboxyl sulfone functional groups, which are responsible for increment in hydrophilicity of the membrane. Then from the same images, we have seen the macro voids and plasma etching. Then from the AFM images, surface roughness has been increased by 38% for 30 seconds of cap treatment. So for only one treatment we have considered, that is 30 seconds. And hydrophobic recovery is less in water medium as compared to atmosphere. So in water medium, the possible reason for this may be dipole-dipole interaction between the polymer surface and water molecules, which actually slow down the recovery process. But in case of atmosphere medium, since there's a variation in relative humidity and temperature, so the factors which are responsible for hydrophobic recovery, that is diffusion and reorientation, these two processes are very high in case of atmospheric medium. And plasma treated membranes undergo filtration process for mud water, which ultimately increase the permeate flux from 32% for 30 seconds of plasma treated membrane. So in the future scope, I will go for the complex nanostructure, investigating the creation of complex nanostructures on polymeric surfaces using CAMP plasma. Then to identify the potential application of plasma treated membrane for other fields like oil water separation and antimicrobial properties. There is gas separation. For gas separation is also membrane is used. So this is our lab. So my guide is Dr. Bharat Kakati, assistant professor from Department of Energy Engineering, Assam. So these are some references. Thank you.
Thank you, Prince. And this was a very interesting talk, I think, in context of present scenario of the plasma technology. And I also mentioned in my presentation, really it's a very nice work under this. So you are using DBD, na?
Yes.
Why DBD? Is there any other option? And what are the advantages? I think there are other methods also, na?
Yes, sir. There are other methods are also there, but sir, in case of that DBD, basically the requirement of vacuum pump. The requirement of vacuum pump is not there. So this was one advantage with respect to
atmospheric pressure. We don't require vacuum pump.
Yes.
Anyway, DBD is one of the simplest one, but nowadays there are some other methods which are more means helpful, or in some way it is more accurate, I can say. Okay. So just explore it also. And, yes. And any other question from the participants? Any question?
Yes. So if there are no questions, so we can.
If there is no question, then we can move. Thank the speaker and move to the next one.
Yes. So Yeah, thank you, Prince. So next we have Krishnanka Jyoti Vaishya from Debajyoti University. So he will be speaking on. Are you there, Krishnanka?
Krishnanka, are you there?
Yes, I am here.
Okay.
Yes. Okay. So here he will be speaking on 30-year analysis of rainfall pattern during the monsoon season as observed over Debajyoti case study.
Yeah. Is my screen visible?
Yes. Please proceed with full screen mode. 10 minutes.
Okay. Is the full screen visible now?
Yes.
Okay. Good evening to everyone. I am Krishnanka Jyoti Vaishya from the Center for Atmospheric Studies, Debajyoti University. Here I'll be presenting a 30-year analysis of the rainfall pattern during the monsoon season as observed over Debajyoti. So we are already familiar with the impacts of global climate change, which extends far beyond temperature fluctuations. This change also impacts the rainfall pattern over a certain place, which in turn impacts the hydrological cycle. In this study, we will cover a temporal trend of the rainfall accumulation from 1994 to 2023, and it will enhance the understanding of changes in the rainfall pattern with their implications for the region's water security, agriculture, and socioeconomic stability. For this, we have taken IMD data, Indian Meteorological Department's rainfall accumulation data, with a resolution of 0.25 degree into 0.25 degree. Now, why is monsoon rainfall important? Firstly, it impacts the life cycle. How it impacts? It impacts by providing necessary water to numerous species, animal habitat, plant growth, and the ecological balance of the region. Secondly, the hydrological cycle, as rainfall replenishes water bodies, maintain groundwater levels, etc. And any extreme events of rainfall will lead to water scarcity or even flooding. Thirdly, the socioeconomic stability. Agriculture is a primary source of livelihood, which is dependent on the water cycle for its growth, and any disturbance to it will lead to crop failure, economic hardships, and food insecurity. Fourth is the water security. And we already know of the challenges we have to face if there is any change in the rainfall pattern, because it will be rainfall pattern because rainfall from rainwater harvesting is also one kind of adaptation. We have to do one kind of government policy from which water has been distributed to households, and also any changes in it will lead to a challenge in meeting the increased water demands of the growing population. Then this study shows a variability in the accumulated rainfall with a decreasing trend as the timeline proceeds to the recent years. There were some occasional highs and lows, with the highest during the year 1999 with a total of 1753.27 mm, and the lowest during the year 2021 at 1018.59 mm. We have identified the years 1995, 1999, and 2007 as the increased rainfall accumulation period, with each year exceeding 1700 mm. And conversely, the years 1996, 2005, 2011, and 2021 are identified as decreasing periods, with each year having rainfall below 1200 mm. We have also studied these 30 years as 3 separate 10-year periods. In the first decade, that is 1993 to 2024, the rainfall accumulation ranges from 1059 to 1753.27 mm. The second half, as you can see from the graph, the second half of rainfall accumulation is almost consistent around the decadal mean. The decadal mean of this rainfall accumulation is almost 1409 mm, and the second half of the decade is almost consistent around 1400, the value of 1409 mm. And the overall rainfall accumulation suggests an increasing trend as we go from 1994 to 2003. The next decade, that is 2004 to 2003, had a decreasing trend, with most of the years being along the decadal mean of 1380 mm, while the years 2005, 2011, 11 being extremely low contributed heavily to the overall decreasing trend, thereby marking some significant fluctuations in rainfall pattern. The third decade, that is 2014 to 2023, however, shows a rather unusual trend, with only 4 of the 10 years being above the decadal mean of 1316.46 mm, while some of the other 6 years being extremely low contributed to the variable trend line through the years. In comparison to the other two decades, here the decadal mean of rainfall accumulation is reduced almost by 100 mm. This decrease in decadal mean accumulated rainfall throughout the 30 years actually suggests a shift towards the drier conditions compared to the previous decades. And causes for this rainfall variability, well, the first and the major cause is already known to us, that is climate change. And second, it is the ENSO, also known as El Nino Southern Oscillation. Actually, El Nino and La Nina are some weather patterns associated with trade winds. And these trade winds brings along the drought, means the El Nino brings along the drought, and the La Nina brings about the monsoon season, rainfall during the monsoon season over particularly the Northeast India. Third is the local topography. That topography means the topography is quite amazing over Dibrugarh. The presence, there are Himalayan foothills surrounding this region, as well as the Brahmaputra River and other these tea gardens. These all contribute to the rainfall pattern over this region. And fourth is the anthropogenic activities. We are also familiar with these anthropogenic activities. That means human activities, which such as deforestation and urbanization, and how it has affected us globally. Next are the challenges. Any increase or decrease in the rainfall poses a challenge for agricultural practice over any region, not only Dibrugarh. It poses a great threat to the agricultural practice over a certain region. And fluctuations in this rainfall pattern influences the water management system from irrigation to household activities. Thirdly, it is the adaptation. With this change, it is high time to develop adaptation strategies for sustainability of the agricultural practices. And fourth, it is the weather forecasting. Weather forecasting is the one of the most essential, means it is one of the essential steps that needs to be undertaken at a faster rate, because improvement means if weather forecasting is undertaken at a faster step, then it will lead to improved weather forecasting, and it will lead to proper planning of the plantation and other agriculture practices, as well as water management. And these are some strategies for adaptations which we need to undertake for the sustainable development of the region, as well as mitigating the problems caused by extreme rainfall, as well as some droughts, extreme rainfall, as well as drought which occurs in between some years that had extreme rainfall. Then these are these conclusions. Significant shift in rainfall pattern. Over the past 3 decades, Dibrugarh has experienced a notable decrease in the seasonal rainfall, especially during the monsoon months. Then this decline has major impacts on the region's water resources, agricultural practices, and socio-economic stability. Thirdly, there is an urgent need for adaptive strategies to address these changing patterns and their effects. And future efforts should include exploring long-term trends, developing advanced forecasting models, and understanding climate change impact on the monsoon system in Dibrugarh. Lastly, thank you to everyone for listening, and thank you to the organizers as well for arranging the conference and giving new researchers like me an opportunity to present my preliminary work. Thank you so much.
Thank you, Krishnanka.
Thank you, sir.
Any question from the participants?
I have a question to the speaker.
Yes.
Hello?
Yes.
Yes, I'm listening.
Yeah. So in your study, you have taken a cumulative time of 30 years now, or the
Right, sir.
rainfall that Dibrugarh has suffered.
Right.
So are you using any kind of satellite data collection technique for this study?
No, actually, my research center, that is Center for Atmospheric Studies, it already has some in situ instruments like the AWS, Automatic Weather Station. But unfortunately, the AWS was installed recently. So the data that is available from IMD, that is in Indian Meteorological Department, I have been using that only for this research purpose. And in further course of time, I'll try to use any satellite data that is available. So for this, I
Okay,
have
okay.
been
Actually,
using
there
only
are some.
IMD data. Yes, sir.
So there are actually some techniques, techniques of satellite data collection, like INSAR, PS INSAR. So like as you have included the time in that the time factor in your studies, so I think that PS INSAR or DINSAR technique will be very much effective, because these techniques of satellite data collection includes the time factor in them, and also they study the geomorphological or any kind of activity that has been happening in a place. So if you can do that, that it will be good. But that will be make your research more profound. I think so.
Okay, thank you so much for the suggestion. Actually, I am very much new to this field, so I have been doing only the preliminary work. The further work will be done in the near course of time, sir.
Okay, great. Yeah, by the way, the presentation was very good. I really enjoyed it, and all the best for you.
Thank you so much, sir.
Okay.
I have faltered a lot in the middle.
Okay.
Thank you, Krishnanka.
Thank you, sir. So I'll answer it. Stop sharing.
If there is no question, then we can move forward. Darpan?
Yes, this is the end of this session, the last session of the last day of this conference. So thanks a lot, Dr. Kamal Saharia, sir, for your cooperation and chairing this session with us. So
Thank you.
Thanks a lot, sir.
Thank you too.
Yeah, thank you.
So
it's over to you, Vivek.
yes, so yeah, so thank you so much, Dr. Saharia, sir, for your time basically and for the beautiful talk. So this marks the end of the 3-day national conference. So thank you all. This would not have been possible without you basically. So I'd like to call upon our IQAC coordinator, sir, Dr. Nabin Kumar Pokhrel. Now he will be delivering the concluding remark and vote of thanks. So over to you, Dr. Pokhrel.
Thank you, Vivek. Let me start. Good evening to all present here. As we conclude this enlightening physics conference, we reflect on the wealth of knowledge shared, the innovative research presented, and the stimulating discussions that have taken place over the last 3 days. This gathering has not only highlighted significant advancements in the field of physics, but also fostered collaboration and inspired new ideas that will propel future research. I'm confident that the ideas shared by the researchers from various areas related to physics will help them develop new innovative techniques and concepts. We extend our heartfelt gratitude to all plenary speakers, presenters, and attendees for their valuable contributions and active participation. Even though we recognize this event as a national one, but we got a good number of abstracts from abroad. We are thankful to the plenary speaker and participants joining us from abroad. Special thanks to the organizing committee for their hard work and dedication in making this event a success. As a newly established department in the college, I can feel the challenges faced by the Department of Physics in successfully and smoothly running the conference. Kudos to them. Additionally, I would like to thank the Assam Science Society and ESTEC Guwahati for their support throughout the conference since its inception. Let us carry forward the insights gained and the connections made here as we continue our pursuit of scientific excellence. Together, we are shaping the future of physics. Thank you, and we look forward to seeing you in our next conference. Regarding Bhawanipur Anchalik College, our college is a multidisciplinary college having all 3 streams: arts, science, and commerce. And the science stream is in its infant stage, having currently enrolled only 2 batches. One is the 3rd semester and the newly admitted 1st semester. Please visit us and give us your valuable suggestions for the upliftment of the college. I request you all to visit us whenever you cross Bhawanipur. Our college is just adjacent to NH27. It's well connected by the national highway. Whenever you cross Bhawanipur, please do give us a visit. And there is an important announcement regarding the conference. We will be sharing the feedback form shortly. I request you all to please submit your valuable suggestions, reviews, or comments, whatever you say regarding the conference. Your honest feedback in this regard will help us to improve in the coming days. And if you don't want to reveal your identity in the suggestion, you just type anonymous in the place where the name should be written. We eagerly await your comments. Thank you again. Thank you for joining the conference. Now I request Dr. Thapa to conclude the session, and in case of any official announcement, please proceed.
Yeah, thank you, Dr. Pokhrel, for your motivation and kind words. So you have been the driving force of the conference since the beginning. Okay, so regarding as IQAC coordinator mentioned, we have a couple of announcements. So regarding, as you mentioned, regarding the feedback form, so we'll be having we'll be providing you a Google form where you will be you can provide your raw comments, raw suggestions, anything, and in the feedback form itself, we also want to correct the names of some of the participants for the issue of certificates. So kindly, if you want, it will be better if you so I think it will be a good option if we float another Google form for search for the names, affiliations, titles of your talks, and abstract ID. So we'll float one form where kindly fill it within, I think, 7th of July. We'll float it today itself so that we can issue the certificates in due time. And regarding, and few of the participants mentioned about the issuance of payment receipts. So we'll be issuing those. We are in the process of issuing them. So they are, I think it is already done. So we'll issue them together along with the certificates to the respected participants. And one more announcement regarding the full paper submission. So we already mentioned in the registration form, there was one question regarding if you want to publish your work as a full paper. So we have your answer. So accordingly, we will float another form, Google form, where you can upload your full paper. The format, the template of the full paper is already in the website. You can kindly go there and check it accordingly. So regarding the publishing it, so we are lucky enough, we are fortunate enough that the Assam Science Society has agreed to publish the full papers as book chapters in one of their books. And we'll be sharing the details regarding a part of the publishing charges will be covered by some external funding support, but a part will have to be contributed from the applicant side. So we'll let you know regarding that particular publishing charge, so in due course of time. And yes, that's all for the announcement. And one last one, that this year, since due to some logistic issues, we had to conduct the conference in online mode. But we look forward to look forward to organizing it in offline mode. Offline mode is always a better option. You get to know more people. You get to have more good connections. So we look forward to having offline conference, this conference next year. So and that's all from our end. Thank you very much for your time. Thank you very much for the enthusiasm of the participants. We loved it. We loved your enthusiasm and the overwhelming response from not around the nation but around the globe. We never expected we'd get such a good response at our debut itself, but we got a very good response, and all thanks to you. And okay, then yes, it has been a long day. I won't take much of your time. So it's been a long day, and good luck, and hope to see you soon. Okay, good night. So I conclude the meeting. Good night.